Chapter 1 of The Romance of Modern Engineering. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Krista Zaleski. The Romance of Modern Engineering by Archibald Williams. Chapter 1 The Harnessing of Niagara. It is indeed hard to conceive that anyone in full possession of his senses could stand unmoved in the presence of a great waterfall. The sight of huge masses of water, tumbling as it were from the blue of the very heavens, dissolving into arrowy streams as they descend before the final crash into the mist-laden gulf below, must appeal even to the most brutalized mind by its sheer majesty and magnificence. What then are the thoughts of those whose emotions are strings easily attuned to the grander moods of nature? The first impression is doubtless one of awe, called forth by the involuntary comparison between our own insignificance and the immensity of the force before us. What right have we, frail creatures of the day, to speak of lordship of creation face to face with this watery avalanche that has thundered down for centuries, nay, thousands of years? What can human art avail against the violence of those ceaseless, seething torrents, stunning our ears with sound, dazzling our eyes to weariness by their motion? Then follow what we may call the secondary emotions. The poet feels the inspiration of descriptive verse, the artist reaches for his pencil, the engineer or man of science, not less alive, perhaps, to the artistic beauty of the scene, yet from habit and profession sees here a mighty source of power, of motive force to drive the myriad whirring wheels conjured into being by civilization and its needs. "I look forward," said Lord Kelvin at Niagara Falls, "to the time when the whole water from Lake Erie will find its way to the lower level of Lake Ontario through machinery, doing more good for the world than that great benefit which we now possess in the contemplation of the splendid scene now presented by the waterfalls of Niagara." On another occasion, another famous electrician, Sir William Siemens, looked upon the scene with similar thoughts. The stupendous rush of waters filled him with fear and admiration, as it does everyone who comes within sound of its mighty roar. But he saw in it something far beyond what was obvious to the multitude, for his scientific mind could not help viewing it as an inexpressible manifestation of mechanical energy. And he at once began to speculate whether it was absolutely necessary that the whole of this glorious magnitude of power should be wasted in dashing itself into the chasm below. Whether it was not possible that at least some might be practically utilized for the benefit of mankind. Footnote from William Pole's Life of Sir William Siemens. End footnote. It seems as if we may trace the finger of a perverse fate in the necessity that drives us, in an age when man is peculiarly appreciative of the beauties of nature, to invade with our instruments and machines some of the fairest spots on earth. To obtain a good water supply, we throw a huge mass of masonry across the Nile, and dam lovely valleys. To furnish us with timber, stately forests are levelled. To yield us coal and iron, smiling countrysides are disfigured by towering chimneys, and the atmosphere filled with a foul reek. And that our source of energy may be in proportion to our wants, the rushing mountain stream in Norway, Switzerland, Italy, France, and elsewhere is hemmed in by walls and weirs, and its only way to freedom lies through huge pipes to whirling turbines. Much as we must regret these things, we know that they are inevitable. Many of the conditions of life are changing. Today, that nation is ascendant which is not necessarily hardiest, or numbers the bravest hearts and stoutest arms, but, as we are told, the one which can produce the cheapest ton of steel. In other words, wealth holds the balances. Wealth depends on commerce. Commerce comes to those who are able to hold their own against the world in the fierce struggle of economical production. To carry the train a little further, economical production is based upon a plentiful supply of cheap energy, whether in the form of motive force or heat. The manufacturer is so eager to clip off a decimal of a cent here or a fraction of a penny there from the cost at which he can produce his goods that any method for cheapening the prime mover, power, of his factories is gladly welcomed. The engineer is always busy bringing the latest appliances of science to his aid. We hear of enormous steam engines, many times more efficient than those of half a century ago, of great machines actuated by explosions of gas, formidable competitors to giant steam, and water power in its newest developments is fast pushing its way to the front, threatening both steam and explosive vapor. Coal fields are exhaustible, oil fields are exhaustible, but a river flows on forever. Once in harness, water becomes man's servant for the ages. As a consequence of the new lease of life given to water power, we may expect to see great changes in the industrial world. Hitherto, trade and manufacture have gone to those countries which possess well-worked coal fields. In the future, a bid for supremacy will be made by those districts where the force of gravitation, as represented by falling water, may be cheaply transformed into other forms of energy. Numerous experiments and statistics prove that the steam engine has almost reached its limit of economy. We cannot expect to get much more power from every pound of coal we burn than we do now. The cost of raising that pound from the bowels of the earth tends to increase as the supply decreases. Many great water power installations are already in full working. On the Rhone, the Rhine, the Adda, the Reuss, the Aar, hundreds of thousands of horsepower are daily produced at the turbines and flashed noiselessly to thousands of machines through great cables pulsating with electricity. But at Niagara, the electrical mecca of the world, nature has furnished mankind with the most magnificent of powerhouses. Here the overflow from 4 lakes, or rather inland seas, linked so as to form one huge reservoir of 90,000 square miles, is herded by cliffs into a narrow channel and compelled to make a magnificent leap of 165 sheer feet into the lower river. The figures are almost appalling. A solid wall of water 20 feet deep, representing 275,000 cubic feet per second, passes over the falls continuously. Its daily force, some 7 million horsepower, equals that of the latent power of the 200,000 tons of coal mined every 24 hours throughout the world. Think of the thousands upon thousands of stately ships furrowing the ocean, the myriads of locomotives that flash over the ironways, the huge boilers bringing movement to countless factories. Their combined average energy is not equal to that running to waste at the roaring of the waters. Now, were Niagara situated in some desolate, sterile Arctic region, the eyes of engineers would still turn longingly to its enormous power. Nature has, however, dealt kindly with the human race in placing the falls where they are. In a healthful country, teeming with natural resources, among peoples of superabundant energy, it would be almost less a matter for surprise were the waters to leap upwards than that the enterprising American and Canadian should fail to utilize the vast power flowing past his doors. Niagara Falls are the right thing in the right place. The time has come when toll can be taken of those rushing waters. Electricity, the genius of the 20th century, has long burst its swaddling bands and can be united to water in a most advantageous partnership. Ever since the first sawmill was set up at Niagara in 1725, the idea of subjecting some part of the enormous power of the falls to industrial uses has stirred the inventive faculty of engineers and manufacturers. Early in the 18th century they cast about for a means of harnessing this lavish provision of nature, but the scientific knowledge of the world had not yet sufficiently advanced. In the 19th century, steam and steam power made such progress that manufacturers quitted the riverside for the coal field. But the advantages of water were not forgotten. In 1842, we find Augustus Porter, one of the principal proprietors of Niagara, proposing a system of canals to the high bluffs overlooking the falls, whence the water might fall over large wheels to drive the machinery of mills. As a result of continuous negotiations, a syndicate of gentlemen obtained a right to construct a canal 35 feet wide, 8 feet deep, and 4,400 feet long, from the water of the upper Niagara River to those bluffs, where, by 1885, the available capacity of the canal was being converted into some 10,000 horsepower. Still greater projects were to follow. Mr. Thomas Evershed, an engineer who has done noble work in protecting the falls from utilitarian desecration, was called upon the same year, 1885, to develop a plan whereby the beauty of the falls might be preserved, and at the same time a large bulk of water turned to practical purposes. He conceived the idea of tapping the Niagara above the falls, precipitating the water into a huge pit where machinery would be stationed, and carrying the waste along through a large tunnel nearly 1.5 miles long to an outlet below the falls. His plan was strongly opposed as impracticable, but in spite of discouragement, 8 gentlemen of Niagara obtained from the New York legislature in 1886 a special charter, granting the right to take from the upper river sufficient water to develop 200,000 horsepower. A second concession, of a later date, from the Canadian government permits the same company, now known as the Niagara Falls Power Company, to draw from the Canadian side an additional 250,000 of horsepower. It has been estimated that the difference of level made at the edge of the falls by the withdrawal of all this water will be but a few inches, not enough to detract in any way from the scenic effect of Niagara. The company also bought land extending for about 2.25 miles along the river, intending to lease or sell it for factories as soon as the plant was in working order, and to erect on it a residential quarter for the operatives. On paper, the company's prospects were decidedly attractive. Their total horsepower represented more than a third of the total produced by water in the States in 1880. Niagara was within a night's journey of Boston, New York, and Philadelphia, Chicago, Pittsburgh, Toronto, and Montreal. Within a radius of 400 miles dwelt 1/5 of the population of the States. It was the natural port of the Great Lakes. It also lay in the neighborhood of the great coal fields. This last consideration raised the question: could Niagara Power compete successfully with steam-made power? After careful consideration, the company decided that it certainly could, and might even be carried at a profit into the coal fields themselves. As soon as great financiers had lent their names and support to the undertaking, the officers and directors of the company proceeded to attack the problem of how best to convert the water they had permission to control into energy. The problem, says Mr. L.B. Stillwell, electrical engineer of the company, was one without precedent in its magnitude and almost without parallel in its significance. The promoters of the scheme made up their minds to spare no expense or trouble to ensure the installation of the best machinery in the best possible manner then known. They called in to their aid leading engineers and electricians of all countries, thus exhibiting a breadth of policy superior to all motives of natural prejudice. As regards the method of supplying and carrying off the power water, it was finally decided to construct a surface canal above the falls, 250 feet wide at the mouth, and running into the land for a distance of 1,500 feet to the site of the powerhouses, the latter to contain eventually machinery capable of delivering 50,000 horsepower. A wheel pit would there be dug to a depth of 178 feet, and connected at the bottom with a tunnel 7,000 feet in length, having a slope of 6 feet in 1,000, and a maximum horseshoe section of 21 feet by 18 feet 10 inches. Water would flow through the tunnel to the outlet below the falls at a rate of a little less than 20 miles an hour. The questions of machinery and power distribution were not settled so easily. In the first place, the forms of turbine most popular at that time did not appear convenient for the installation in question. In the second, given a most efficient turbine, how was the 5,000 horsepower developed by it to be brought to the surface many feet above? In the third, how was the power, when delivered to the surface, to be distributed in the neighborhood and at a distance? The company did a very wise thing. Instead of sitting down and trying to think the matter out by themselves, they appointed an international commission, consisting of Sir William Thomson, now Lord Kelvin, as chairman, Dr. Coleman Sellers of Philadelphia, Lieutenant Colonel Turretini of Geneva, Professor G. Mascart of the College of France, and Professor William Cawthorne Unwin, Dean of the Central Institute of the Guilds of the City of London. This commission, established in London, was empowered to obtain records of all sorts that should help to solve the three problems now before the directors of the company, and to award $22,000, £4,400, in prizes. Inquiries and examinations concerning the best-known existing methods of development and transmission in England, France, Switzerland, and Italy were made personally by the officers and engineers of the company, and competitive plans were received from 20 carefully selected engineers, designers, manufacturers, and users of power in England and the continent of Europe, and also in America. Footnote: Cassier's Magazine. End footnote. The first important result of this commission was that Messieurs Feisch and Picard of Geneva were selected to design the turbines. The character of a turbine is probably widely known to the public, but to prevent any possible misconception, we may here state that a turbine is composed of a number of vanes, set spokewise round an axis, and enclosed in a cylinder in such a fashion that all water passing through the cylinder must push the vanes aside in its course, imparting to them and their axis a circular motion. In order to make the water more effective, fixed vanes are attached rigidly to the cylinder walls at a short distance from the moving vanes, so as to deflect the water onto the latter at the most efficient angle. The turbine principle has lately been employed largely with steam to drive torpedo destroyers and merchant vessels at high speed, and to supply motive force for dynamos and the ventilating fans of mines. The Niagara turbines are about 5 feet in diameter and have a vertical axis. A peculiarly ingenious feature of their construction is that they are made in 2 stories, as it were. The top vanes the larger, and the water from the penstocks or supply pipes is made to enter between the 2 sets. The pressure against the upper vanes being greater than that against the lower vanes, the turbine is endowed with sufficient lifting power to support the entire weight of all the revolving parts, namely the wheels, the vertical shaft, and the revolving parts of the generator driven by the wheel. The mention of the shaft brings us to the second point under investigation, the best means of bringing 5,000 horsepower from the point of development to the surface. For this purpose it was decided to employ a shaft of steel tubes 38 inches in diameter, contracting at intervals into a solid bar 11 inches in diameter, to run in journals for the sake of steadiness. At the upper end of the shaft should be placed what? The answering of this question demanded the most careful investigation. In 1890 there were people to plead for 4 different methods of power transmission. Some could point to the good work done at Schaffhausen and elsewhere by turbines driving manila and wire ropes. Others to Geneva, where turbines transmitted hydraulic pressure for considerable distances through pipes. At Paris, again, the compressed air system had been largely developed, and in America this method had a stout champion in George Westinghouse, the famous inventor of the air brake for trains. The fourth method, that of transmission by electricity, could, however, produce the best credentials, a particularly good proof of its reliability being afforded at Domaine in the Dauphiné Alps. The power for a paper mill is there drawn from a glacier in the mountain 4 miles away, where the powerhouse is inaccessible for 3 months of the year. In spite of sleet and snow and storms and intense cold, the conducting wires do their duty continuously and well, with great profit to the owner of the mill to which they supply power. As the Niagara plant was to be on an unprecedented scale, the dynamos were of unequaled capacity, able to produce currents in large quantities. These generators differed from the usual type in one very important particular. That is, that the position of the stationary and moving parts was reversed at Niagara. It is customary for the armature, a series of coils of insulated wire, to be rotated rapidly inside a circular ring called the field ring, to the inner face of which are attached a number of powerful magnets. In the Niagara installation, the armature is fixed, and the field ring made to revolve. We may assume that the armature in question resembles a huge cake with a large hole cut through the center. The turbine shaft is extended to pass through the cake and project some distance above it, ending in a taper which fits tightly into a hole in the center of a horizontal plate or driver, of rather larger diameter than the armature. The field ring is bolted tightly onto the end of the driver, and the shaft, driver, and ring have together a decided resemblance to a Chinese umbrella, the turbine shaft representing the handle, the driver the top, and the ring the hanging sides. It is a noble umbrella indeed, the carrying of which would need the sinews of a small celestial army. Its weight is 79,000 pounds, or about 35 English tons. This includes the shaft, the driver, and the ring with its pole pieces and bobbins, each of which weighs more than a ton. The whole revolves at a rate of 250 revolutions a minute, giving the flywheel an effect of 1,274,000,000 pounds. One advantage of this arrangement is therefore obvious, that the need of a special flywheel, as originally designed, is done away with. Another is that the magnetic attraction between the field magnets and the armature acts against the centrifugal force, tending to burst the ring, and so increases the factor of safety of the ring. This last is worthy of a few lines to itself. Its diameter is 11 feet 7 1/8 inches, its depth about 4 feet. The ring is forged in one piece without weld from a nickel steel ingot 54 inches in diameter and more than 16 feet long, through the center of which a hole was bored preparatory to expansion on a mandrel under a 14,000-ton hydraulic press. The Bethlehem Iron Company was responsible for the forging, and the Westinghouse Electric and Manufacturing Company for the truing and turning up on their mammoth lathes. The Niagara Falls Power Company have on the American shore 2 powerhouses. Each is designed to accommodate 10 generators, giving a combined output of 50,000 horsepower. The one is finished and in full working, and the other rapidly approaches completion. Beneath the stately row of dynamos, which we see on entering a powerhouse, yawns the wheel pit, 463 feet long, 20 broad, 180 deep, a huge slot cut out of solid rock. If we are permitted to descend, we find men busy attending to the bearings, watching that the oil supply keeps down their temperature to the proper figure. Near the bottom, the turbines hum on their platforms of stout steel girders spanning the gulf, and fling vast quantities of water into the nether darkness, whence it finds a path through a side tunnel into the great main tunnel that occupied 1,000 men continuously for more than 3 years, in the removal of over 300,000 tons of rock and the placing of 16 million bricks for lining. Near the portal, the grade falls very suddenly, so as to permit the discharge of 1/2 of the flow from the tunnel below the surface of the rapids. In the powerhouse, flanking the generators, stand 2 platforms of white enameled brick, each nearly 20 yards long and some 13 feet wide, surmounted by 8 upright stands on the face of which are many indicating instruments. These structures are technically known as the switchboards, to each of which is conveyed the total 25,000 horsepower from a group of 5 generators. The switchboards are the main nerve centers of the plant, from which its various functions are directed and controlled. Upon them are located instruments and appliances, by means of which the attendant is always informed as to the output and voltage of the various generators, and which indicate instantly the nature and, within certain limits, the location of any disturbance in any part of the system. In front of the attendant are 100 levers, controlling pneumatically the great dynamo and feeder switches and auxiliary switches. Here, by the crook of a finger, the attendant can at will cut off instantly the entire supply, or any portion of it. Footnote: Mr. Philip B. Barton, in Cassier's Magazine. End footnote. In comparison with the power handled, the number of men required to control it is small, but the well-being of so many thousands depends on the small band in the powerhouse, that it becomes an absolute necessity for each man to be specifically trained, alert, resourceful, to meet any emergency that may arise. The working of the generators goes on night and day, and the employees are therefore divided into 3 shifts of 8 hours each. At the head of each shift is the electrician in charge, whose particular duty is to operate the 2 main switchboards, and his post, the captain's bridge of the plant, as it has happily been called, is switchboard number 1. An assistant electrician has charge of switchboard number 2. A shift foreman is responsible for the operation of the motive power plant, having under him oilers to tend the bearings, labourers to keep the inlet racks to the penstocks free from eelgrass, ice, and drift, and the man who looks after the elevator in the wheel pit. Other officials are in attendance to repair the machinery at any point, whether hydraulic or electrical, and attend to the telephone through which important orders may come at any moment. The current manufactured by the generators may be used either locally or at a distance. In the former case, the pressure, or voltage, is that of the generators, but for transmission to distant places such as Tonawanda or Buffalo, 20 miles off, it would be unprofitable to use so low a pressure on account of the loss that results from the resistance of the conducting cables. The current is therefore stepped up, or increased in intensity, to 11,000 or 22,000 volts, just as water or gas is pumped at very high pressures through long pipes. On reaching the receiving end of the transmission cable, it is stepped down or reduced by transformers for local uses and converted, if necessary, from alternating to direct current. Niagara Power was first sent to Buffalo in 1896. The cables are slung on stout poles 35 to 65 feet high, placed about 60 feet apart. Porcelain insulators of unusual size are employed to protect the cables from leakage, and, in order to maintain an efficient guard of the line, the Niagara Falls Power Company has purchased a strip of land 30 feet wide, reaching from the falls to Buffalo. The line is patrolled night and day by men who are able to communicate by telephone with headquarters. At the Buffalo Exposition of 1901 was witnessed the most magnificent display of electric illumination that ever gladdened the eyes of man. The central point of the display was the electric tower surmounted by a superb figure of the Goddess of Liberty. Several hundred thousands of 8-candle power lamps had been arranged along the angles and edges of the building and its chief architectural details. At a given signal, the operator in the electricity building started a small motor, controlling a worm gear that slowly poured into the lamps the whole of the power taken from a generator at Roaring Niagara, 20 miles away. The gradual change in myriads of lamps from faint luminescence to full incandescence came as a revelation of beauty to the thousands of spectators in the grounds below, and soon after a huge searchlight swept the horizon, even to the mighty cataract from which it derived its force. The purposes to which Niagara Power is already turned are legion. The population of the northwest corner of New York State has become dependent for many conveniences and comforts on the energy issuing in vast quantities from the grey limestone powerhouses flanking the sides of the inlet canal. 4 cities, of a combined population of 500,000, are lit throughout by Niagara Force, which also operates their 350 miles of streetcar track. In Buffalo, the Tonawandas, Lockport, and Niagara Falls, 50 large manufactories, representing a capital of $100 million, depend entirely for their success upon a constant supply of current from the company's generators. And so efficient is the organization of the company's plant that during a period of nearly 3 years, total interruption of power has occurred but once, and then only for 18 minutes, on account of an ice jam in the river. As the plant is increased, the possibility of interruption will become even slighter, since the switchboards are so arranged that the current from any one group of generators can be switched in a moment into any supply line. The rapidity with which improvements in electrical apparatus succeed one another may be gauged from the fact that, in the second powerhouse on the American side, the 5 turbines last put in will be of a fixed field ring type, an improved reversion to old practice, while on the Canadian side, where tunnel, wheel pit, and intake canal for a capacity of 100,000 horsepower are being completed, the company is establishing dynamos producing the enormous figure of 10,000 horsepower each. This increase in the size of the unit is, of course, the result of proved economy in larger generators, as regards cost per horsepower in the construction of the generator, and the turbine to drive it, and the space required in the wheel pit and powerhouse. It is possible that in the future we shall see far larger generators even than these in common use, for the big thing of today becomes the normal practice of tomorrow. We should at least mention, though full details of management, construction, etc. are not at the author's disposal, an independent company, known as the Niagara Falls Hydraulic Power and Manufacturing Company, which already develops and sells 35,000 horsepower to various industries. This company's powerhouse is situated below the falls. It draws its supplies from a canal that connects the upper river with the edge of the bluffs, whence 3 penstocks, 11 feet in diameter, conduct the water 210 feet vertically to 14 turbine wheels of from 2,000 to 2,500 horsepower each, connected directly to generators coupled at each end. From these generators, the current is led to the top of the bank by means of wires and aluminum bars built along the side of the penstocks, and thence in underground subways to various consumers. With power so abundant, it may well be cheap. In how many regions of the world could you, for the sum of $8, £1 12 shillings, obtain from year's end to year's end without a break energy representing 1 horsepower? Having these figures before us, we can understand why the Pittsburgh Reduction Company, which controls the aluminum industry of America, left Pittsburgh, where good coal cost but 68 cents, 2 shillings and 10 pence a ton, and migrated to Niagara, and how it comes about that many manufacturers can here save enough on power in 1 year to pay for building and cost of removal. The company just named produces pure aluminum, a metal distinguished by its lightness, beauty, and freedom from corrosion, from an oxide of alumina, by smelting the latter in carbon-lined retorts, which act as one terminal of a heavy electric circuit, massive carbon rods suspended above the crucibles forming the other pole. The carborundum company also employs intense heat. Electric furnaces of today are used at a temperature of 7,000 degrees to smelt carborundum from its ore into crystals, which are ground into powder and pressed into various forms for grinding purposes as emery, large wheels for shaping tools, or tiny discs for smoothing teeth. Among electrolytic and electrochemical processes, none are of greater interest than the carborundum processes, whereby an artificial abrasive is made in much the same way as that which brought the diamond into existence. Great factories are springing up for the manufacture of carbide and calcium, and other chemicals. Thomas Edison, the great electrician, has prophesied that Niagara will be the great electrochemical center of the world. It may already claim that distinction, so powerful an ally is an unlimited supply of cheap power to the chemist. Paper, silver plate, graphite, lamp, cloth, and steel factories are rapidly rising within sound of the falls. Electricity heats the ovens in the huge establishments of the Natural Food Company. At Tonawanda, electricity saws and planes vast stacks of timber. At Lockport, it whirls heavy trains. At Buffalo, it runs the streetcars, prints one of the leading newspapers, handles thousands of tons of cereal, helps in the creation of steel bridges, operates refrigerators, supplies the motive power for great dockyards, tan yards, breweries, and pumps. At Niagara, as a result of this newborn power, a great city is springing up with mushroom speed, a city free from smoke, gas, ashes, an ideally clean city. 5 trunk railways lead westward from it, 5 to New York, 5 to Boston. On the completion of its docks, Niagara will be the eastern terminus of the Great Lakes Basin, at the greatest transshipment point of raw material in America. All things augur for Niagara a future comparable to the present of Chicago. It is a matter for thankfulness that the great power installations have been so arranged as to leave the picturesque beauties of the falls unharmed. Tourists will still find the huge cataract a thing to gaze upon with rapt admiration, despite the turbines pulsing with mighty energy not far away. The public-spirited action of the company is further seen in the industrial village of Ekota, which they have built for the employees in the factories. A few years ago, the 84 acres on which it stands was waterlogged meadowland, subject to inundation by the streams that run on 2 sides of it a few feet below its level. The company therefore built a high dike all round it, and, as it was impossible to raise the area to a height at which it would drain readily into the river, they instituted a system of deep drainage, which, traversing the city in all directions, discharges into large pits, whence the water is pumped into the streams. So carefully has this been done, that rains no longer make the earth heavy and muddy, nor does the sun scorch it into cracked clay and dust. Lawns and trees flourish, and wet cellars are unknown. broad roads intersect the property on a systematic plan, passing between rows of trim houses well provided with modern comforts, running water, electric light, and a wholesome sanitary system. The streets are lit with large clusters of lamps by night. Boughs of trees give grateful shadow by day. A frequent service of electric cars runs at all hours. And last but not least, rentals are as low as $9 a month, light and water included. The village of Ekota has been evolved, writes Mr. John Bogart, footnote, in Cassier's magazine, end footnote, in accordance with the careful study of the men to whom was committed the responsibility of the solution of a complex problem. A district not fit for comfortable residence has been transformed into an ideal, healthful village. Ground upon which no vegetation would thrive has been changed to a region of velvet lawns and blooming gardens. Roads which were a discomfort from dust or annoyance from mud have been made into well-paved, beautiful streets. An attractive expanse of poor meadowland has become a model town. We may here say farewell to the great Niagara Falls, and in conclusion turn our thoughts for a moment to the Zambezi, where the Victoria Falls, twice as broad as those of Niagara, have a sheer drop of nearly 400 feet. Today, in California, power is successfully transmitted for nearly 150 miles, and with this precedent it is to be hoped and expected that in the future water power available in unequaled volumes at the Smoke That Thunders will be utilized to aid the development of the great mineral resources of Rhodesia and South Central Africa, converting what is now semi-explored territory into centers of industry. Note: on the Canadian shore, there are at present in progress two separate undertakings independent of the Niagara Falls Power Company. That is, the Ontario Power Company, which is now constructing a proposed initial development of 30,000 to 50,000 horsepower, and the Toronto Niagara Power Company, which has recently commenced the construction of a 50,000 horsepower plant. End of Chapter 1.
Chapter 2 of the Romance of Modern Engineering. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Romance of Modern Engineering by Archibald Williams. Chapter 2 The Taming of the Nile. To no country in the world does the veil of romance cling more closely than to Egypt, that strange, mysterious land of utter barrenness jostling prodigal fertility, in which huge monuments tell of great bygone races, and proclaim that here was the cradle of civilization and the birthplace of history. To visit and explore Egypt is to visit and explore the Nile, the huge river that has its beginnings at the equatorial Nyanzas, and flows northward 3,000 miles before its majestic stream discharges itself into the waters of the Mediterranean. Countless years prior to the advent of man, the river hollowed out its bed in the plains and through the rocks of eastern Africa, struggling with the thirsty Kamsim-swept desert for a narrow strip of verdure on which mankind might dwell. In course of time, the land of the Nile teemed with a great population that conquered surrounding peoples and left records of their victories, their religion, and their kings in the temples and tombs that line each bank of the river. Its waters were the scene of many a great pageant. In the temples hard by, the Egyptians did reverence to the bounteous Nile, the giver of all good things to them, under the name of Osiris, the god of life, in eternal combat with his murderer Typhoon, the demon of the desert and personification of evil itself. From the uncertainties of history that begins with the very beginnings of history, the Nile flows out, the lifeblood of countless generations that have been and of many more to come. It does today what it did in the days of Ramses and Cheops, of Cambyses, Alexander, Julius Caesar, and Napoleon. The great conquerors who have floated on its bosom are turned to dust, but still every year is seen the wonder of the flood rising in summer heat under a cloudless sky, overflowing its banks till the adjacent villages are but as islands in a watery waste, covering the land with its fertilizing silt, and then, gradually, sinking into its bed again. The year is divided for the Egyptian into 3 seasons: summer, when the Nile dwindles to its lowest level; flood time, during which the melting snows of Abyssinia and the incessant tropical rains of the Nyanza basin, thousands of miles away, rolled in increasing volume down the valley, laden with the rich red silk of the Atbara; and winter, when green crops come up as if by magic on the sinking of the flood, and the corn crops are sown for the harvest in March. The anxiety with which the rising of the Nile is watched may be appreciated by those who have experienced a season of drought in climes usually blessed with an abundant rainfall. They, however, keep their eyes fixed on the heavens for the clouds that are long delayed, or roll over without shedding the dew of heaven. The Egyptian looks at his feet, watching the rise of the waters. The Nilometer is the arbiter of his fortunes. The ordinary rise at Cairo is about 24 feet. Less is insufficient, more brings danger. A rise of 18 or 20 feet spells famine. A flood of 30 feet means ruin. The silt, deposited at the rate of some 5 inches a century, is of an extraordinary productiveness. Wherever the soil is fairly cultivated and properly watered, it amply repays the toil of the husbandman, yielding luxurious crops of tobacco, cotton, sugar-cane, and indigo. Among the shallows of Lake Missoula lingers the once prized papyrus. In the beautiful valley of Fayoum, myriads of roses burden the air with fragrance, and every peasant's tiny nook of ground affords a supply of leeks, garlic, melons, and cucumbers. Acres of sunny cornfields are contiguous to the eternal barrenness of the desert. It has been truly said that if the soil of Egypt be but tickled with a hoe, it will laugh with a harvest, a quality that has made it, like India, the scene of much contention for its possession. During a great part of the year, the Egyptian is like a man ushered into a treasure house from which he may carry out only what his hands can hold. The Nile flows past his home in vast volume, amply sufficient for the needs of the whole country were it but available in a constant supply, and in all spots of the long narrow valley that is the true Egypt. For centuries, at low Nile, the farmer has been obliged to ladle water painfully to upper levels by means of a primitive shaduf, or pole bucket, and discharge it into the myriad canals and ditches that intersect his property. The English farmer is happy in being able to exclude from the list of his burdens that of lifting water onto his land at the cost of some 50 shillings an acre. "It will be seen," says Sir Benjamin Baker, "what a vast amount of human labour is saved throughout the world by the providential circumstances that in ordinary cases water tumbles down from the clouds, and has not, as in Egypt, to be dragged up from channels and wells. Now, though the Egyptian is probably doomed to expend a great portion of the sweat of his brow on this task of watering, Western science has come to the aid of the unchanging East. The same necessity that drove the ancient pharaohs to the construction of canals and reservoirs has, during the last half-century, exercised the thoughts of those responsible for the welfare of Egypt. The scheme has been gradually evolved of putting a bridle upon the Nile to check its course somewhat during flood time, and rescue some of its surplus water from the Mediterranean against the season of greatest need. To a Frenchman, Michele Fry, belongs the honour of having first spanned the stream, below Cairo, with a barrage. This work consists of 2 brick arched viaducts crossing the Rosetta and Damietta branches of the Nile, containing 132 arches of 16 foot 4 inches span, which are closed during the summer by iron sluices, so as to retain, on the upper side, a head of 15 extra feet of water to be thrown into the made irrigation canals below Cairo. The building of the barrage occupied 15 years, and another 20 passed before it could be considered in satisfactory working order. The chief difficulty of construction arose from the unstable nature of the matter below the foundations, through which the water forced its way, despite the timber pilings driven deep down into the riverbed. At a later date, Major Brown, Inspector General of Irrigation in Lower Egypt, found it expedient to relieve the pressure on the old barrage by constructing auxiliary weirs below it, and so raise the water level on the lower side. He effected this by dropping cement rubble from rafts into a movable timber caisson, thus forming solid and continuous masonry blocks from bank to bank. The effect of Michele Bey's great work, hampered by the whims of Egyptian officials and costly in spite of forced labor, has been immensely beneficial to Lower Egypt. This is sufficiently proved by the fact that in 1900 it saved the cotton crop in the Delta from utter disaster, and, according to Lord Cromer's calculations, has doubled the cotton crop of Egypt, an annual gain of £5,000,000. To give the reader an idea of the water-retaining capacity of the barrage, it may be mentioned that it feeds 6 canals, the largest of which, the Central Canal, at the apex of the Delta, carried, even in the drought of June 1900, a volume 1/4 greater than that of the Thames in mean flood, and the Ismailia Canal, running to the Suez Canal, was still a river twice as large as the Thames at the same season. The steamer, or picturesque dahabeah, after passing through the huge barrage locks on its way upstream, encounters no obstruction for 250 miles, when it reaches Asyut, the thriving capital of Upper Egypt, lying in a fertile plain at the foot of the Libyan mountains. Here is the second step in the staircase of the Nile water scheme. The recently erected barrage, rather more than half a mile long, and pierced with 111 arched openings, 16 foot 4 inches wide, all of which can be closed by steel sluice gates. The barrage measures about 50 feet from front to rear at the base, and 47 at the top, along which runs a roadway from shore to shore. The whole rests upon a platform of concrete and masonry, 87 feet wide and 10 feet deep, which is protected from the undermining influence of the water by tongued and grooved iron sheets driven down 23 feet into the riverbed, made tight at their joints with cement. As a further precaution, a strip of the bed both up and downstream is covered for a width of 67 feet with stone pitching, resting on clay puddle and layers of fine gravel and pebbles respectively, so that, supposing a small quantity of water to have penetrated the clay on its upper side, and worked its way right under the 2 fences of iron sheets, its upward course is severely checked, if not annihilated, by the sand reinforced by pebbles in turn held down by stone blocks. Work was commenced at Asyut on December 1st, 1898, in the formation of sads, or dams, surrounding the site of the foundations on the western side. By February in the following year, everything was ready for pumping the water out of the sads. An area of 13 acres being laid dry, men were crowded on to drive piles, lay the cement and rubble foundations, and build the masonry on them. The next year, further sads were made on both sides of the river, fresh foundations laid, and the first section continued. In 1900, which witnessed nearly 1/2 of the entire work, the sads met in midstream, and navigation was diverted to a gap purposely left near the east bank. The following figures will give an idea of the scale of operations during this year. In May and June, the average number of men at work was 13,000. Nearly 1.5 million sandbags were placed in position, more than 100,000 superficial feet of iron piling driven, over 90,000 cubic yards of masonry and foundations laid, nearly 500,000 cubic yards excavated and filled. To keep the water down in the sods, 17 pumps, each throwing a solid column of 12 inches, were constantly employed, in addition to many auxiliary pumps. The barrage was completed in the spring of 1902. It will, it is estimated, bring under cultivation an additional 300,000 acres, supplying their needs by means of the great Ibrahimiya Canal, which receives water just above the barrage, and will render more effective the work of the Cairo barrage. 350 miles above Asyut, the Nile is once more spanned at Aswan by the huge dam which will, for centuries, be monumental evidence of the enterprise of English rulers and of the skill of English engineers. Aswan, or Aswan, signifies the opening. Its ancient name was Syene, and as such it had fame as the depot of merchandise passing from north to south, as a strategic position at the gates of Nubia, and as having in its neighborhood famous quarries, whence came many of the colossal structures of old Egypt. The first of the 7 so-called cataracts, they are really no more than rapids, of the Nile, until recently shot between the rocky islands which here unite with the towering cliffs that press in towards the river on either side. The cataract fell in 3 stairs, of which the uppermost was the most formidable, and boats going upstream had to be towed through rushing water by gangs of half-naked Arabs. A writer has thus described the scene. The Nile, bending abruptly, broadens into a kind of bay, which is shut in by the green and lovely island of Elephantine, whence an early dynasty of Egyptian kings derived their name. The high, bold rocks which rise on every hand seem like the boundaries of a lake. On the left, nestling under crags, whose summit is crowned with ruins, lies the modern village. In the distance, the yellow sandy hills are covered with the remains of Saracenic architecture. To the right, the shattered walls of a convent mark the crest of a sandstone eminence, and all around, between the desert and the river, the palm groves cluster in verdurous masses. The view from the environing rocks is very striking, a view of hill and water, wood and lowland, and beyond, the confused and blown heaps of the rolling sands of the desert. The river hurries past in a succession of rapid eddies and foaming whirls. In their midst lie various black-colored islets, marking the boundary of the cataract. Above the cataract is the island of Philae, the Mecca of the ancient Egyptians, who there worshipped at the shrines of Osiris, Isis, and Horus, the sacred triad of their mythology. In the bed of the cataract, so the story ran, lay the body of the murdered Osiris, to rise every year in the form of the life-giving flood. So what spot more fit than Philae in which to raise magnificent temples to him, his sister-wife, and son? Huge ruins still crown the island, colossal propylons, shadowy arcades covered with hieroglyphics, gigantic columns, obelisks, and statues, forming so wonderful a testimony to Egyptian art that modern travellers visit it with an eagerness akin to that of the old-time worshippers. For the last 5 years, the iron-bound precipices that form a stern setting to the lovely island have looked down upon a mighty struggle between man and nature. For in the heart of the cataract, where the waters rush at a speed of 15 miles an hour, has been raised a huge dam from hills to hills, offering a broad breast of enormous strength to the hurrying Nile. Surely imagination kindles at the thought of men, so small and weakly, bridling a prince among the rivers of the world, despite the silent, unceasing hostility of the watery element. To begin the story of the Nile Dam aright, we must go back to the day when Sir Samuel Baker first suggested that here, at the gate through which the fertilizing flood rushes with maximum force, should a gate of masonry be placed. He conceived the idea of a series of dams to form reservoirs from Khartoum downward. This great work might be commenced by a single dam above the first cataract at Aswan, at a spot where the river is walled in by granite hills. By raising the level of the Nile 60 feet, obstructions might be buried in the depths of the river, and sluice gates and canals would conduct the shipping up and downstream. After 40 years, Sir Samuel's proposal has been carried out almost to the letter. Mr. Wilcox, formerly Director General of Reservoirs in Egypt, worked at the idea of constructing such a dam for years, and after surveying all likely points in the valley, came to the same conclusion as the great explorer, that Aswan was the most suitable spot. An international committee, consisting of Sir Benjamin Baker, already famous for his work on the Fourth Bridge, Signor Giacomo Torricelli, and Monsieur Auguste Boule, to whom the matter was referred, also arrived at the same opinion. Mr. Wilcox accordingly drew up plans for a dam, or rather series of curved dams, capable of holding back 3,700 million cubic meters of water. The project, unfortunately, involved the submersion and destruction of the ruins on Philae, and on that ground was so vigorously opposed that fresh designs were made, and a single straight dam substituted of such a height as to retain 1,065 million cubic meters, or less than 1/3 of the original estimate. The dam is of a most impressive size. From end to end it measures 1.25 miles. Its maximum height from lowest foundation to parapet is over 120 feet. On the upstream side it is perpendicular. On the downstream side it thickens downward from the summit, where it has a width of rather more than 16 feet, with a regular batter of 1 and 1½ which, in its deepest parts, gives it a foundation breadth of 100 feet. The total weight of masonry is over 1,000,000 tons. No less than 180 openings pierce it from face to face. Of these, 140 are 23 feet high by 6 feet 6 inches broad, and the remaining 40 are 12 feet high and of equal width. These openings are closed at their upstream ends by steel sluice gates, working mostly on the stony roller principle, which enables them to be opened by hand even when subjected to a pressure of 450 tons. When open, they will pass the entire volume of the Nile in full flood at the rate of 15,000 tons per second. The water levels on the dam faces differ at the beginning of a summer by 67 feet, and this head of water forms a lake 150 miles long that would reach from London to Nottingham and still leave enough over for Thirlmere. Sir Benjamin Baker, the consulting engineer of the Dam Construction Committee, said in a paper read at the Royal Institution that the quantity of water stored in this artificial reservoir may be made to appear enormous or trifling according to the standard to which it is compared. Thus, on the one hand, when we consider that the rainfall within a 4-mile cab radius from Charing Cross amounts to 100 million tons annually, we become aware of the insignificance of the reservoir as a substitute for a rainfall such as ours over the whole land of Egypt. But, on the other hand, when calculation shows that the reservoir holds enough water for a full domestic supply to every one of the 42 million inhabitants of the British Isles, then the vastness of the quantity becomes appreciable. And it increases our respect for the Nile to learn that in flood time a volume of water equal to the total contents of the reservoir passes through the sluices every 24 hours. As soon as the initial difficulties regarding finance had been overcome by the timely aid of Sir Edward Castle, tenders were invited for the construction of the dam. Sir John Aird and Company were the successful competitors, and in February they signed a contract including Messrs. Resolmes and Rapier as subcontractors for the steelwork to complete the dam by July 1903. The foundation stone was laid by His Royal Highness the Duke of Connaught on February 12, 1899, and the dam formally opened by His Royal Highness on December 10, 1902, or 8 months in advance of contract time. The merit of this feat is enhanced by the unexpected difficulties that the constructors were called upon to cope with from time to time. Even the expected difficulties were formidable enough. "It would not be too much to say," writes Sir Benjamin Baker, "that any practical man standing on the verge of one of the cataract channels, hearing and seeing the apparently irresistible torrents of foaming water thundering down, would regard the putting in of foundations to a depth of 40 feet below the bed of the cataract in the short season available each year as an appalling undertaking." But everything had been carefully thought out, and in a short time after the signing of the contract, a large tract of the desert adjoining the river was taken possession of, and on it rose railways, houses, offices, machine shops, stores, and hospitals. Soon thousands of natives and European workmen transformed the solitude into a busy town. The islands across which the dam runs were submerged at flood time, but in summer only a few channels passed the water. These, naming them in order from east to west, are the Bab el-Kabir, the Bab el-Haroum, the Bab el-Seguinier, the Central Channel, and the West Channel, the last two the widest. Through them the water rushed at a pace exceeding the fastest progress of a university crew. The question arose how to block these channels in such a manner that the site of the foundations could be pumped dry. Recourse must be had, as at Assiout, to sods, but under very different conditions. It was therefore determined to build stone sods at the lower end of the channels from island to island, before high Nile, and when comparatively still water had thus been secured above them, to form sandbag sods at the entrances, so that when the flood had subsided, pumping operations might be at once begun. The Kabir, Haram, and Segbiar channels were attacked first. Huge stones, weighing up to 4 tons, were lowered into the current by cranes, but such was the momentum of the water that even they were carried away. It was therefore found necessary to enclose several blocks at a time in large nets of steel wire, And on occasions when this method proved ineffective, the engineers adopted even more heroic measures, and shot into the stream railway trucks laden with granite blocks lashed tightly together by wire ropes. These masses, weighing upwards of 50 tons, acted as a tow or lodgment for smaller bodies, and at last patience was rewarded by the appearance of the temporary dams above the surface. Cement and sand were then tipped in on the upstream side to work in among the stones and fill in all interstices. The completed stone sides were 22 feet wide at top, thickening rapidly downward to a maximum depth of 50 feet. Full Nile put them severely to the test, for after its subsidence steel rails were found strangely twisted, and the surface of the stones was like that of polished marble. As soon as the summits were exposed by the sinking flood, huge numbers of sandbags were thrown into the entrances of the channels, forming dams 16 feet wide at top and 55 deep. Since the flood of 1899 was unusually low, the temporary dams were carried across the ends of the central channel as well, and completed in February 1900. Pumping then commenced. Many large 12-inch centrifugal pumps got to work, and, as Sir Benjamin Baker admits, the engineers watched the result with great anxiety, as no one could predict whether it would be possible thus to dry the riverbed. Fortunately for the progress of the dam, the sod stood the test extremely well. In one day, the Bab el-Kabir was emptied of all but a small leakage easily nullified by a single pump, the Bab el-Haram, the Bab el-Saghir, and the central channel being equally amenable. By March 1900, the contractors were hard at work on the excavation of the drain surfaces, cutting down until hard, firm rock was reached. Great trouble resulted from the fact that in 3 channels, an unexpected depth of schistous formation had to be removed. The Bab el-Kabir especially furnished a great quantity of extra work, inasmuch as the rock had to be excavated to a point 38 feet below the level of the contract drawings, and the batter of the walls being maintained of necessity, the foundation breadth at this place was 100 feet instead of about 70. This delay, as serious as it was unexpected, aroused the contractors to tremendous efforts to make up for lost time and raise the masonry to a sufficient height before the following flood time. In June, work was carried on day and night, brilliant arc lights replacing the sun at sunset. A contributor to the Daily Mail has graphically described the scene. Orders are given for all workers to assemble at 6:30 for 7 a.m. duty. At 7, the engineer takes his coffee and roll, lights a cigarette, and is swiftly driven to his work by fleet runners from his own door, and landed practically in the center of activity. Arrived on the barrage, or dam, a knot of Sikhs and Rays greet him with the courtly Eastern salaam, and shortly after may be seen speeding towards the various quarters of the work. Maybe 1,000 men are at work, each section under its particular chief, the fellahin from near Cairo, famous stone dressers and masons for centuries back, so far back that the vista of age grows dim. These are attended by boys in picturesque galabeys, carrying water, and very often by women gracefully bearing boxes of humra or mortar on their heads. Bedouin and fellahin work like ants at the rough work, and dark-skinned, smiling, good-natured Sudanese ram the concrete as it is placed in position, as if they took the whole thing as a huge joke. As the work proceeds, one presently hears the Arabs and Sudanese, once and not long ago masters and slaves, as the remains of the Cairo slave market, now in ruin, testify, chanting some of their melancholy and weird dirges, throwing great heaps of undressed stone from one place to another, which, as one looks, become spread out into the evenness of a revetment wall, or, neatly dressed, becomes the facing of the dam. Here and there, under broad sun helmets, like tall mushrooms, may be found a wily Greek or excitable Italian, acting as a useful lieutenant to, and directing the work being executed by, the solitary Englishman perched yonder on an excavation of masonry, apparently an idle spectator, and yet seeing all, and occasionally acting as judge in the many disputes arising between the different factions. Ceaselessly the work goes forward, drowned by the equally ceaseless chant, till 12 noon, when up goes the Egyptian flag to the top of the flagpole, and work ceases until 1 p.m. Away fly the Europeans on trolleys, the Rice and sheiks on donkeys, to their homes for dinner, and the long wished-for drink, poor Stephen so well described. The trolleys, propelled by gaily clad runners, shouting, "Oh, right, ligla!" mind your feet, at the top of their lungs, till one wonders where the breath is coming from for the next call. A company of red and white turbans move off to one spot, another of close-fitting brown skull-caps, representing the Fellahin, tear off, scampering like children, to another locality, and the rear of this motley crowd is generally brought up by the more dignified company of inky black Sudanese, who at once seek the encampment where their wives are, without whom they never travel any distance. Amid ceaseless chattering and gesticulating, a hearty meal is made. Off what, ye British workmen? Simply a few cucumbers or turnip tops, 2 or 3 lettuces perhaps, and this, with a bowl of lentils and the puffed-out flat cakes of the East, washed down with muddy Nile water, constitutes for them an excellent meal. Possibly, if in season, a piece of sugar-cane fulfills the same object. This lordly repast being over, the chattering ceases. The burnouses are brought out from a pile, spread over their bodies, face and all, and they sleep till 2 o'clock. By 2:05 p.m., all hands have fallen to again, to work without break until 5:30 p.m., with the blazing sun overhead blistering all that it touches. Still the ceaseless chip-chip of the mason, the thud of the rammers, the clank of the drivers' air-pumps, the monotonous sing-song, and the shriek of diminutive railway engines, till the magic hour of 5:30, when up goes such a shout from the throats of 1,000 men as might raise their departed ancestors for generations back, and the shrill loo-loo of the women, and the Egyptian crescent once more floats in the cool evening breeze. Hundreds of devout worshippers drop about in all directions, having spread their prayer mats, turn their faces to Mecca, and give their fervent thanks to Allah, swinging backward and forward like the stalks of a cornfield. Then takes place one of the most interesting functions of the day. On a strip of sand left dry by Father Nile, 3 or 4 circles of crouching figures are formed, with a race in the centre of each, and every 5th man sitting forward receives the pay of the 5 from a large bag of coin, and distributes it directly after. Meanwhile the scribe, generally a Copt, standing at the elbow of the paymaster, ticks off the payees' names. As each circle is paid off, it dissolves into a crowd of happy children making for the bazaar, there to indulge in the nightly fantasia and the everlasting tap on the tom-toms. At the hoisting of the flag at 5:30 p.m., a solitary figure is rowed away down the old river, the headpiece and mover of this vast machinery of humanity, and if one could look through the lattice window of his room 2 hours after, one would see a picturesque group of gaily dressed Arab sheiks and reis standing round that one man of a foreign race, making reports and receiving them till midnight strikes, when this representative of the dominant power encloses himself within his mosquito curtains with a kulu kalas a la nobra kula ela, and the height of the dam has risen 2 feet within the last 24 hours. By the end of 1900, the most momentous year in the history of the dam, the back of the work had been broken. The amount of excavation then amounted to 577,515 cubic meters, and the masonry to 239,468, or about 2/3 of the whole. In the following year, the west channel was closed, and foundations were laid up to the western shore, where they met the northern end of the great navigation lock, which is in itself a large piece of engineering. The lock contains 4 steps, controlled by 5 huge gates 32 feet wide and 60 feet high. Instead of being placed in pairs, meeting at an angle in the middle, as in river locks of the usual type, these gates are hung from the top on rollers, and slide sideways like a coach-house door into recesses on the flank of the lock. This arrangement was adopted for safety's sake, the 2 uppermost gates being made sufficiently strong to withstand the whole head of 67 feet of water if suddenly called upon to do so. At highest flood, the ruins on the island of Philae are partially submerged, and a general saturation of the silt and mud of which the island is composed takes place. Measures were therefore taken, under the superintendence of Dr. Ball and Mr. Matt Talbot, to protect the monuments from the risk of settlement by underpinning the most important parts down to solid rock, or at least to a point below the saturation level, so that we may hope that for many years to come, modern engineering, as represented by the colossal dam, may not be blamed as the destroyer of ancient art. When the river is rising, the sluices will all be opened to permit the free passage of the silt-laden water. After the flood, When the discharge of the Nile is diminished to 2,000 tons a second, the sluices will gradually be closed, and the Nile slowly mount the upper side of the dam. In May, June, and July, the water will be doled out to the farmers. Huge though the storage is, it is not abundant, and in order that those enjoying it may be fairly treated, the government of Egypt has bound down the population to a long list of most elaborate regulations, which forbid even the drawing of water in buckets except at the appointed time. Already schemes are under discussion for additional dams further up the Nile to extend the benefits conferred by the works here described. The revenue and prosperity of Egypt are so closely bound up with the question of water, that with men of the stamp of Lord Cromer and Sir William Garstin at the head of affairs, we may look at no distant date for new developments possibly approaching in importance the construction of the Great Nile Dam itself. End of Chapter 2. Recording by Todd.
Chapter 3 of The Romance of Modern Engineering. This is a LibriVox recording. All LibriVox recordings are in the public domain. For information or to volunteer, visit LibriVox.org. The Romance of Modern Engineering by Archibald Williams. Chapter 3, Dams and Aqueducts. Probably few of us whose houses are connected with a public water supply give much thought as we watch the crystal clear liquid issuing from a tap to the journey that it has taken from the point where man first gathered it for his own. Yet, perhaps, it has come many a mile through pipes and tunnels, been flung into reservoirs, strained, filtered, passed again into pipes, first for the town, then for the street, lastly for the house, until fresh from its mountain stream or subterranean cave, it emerges into the unromantic surroundings of the bathroom or back kitchen. Our direct experience of the mechanical side of a water supply is usually confined to the operation so often seen in the minor veins that multiply towards its urban extremity. We know only too well the doings of the plumber and of the laborer who converts the smooth surface of our roads into a dangerous succession of hills and valleys. The consequent bills and rates are apt to blind us to the real romance and magnitude of the work needful to give us our daily water. We must trace the system backwards from our doors, through mains of increasing size, to the very heart and arteries, before we realize how nobly the brain of engineer and muscle of artisan have been employed in the cause of health and sanitation, on undertakings about which but a few of those who are directly benefited possess more than a shadowy knowledge or proper appreciation. Those wonderful old builders, the Romans, have shown us, by the stately march of their aqueducts across plain and valley, that the question of a good water supply for large towns pressed even in their days. Since then, the problem has become increasingly difficult in thickly populated countries, on account of the artificial contamination of streams and strata by the processes of manufacture. And while, on the other hand, we see the engineer driven further afield for his source of supply, on the other, we notice that the demand for an even greater consumption per head is pushed vigorously by common sense and scientific consideration. The daily supply of London has reached the enormous total of 200 million gallons, drawn from the New River, the Thames, and subterranean sources. During the last few years, the metropolis has experienced the inconveniences and dangers of a water famine, which have turned men's eyes to schemes discussed in 1866, of tapping the waters of the Welsh valleys, collecting it in huge reservoirs, and bringing it across country by pipelines 180 miles long, at a cost of £12 million, or of pressing into the service of the Westmoreland lakes with their available storage of some 36,000 million gallons, and connecting them with London by 270 miles of pipes at an outlay of £13.5 million. For their boldness, these schemes may compare with that of the Parisians to fetch supplies from the Swiss lakes across 300 miles of France. At present, none of these projects have come to anything, and the first two have let slip an opportunity, since Manchester now draws from Thirlmere, and Liverpool and Birmingham from the Welsh area earmarked for London. In the following pages, it's proposed to describe at short length the construction of the huge pipelines that help to supply our three largest provincial towns. We will first turn our eyes to Thirlmere in Westmoreland, a picturesque little lake of a natural area of 328.25 acres. Previous to 1894, the great cotton city drew its water from Longdale, a valley situated about 18 miles east, through which flows the river Ethro, one of the principal tributaries of the Mersey. The reservoirs, of a storage capacity of some 6,000 million gallons, collect the water of 19,000 acres and deliver about 25 million gallons a day to the inhabitants of Manchester. The rate of consumption increased so rapidly between 1856 and 1875 that the corporation foresaw a shortage unless a further area were laid under contribution. And after an examination of various sources, it adopted a scheme for impounding the Thirlmere and leading its waters 96 miles to the great reservoirs at Prestwich. An Act of Parliament authorizing the scheme was obtained in May 1879, and 6 years later the glens of Westmoreland began to resound to the snort of engines and clink of hammers. A huge retaining wall gradually rose across the north end of the lake, where it found an outlet into the St. John's Beck. The dam is divided into two portions by a small rocky eminence, through which surplus and compensation water is discharged by means of a tunnel 12 feet wide and 9 feet high. This tunnel is closed by a transverse masonry wall pierced with two 36 and one 18-inch pipes, controlled by valves actuated by hydraulic and hand power. The dam is driven down throughout its length to solid rock, reaching a maximum depth of 50 feet below the riverbed, at which point, as it rises 50 feet above the lake, it has a height of 100 feet. The increase of depth in the lake thus artificially produced gives a total storage capacity of 8,130,686,693 gallons. But for present purposes, only 20 feet of extra depth is necessary for the supply of Manchester. As occasion dictates, the level of the overflow will be raised and a larger body of water impounded. The most interesting part of the scheme is the aqueduct, which brings the limpid stream from under the lofty crest of Helvellyn to a point 4 miles outside Manchester. The Romans, to whom iron piping was unknown, led their aqueducts across valleys on tiers of arches, built at the cost of much labor. The modern engineer is able to adopt the simpler method of gravity flow. By means of siphons, he takes the water down one side of a valley and up the further slope to a point where it finds its own level and continues its onward course in a gentle fall towards its destination. These long pipelines are not hermetically sealed from end to end like the service pipes of a town, for in the case of a large total drop between the source and point of final delivery, there would be an excessive pressure in the siphons at the valley bottoms, the pressure increasing in proportion to the difference in height above sea level between the inflow and the lowest portion of the pipe siphon. The engineer, therefore, after determining the hydraulic gradient or rate of fall in the thermal aqueduct 20 inches per mile, maps out the course of the pipeline in such a manner as to ensure a certain amount of fall between the ends of the siphons, and by placing the upper end of each important siphon on the hydraulic gradient, makes it hydrostatically independent of the rest of the pipeline as regards pressure. The greatest pressure in the thermal aqueduct occurs at the bridge over the river Lune, where the lowest pipes of the siphon have to support a hydrostatic stress of 410 feet, equivalent to 180 pounds to every square inch, and therefore are 1 3/4 inches thick. Another important consideration is the tendency of any fluid or gaseous body enclosed in a pipe under pressure to straighten out that pipe. This effect may be noticed in the flexible tube connecting an air pump with a pneumatic tire. At each stroke, the tube gives a kick, unless it be carefully laid in a straight line. The sharper the curves, the greater is the resistance to the flow of air, and the more pronounced is the resultant kick. It therefore becomes very necessary for the engineer to lead his pipes in as gentle curves as possible, both vertically and horizontally, and at unavoidably sharp bends to anchor them securely to a stable foundation. At the bridge over the Lune, the straightening pull is equivalent to a pressure of 54 tons, which is counteracted by steel straps passed over the pipes and attached to stout anchorages. On the steep descents on the sides of valleys, any slipping of the pipes is prevented by projecting rings which engage with the surrounding bed of concrete. The thermal aqueduct is made up of 3 classes of construction: tunnels, 14 miles, cut and cover, 37 miles, pipelines, 45 miles. The tunnels, which were bored out by pneumatic drills, are 7 feet wide and 7 feet 1 inch high, and lined where necessary. The cut and cover lengths have a transverse section of the same dimensions and a lining of concrete 18 inches thick. Manholes and ventilators are placed every 1/4 of a mile. Both tunnels and cut and cover lengths will accommodate the ultimate maximum flow of 50 million gallons, but in the metal lengths the channel is divided into 5 parallel pipelines, each 40 inches in diameter, and capable of passing 10 million gallons daily. With the exception of all pipes within 9 miles of thermal, where the 5-fold line is replaced by a 3-fold of 48-inch pipes. In the first instance, only 1 line was laid, and the others will be added as need arises. The aqueduct, after leaving the lake at the southern end, plunges into Dunmail Tunnel, 5,165 yards long. Then, through a succession of small tunnels, to that of Nabskar, 1,418 yards long. After traversing Skeghill, 1,243 yards, in Moorrow, 3,040 yards, tunnels, it is mostly in pipe and cut over, the latter a trench dug to the gradient level, floored and walled and roofed with concrete, and covered in again. Before reaching Manchester, 30 depressions have to be negotiated by siphons of varying depths. As it is at these points that the greatest danger from bursts occurs, we may notice the precautions adopted, which precautions apply in part to Liverpool and Birmingham aqueducts. The most likely point for a burst is naturally at the lowest portion of a siphon, where the pressure is greatest. As a matter of fact, only a very few bursts have ever occurred. But the possible damage resulting from a large body of water let loose suddenly on a countryside is so great that the engineers have taken elaborate measures to reduce such effects to a minimum. At the north and upper end of each of the thermal line siphons is a well divided into 2 main compartments by a wall. The south compartment is subdivided into 3 or 5 divisions according to the number of pipes supplied, and each of these divisions is connected with the north compartment by a pipe, the open ends of which are flush with the floors. In the north compartment are a number of large bell-shaped vessels, 56 inches in diameter, each of which is suspended, small end downwards, from a lever 18 feet long, having at one end a fulcrum and at the other end a float, supported by the water of one of the southern divisions. In case of a burst in any one of the siphon pipes, the water in its particular southern division at once sinks rapidly, causing the fall of the float, and the motion transmitted by the lever to the bell barrel lowers the latter into the mouth of the corresponding pipe, and so cuts off supplies from the burst siphon. The rise in the northern compartment is neutralized by a number of overflow orifices, which conduct the surplus water into a specially prepared channel until such time as the supply is lessened at the thermal end. The water in the siphon has still to be reckoned with, and as 2 of the siphons are over 9 miles long, the body of included water is very great. In the northern leg of each siphon is therefore stationed a valve, or a succession of valves at intervals, released automatically by an abnormal rate of flow. Briefly described, the valve consists of a metal disc connected in its central line with 2 trunnions protruding through the walls of the pipe. At the outer ends of the trunnion are pulleys, actuated by chains, to the extremities of which heavy weights are attached. One of the chains, after passing round its pulley, is linked to the end of a piston rod connected with a piston working in a cylinder full of glycerin and water. Above the pipe is an air chamber bolted down to a circular orifice, so that there is an airtight joint between the chamber and the pipe. Athwart the chamber and through its walls runs a shaft, from the center of which depends into the waterway a lever, carrying at its lower end a metal plate 21.5 inches in diameter. At one end of the shaft, outside the chamber, is an arm so weighted that the pressure of water on the plate is just counterbalanced, and the latter maintained in a horizontal position. When a burst occurs, the plate is pushed in the direction of the flow, moves over the lever to which it is attached, and communicates the motion to the shaft, which releases a second lever that in turn releases the trunnion chain wheels and permits the weights to rotate the wheels and gradually bring the internal valve disc from a horizontal to a vertical position, completely closing the waterway. The reader has probably noticed the noise of a water hammer resulting from the sudden closing of a tap somewhere on the house supply. The running water, abruptly checked, expends its impetus on the walls of the pipe with a sharp rap that may be heard for a considerable distance. The effect of such a water hammer on the great pipelines would be disastrous, and it is to ensure the very gradual cutting off of the water that the cylinder mentioned above is employed. At the moment when the chain wheels are released, a small cock in the pipe leading from the cylinder is also opened, and the contents slowly escape, permitting the weight attached to the chain to pull round the pulley at a uniform speed. The danger of a water hammer on the southern or lower leg of a siphon is not so great, as the direction of the rush is the opposite of that of the normal flow, so that for an appreciable time after the burst the water is almost in a state of rest, from which it gradually attains a reverse motion. To check its downward flow, check valves are placed, 3 flaps, one above another, opening only in the direction of the normal flow. On a burst occurring, they at once shut against their seats and remain there until the siphon is refilled and the flow resumed. The charging of a siphon is not so easy a matter as might be imagined. The sudden influx of a full column of water might imprison air in the lower parts, compress it, and cause it to burst suddenly up the lower leg, leaving room for a violent rush of water in its track. An ingenious provision for the charging has therefore been made. In each of the large plugs in the siphon wells is a smaller central one, which is opened by means of a lever of U-section, supported at a short distance from one end on a fulcrum which rests on the main lever between plug and float. A heavy iron ball, weighing 90 pounds, runs in the channel of the short lever. When the central valve is open, the southern end of the lever is depressed, and the ball remains there until the siphon is full, when the float rises and, by raising the main and small levers, causes the ball to roll along its channel and close the central valve. The large plug is now watertight and ready for the next emergency. The pipes used in such works are manufactured with the greatest care, being cast vertically, socket downwards, so that the densest metal may be at the spot where there is greatest danger of fracture. Each pipe is then tested internally with coal tar oil to an internal pressure of 45 pounds per square inch, in excess of the possible maximum exerted by the water, weighted, and its date, number, diameter, length, and thickness entered in a book, after which it is heated in a stove and dipped in a special anti-corrosive composition. During the laying of the line, the position of every pipe is registered, together with the name of the man who laid it and the date at which it is laid. The joints are made by running in molten lead between the socket of one pipe and the spigot end of its neighbor, a process that is too familiar in most towns to need description. The first contract for the work was let in 1885. In October 13, 1894, the first Delmare water arrived in Manchester, the inhabitants of which town are now assured of a splendid supply for many years to come. From Cumberland, we turn our attention to the equally hilly district of north-central Wales, where are the headwaters of the Vyrnwy, a tributary of the Severn. The valley through which the river flows was once the course of a glacier that scraped deep channels in the rock and piled boulders and stones across the glen so as to create a natural dam, behind which a lake was formed. After many years, this lake was filled in with alluvial deposit, which rose to a height of 40 to 50 feet above the rocky barrier. Who would have thought, 50 years ago, that this natural dam would prove of the greatest utility to far-off Liverpool, situated on the edge of unlimited water, and yet casting anxious eyes towards regions where there was water fit to drink? In an interesting report on the Liverpool water supply, the corporation engineer, Mr. J. Perry, tells us how in 1865 a scarcity of water during the summer and autumn produced disastrous results. Quote, "The consumption was restricted in every way. Trade was impeded, sanitary requirements were neglected, public baths and wash houses were closed, and the death rate from diseases caused and aggravated by a deficiency of water became abnormally high. The medical officer of health for the borough, the late Dr. Trench, in evidence before a committee of the House of Commons, stated that hundreds of lives would have been saved during that season if there had been an increased supply of water." End quote. As a result, great works were commenced in 1868 at Rivington in the Yarrow Valley, where there are now 8 reservoirs of 598 acres surface and a capacity of over 4,000 million gallons, connected with Liverpool by a pipeline 15 3/8 miles long, terminating at the Prescott reservoirs. These works cost the corporation 1.5 million pounds. But they did not suffice, and in 1878, Mr. G.F. Deacon, M.I.C.E., was instructed to survey the Vyrnwy Valley and prepare parliamentary plans in conjunction with Mr. Thomas Hawksley for the creation of a second supply. The necessary act received the royal assent in 1880. As no lake existed from which to draw, the engineers decided to create one by closing the valley with a dam superimposed on the rocky ledge left by glacial action. The dam, which rises 85 feet above the riverbed, is 1,172 feet long, 161 feet high maximum, 127 feet thick at its base maximum, and contains 260,000 cubic yards of masonry, weighing 510,000 tons. Quote, below the sill of the dam and above the outlet to the aqueduct, Lake Vyrnwy contains 12,131 million gallons. Its area is 1,121 acres. In a single foot of depth, immediately below the overflow, the lake contains about 304 million gallons. 5 feet lower, a foot of depth contains 292 million gallons. The average cross-section of this remarkable sheet of water does not differ widely from a horizontal base 2,000 feet wide, with a depth of water over it of 70 feet and end slopes of 2.25 to 1. End quote. From Mr. G.F. Deacon, Minutes of Proceedings of the Institution of Civil Engineers. This lake covers the site of the village of Llanwrth, with its 40 cottages, church, school, and 3 chapels. By way of compensation, a new village, church, and churchyard were built below the dam, and thither were removed the living and the dead. The living have gained rather than lost by the move. The new and better houses to live in, a well-regulated river, no longer subject to sudden spates flowing past their doors, a fine carriageway across the valley over the dam, and finally the dam itself, a noble and imposing structure on which the eye may rest with admiration, especially at times when the water passing over the top in an unbroken sheet 700 feet wide thunders down onto the masonry below. Except for the stone and sand, all the materials used in the Vyrnwy Dam, such as cement, bricks, timber, iron, machinery, plant, coal, etc., had to be carted over 10 miles of hilly country from the nearest Cambrian railway station of Llanfwrn. The masonry throughout was executed with the most scrupulous care, since the sudden breaking loose of such a body of water at Lake Vyrnwy into the valley of the Severn, with its large towns, would be terrible to contemplate. A great trench was first dug across the valley down to hard, sound rock. Boulders ranging up to hundreds of tons in weight were met with and removed. All long slopes in the sound rock were cut into steps, and the whole surface was scrupulously cleaned with wire brushes and high-pressure water jets, and coated with Portland cement mortar. The interior rubble work of the dam consisted mainly of large stones, 2 to 10 tons in weight, laid by cranes onto carefully leveled beds of cement mortar. As each stone was placed, a number of men beat upon its center with wooden mallets until it had settled down well, and squeezed up some of the mortar between it and the next stones. The interstices were very carefully filled and rammed with different sized tools, blunt-ended swords for the narrowest cracks, and the precaution taken of only half filling the vertical spaces between the last layer of masonry at the end of each day's work. During the nights, Sundays, and holidays, These half-filled cracks were crammed tight with bags to exclude rain, frost, and sunshine. By this means, the perfect junction of the work was assured. The facing stones, cut to rectangular form, were bedded in like manner, but the mortar not brought to the outer edge. Cracks 6 inches deep from the face at the bottom and 3 inches at the top were left and filled in with iron plates until the mortar had set. The cracks were then caulked to within an inch of the face with special cement, very carefully rammed. The result is a face that will suffer a minimum of disturbance from the contractions and expansions of cold and heat. The dam is pierced by 2 culverts carrying pipes for the discharge of the daily 10 million gallons and the monthly 160 million gallons of compensation water. This discharge has entailed an expenditure of 300,000 pounds, and except in the Venry stream itself, where its importance is small, its effect is trifling, and a concession rather to official pressure than to public needs. About 3/4 of a mile from the southeast end of the lake there rises from the water an ornamental tower connected with the public road, constructed by the corporation at considerable expense along the northeast side of the lake by 4 masonry arches. This tower is 170 feet high and stands out 60 feet above top water level. On the outside of the tower are 2 inlet valves, each made up of 6 9-foot tubes superimposed vertically on one another, end to end. By means of internal guides and a system of catches, it's possible to separate any number of these pipes from the pipes below, so as to permit the inflow of water at any one of 6 different levels. The lowest joint is connected by a U-shaped bend with a similar series of tubes working on the same principle in the interior of the tower. This enables the man in charge to draw water from the surface, where it is purest, and introduce it into the tower in a state of approximate quiescence. The floor of the interior is pierced by 3 vertical bell mouths communicating with as many as 46-inch pipes leading to the aqueduct, each of which can be closed by a throttle valve. Over the bell mouths are cylindrical strainers 9 feet in diameter and 25 feet high, of very fine copper gauze. As soon as a strainer shows signs of fouling, it is raised by hydraulic pressure and cleansed by a washing turbine that removes all clogging material from the gauze in a few minutes. A concrete culvert 730 yards long leads the strained water to a tunnel piercing the hill at the southeast side of the lake. This tunnel, 7 feet in diameter and 2¼ miles long, terminates in an open well, in which the inlets of the 3 pipelines are fixed. Each line is, or will be, of such capacity as to pass 14 million gallons daily. The total length of the aqueduct, in which there is very little tunneling, is 67 miles. It falls into 7 main portions, each of which terminates towards Manchester in a balancing reservoir on the hydraulic gradient. At Norton, where the natural level is 110 feet below the gradient line, a fine red sandstone tower of that height was built, carrying in the top an enormous bowl 80 feet in diameter and 31 feet deep at the center. The bowl is supported at the circumference only by steel rollers, which allow for expansive movements. Its capacity of 650,000 gallons renders it the largest bowl in the world. At the River Weaver, the aqueduct sinks into a channel dredged for it in the riverbed, and is held down by flanges engaging with stout piles. Between Norton and the Prescott reservoirs, the engineers had their hardest work to do, for in addition to crossing 4 railways, the aqueduct encounters 4 canals and the River Mersey. The Manchester Ship Canal length was carried out during the construction of the canal by cut-and-cover work, a culvert 305 feet long being built with terminal shafts at each end of ample section for 3 lines of 36-inch steel pipes. Scarcely had the aqueduct risen on the north side of the canal when it descends again for a long plunge under the Mersey. Quote, "In point of difficulty, this work proved to be the most important upon the whole aqueduct. It was the first tunnel ever constructed by means of a shield under a tidal or other river through entirely loose materials. A romantic and instructive account might well be written of the battles with the elements, of the repeated failures and successes, and of the hairbreadth escapes with ultimate pronounced success which attended this subterranean and subaqueous work." End quote. From Mr. G.F. Deacon, Proceedings of the Institute CE. The tunnel was only 900 feet long and but 9 feet in internal diameter, yet its construction occupied 47 months, baffled 2 contractors, and had to be completed by the corporation engineer, Mr. G.F. Deacon. The company had contemplated laying the pipes in the Mersey bed in the same way as had been done at the Weaver, but the parliamentary committee ordered a tunnel under the river. Owing to the loose and porous nature of the Mersey bed, the engineers at first proposed a tunnel that should be 104 feet below the surface of the Cheshire and 174 feet below the Lancashire side. But the estimate cost was so heavy that they decided to drive a horizontal tunnel 50 feet below high water mark. The first contractors in 20 months had sunk the shafts and driven the tunnel for 57 feet. They then ceased work. The second contractors drove in line 182 feet from the Lancashire shaft and then also relinquished the task. The great obstacle was the difficulty in keeping water off the working face. In sinking a vertical shaft under air pressure, it is easy to prevent the water from passing under the edge of the shield, which is horizontal and therefore acted upon by an external head of water at all points equally. But in the case of a tunnel, the shield is vertical, and the head increases towards the bottom of the face, so that, where a porous waterlogged stratum is encountered, if the pressure inside the shield suffices to keep out the water from the lower portion of the face, it may overcome the water pressure of the upper portion and force the air out and upwards. If, on the other hand, the upper portion only is considered, the pressure may not be great enough to exclude leakage into the lower part of the face. Matters were further complicated in the Mersey Aqueduct Tunnel by the head of water in the stratum varying with the tides. The shield employed by the second contractors was too light for the work, and the cutting edge collapsed for 1/4 of its circumference. When Mr. Deacon took over the responsibility, he had first to repair the shield, a matter of great difficulty, but when the process was completed, operations progressed at a satisfactory rate, except during 12 days consumed in further repair. At the end of 4.5 months, the tunnel was completed, the lining of cast iron segments being placed in position behind the shield as the latter advanced. The aqueduct is furnished with stop valves every 2.5 miles, and with 11 automatic valves similar to those in the thermal aqueduct to shut in case of a burst. In 1893, a telephone system was installed between Prescott and Vernry, a double line for speaking, and a number of short lines from the automatic valves to the nearest signal station, so that an alarm will be given immediately after the occurrence of an accident. On November 28, 1898, the outlet valves of the Vernry Dam were closed, except those for compensation water, and by November 25 of the following year, a new lake had been formed to the overflow level. The quantity of water now delivered through the pipes, single line, from a Westry to Prescott Reservoir is 15.5 million gallons a day. The Birmingham Scheme. The third aqueduct that we shall consider in some detail is one which in a few years will connect Birmingham with the headwaters of the Wye in two valleys of the Radnorshire. As at Manchester and Liverpool, the rapid increase of population has compelled the authorities to derive an adequate water supply from a district favored with a heavy and uncontaminated rainfall. Mr. James Mansurg, called into consultation by the corporation, laid his hand upon the little rivers Elan and Clytun in distant Wales as the source from which the great hardware town should draw a copious supply. The scheme for impounding these rivers in the same manner as the Vyrnwy was of course a very expensive one, but the common sense of the Birmingham ratepayers determined that the outlay must be faced, with the result that a bill introduced by Mr. Chamberlain in 1892 received the prompt sanction of Parliament, granting the corporation borrowing powers to the extent of £6,600,000. At a spot half a mile below the junction of the valleys of the Elan and Clytun is reared a masonry dam 120 feet high and 600 feet long, which will pen in a serpentine reservoir extending a mile up the Clytburn and about 2 miles up the Elan Valley. This reservoir is but one of 6 that will be eventually formed by as many dams, rising like a gigantic water ladder up the valleys. The total storage will be 18,000 million gallons, ensuring a maximum daily supply to Birmingham of 77 millions, in addition to 27 millions of compensation water to the Wye. At present 4 dams are in progress. The lowest, the Cabincock, referred to above, the next, the Carrigdhu, a submerged dam only a few feet high, and the third, Pennegerg, 128 feet high and 525 feet long. The fourth, Craiglocch, 120 feet high and 625 feet long. The first will impound 8,000 million gallons, Pennegerg 1320 millions, and Craiglocch 2,000 millions. The surface of each reservoir at highest level reaching to the foot of the dam further up the Elan Valley. When a still larger quantity is needed, 2 other dams will be built across the Clybourne and their reservoirs connected with the main at Cabinloch by a tunnel cut through the intervening hill. When the dams are completed, there will be seen a succession of beautiful lakes nestling between slopes well clad with woodland down to the water's edge. The masonry is of the usual solid description prevailing in such works, the greatest breadth of the foundation being about equal to that of the maximum height. For the accommodation of the workmen, a regular village has been laid out on one side of the Elan, with streets of houses, a school, recreation rooms, a corporation public house, where limited quantities of liquor are sold at certain hours, and well-ordered hospitals. A bridge over the river is the only approach, and every one who would enter the village to seek employment is examined as to his physical condition, health, and capacities before he is allowed to cross. A sort of octroi is established at the bridge end to keep out contraband articles, among which liquor is chief. Thanks to these arrangements, the health and well-being of the community has been maintained at a high level, and the precedent is one which may with great advantage be followed. End of Chapter 3.
Chapter 4 of The Romance of Modern Engineering. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Romance of Modern Engineering by Archibald Williams. Chapter 4, The Fourth Bridge. A glance at the map of Scotland serves to show that that country is nearly cut in half, towards its southern end by the firths of Clyde and Forth running inland from the west and east respectively. They find their counterparts in the Severn and Thames estuaries, which, in a similar fashion, interrupt direct natural communication between the southern and midland portions of England. The interruption is, however, more serious in the Forth than in the Thames, inasmuch as the intervening water space is broader, and because South Fife and the Lothians are proportionately more important than Kent and Essex. In the case of the Thames, too, the estuary has narrowed into a river long before large towns are reached, and the crossing, even in its tidal parts, is a matter of small danger or difficulty. Until recent years, a traveller in the east of Scotland, when desiring to pass from Edinburgh to the counties of Fife and Perth, had to choose between an inconvenient and sometimes stormy passage of the Forth in a steamer at Queensferry, and making a long detour by rail round by Stirling. The loss of time entailed, in either case, was a serious handicap to traffic between the counties north and south of the Forth. And at length, it became so intolerable that schemes were propounded for connecting the banks of the Forth by a permanent means of intercommunication. As long ago as 1805, a proposal was brought forward to construct a double tunnel under the bed of the Forth, but matters got no further than the issue of a prospectus and pamphlet setting out the advantages of such a tunnel. 13 years later, one James Anderson, an engineer whose ideas and theories were on too large a scale for the engineering science of the time, suggested the erection of a bridge at Queensferry. The bridge to contain main spans of 1,500 to 2,000 feet, be 33 feet wide, and to cost the very modest sum of £205,000. The extant designs of the bridge make it clear that it was as well for any would-be shareholder that the scheme never passed beyond the paper stage. When, however, in 1860, the greatest originator of vast engineering undertakings, the railway, moved in the matter, things began to wear a more feasible aspect. The North British Railway planned a bridge about 6 miles northwest of South Queensferry on 500-foot spans. But the project was dropped, to be revived in 1873, when the Fourth Bridge Company was formed to carry out the designs of Sir Thomas Booch for a suspension bridge with 2 large spans of over 1,600 feet each. The capital was actually subscribed, and an act authorizing the construction passed through Parliament. A commencement had been made on the island of Inchgarvie in the foundation of one of the great main piers, 550 feet high, when the work was suddenly stopped by the terrible disaster of the Tay Bridge in December 1879. Sir Thomas Booch, as the engineer of that ill-fated structure, lost the confidence of the company and the public. His designs were, therefore, laid aside, and investigations made into alternative methods of crossing the Forth. The committee of experts appointed to draw up a report abandoned, after due consideration, all ideas of driving a tunnel under the estuary, since the excavation necessary for the approaches on both sides would involve a very great outlay, and decided in favor of a bridge. In 1881, Messrs. Fowler and Baker, since honored with a baronetcy and knighthood respectively, submitted plans for a cantilever bridge of an altogether unprecedented size, to be constructed between North and South Queensferry. Before going further into an account of this mammoth structure, it will be well to explain the principle of the cantilever. An engineer, let us suppose, is called upon to bridge a gap of several hundred feet. How he will proceed to accomplish his task depends chiefly on the natural conditions of the locality where the bridge has to be made. If, for instance, there is dry land or shallow water on a hard bed below the gap, and the perpendicular height is not excessive, he may elect to build steel or brick piers a moderate distance apart and to lift onto the top of these girders of the truss type, each completed before being moved, and when placed in position independent of its neighbors, its weight being borne at either end by a pier. But when conditions decree that the points of supports must be few and far apart, the difficulties of our engineer are much increased. In the case of the Britannia Bridge, Stevenson built huge tubular girders of 460 feet length and hoisted them into position by means of hydraulic presses. But the difficulties to be overcome were enormous, and such a proceeding would be practically impossible with spans of 500 to 1,000 feet. When such are required, the engineer resorts either to the suspension type of bridge, to be seen at Clifton, Hammersmith, Niagara, Brooklyn, or builds out from his supports on both sides simultaneously in such a manner that the structure as it proceeds is in a state of balance. The balanced arms may be rigidly joined to neighboring arms in the middle of the span, and the connections over the piers severed so as to resolve the structure into a series of independent girders of the type first mentioned. Or a gap may be left, and this be bridged over by an intermediate girder resting at each end on the arms. In this case, the piers, or points of contact, are the centers of pairs of cantilevers, as the balanced arms are named. To make this quite plain, let us suppose two chairs to represent bases of two piers of a cantilever bridge. Men seated on the chairs are the towers. They raise their arms simultaneously, maintaining their vertical balance. A very small pressure would depress their hands, so they are provided with sticks, which they grasp firmly at the upper end and rest against the seat of the chairs. A weight now hung from their hands is borne by the power of the sticks to resist compression and the strength of the arms to resist extension. Our men are two pairs of cantilevers. Between them is, let us say, an interval of 2 feet. This is bridged by a board of proper length resting on the upper extremities of the two inner sticks. If a third man sits on this suspended girder, his weight causes his companions to lose their balance and fall inwards. So a couple of heavy weights are placed on the floor, immediately under the outer hands, and straps are passed from the anchorages over the hands. The cantilevers can now withstand the weight on the central girder without losing their equilibrium. This explanation made, we will return to the plans for the fourth bridge. Footnote: adapted from an illustration given by Sir B. Baker in a lecture at the Royal Institution. End footnote. On the north shore of the Forth, at North Queensferry, a somewhat triangular-shaped promontory projects southwards for 1.25 miles into the water. At a distance of almost exactly 1/3 mile south of the outermost point lies the small island of Inchgarvie, crowned by an ancient castle. Between Fife and Inchgarvie runs the main or north channel of the Forth, over 200 feet deep and more generally used by shipping than the south channel, equally deep and wide between Inchgarvie and the southern shore. There is on the south side of the south channel an expanse of shallow water 2,000 feet wide. The engineers erected 3 huge steel towers, each resting on 4 massive piers, on the extremity of the North Queensferry promontory, the western end of Inchgarvie, and in the shallow water at the south edge of the South Channel. Each tower is 343 feet high from the piers to the summit of the steelwork, and a man standing on the ladder would be 361 feet above the high water level. From these huge supports, 6 cantilevers are built out, each 680 feet long. Those at the north and south ends rest on viaducts leading from the higher ground at a level of 157 feet above high water, the level of the permanent way. The other 2 pairs terminate while yet 350 feet apart, and these intervals are bridged by a couple of girders resting on the cantilever ends. The bridge thus contains 2 enormous spans of 1,710 feet each between the towers, the vastness of which will perhaps be better comprehended if we suppose one tower to be situated in the Strand opposite Chancery Lane, a second in the same thoroughfare at the Waterloo Bridge crossing, and the third on the Trafalgar Square side of St. Martin's Church. In height, the towers would rival that of St. Paul's Cathedral. On the north shore of the bridge is approached by a viaduct 289 feet 11 inches long, and on the south by one 1,978 feet. The total length of the structure, including the length of the towers, 145, 260, and 145 feet respectively, is 8,295 feet 9.5 inches. The 2 main spans, crossing the 2 channels, permit the passage at all states of the tide of vessels whose topmasts are not more than 150 feet above high water level, for a distance of 250 feet north and south of the central line of the spans. The 3 central towers, to be referred to as the Fife, Inchgarvie, and South Queensferry, each rest on 4 solid piers of masonry, built up from a firm foundation. Viewed sideways, the 4 vertical columns composing a tower are parallel, but when seen from the railway track, a decided taper is noticeable. The batter of 1 in 7.5, which contracts the towers from 120 feet at the bottom to 33 feet at the top, is maintained throughout the structure to the cantilever ends, where the height has shrunk from 330 to 34 feet, and the width from 120 to 32 feet at the bottom. Inchgarvie Tower is longer than the other 2, 260 feet as against 145, for reasons that will be seen immediately. The sides of the towers are strengthened by huge tubular bracings, which run from the foot of one column to the top of its neighbor, and all 4 columns are connected together horizontally, both top and bottom, by powerful ties. In addition to these are a number of smaller bracings running in all directions, giving the whole structure wonderful stability. Nature had favored the engineers by placing Inchgarvie in mid-channel and providing firm matter on which to erect the piers. But, on the other hand, the Forth is exposed to gales, which on several days of the year blow with such fury as to prevent the passage of even paddle steamers. The enormous pressure of a wind, blowing upwards of 20 pounds to the square foot on a structure of the size of the Forth Bridge, had to be reckoned with. The tapering shape of the cantilevers towards their extremities had the effect of offering least surface to the wind where it had most leverage to twist the cantilevers about their supports, and the straddling of the columns further minimized danger from air pressure. But Messrs. Fowler and Baker thought it best to make a slight concession to the elements, by a contrivance that also provided for longitudinal expansion and contraction of the steelwork under varying temperatures. Accordingly, one of the 4 columns in each tower was fixed rigidly to its pier, but the other 3 carried at their lower extremities bed plates, moving over corresponding bed plates attached to the piers. Strong bolts passing up through slots in the upper plates allowed the latter to move slightly horizontally, some in a circular path round the fixed pier, and all in the direction of the center line of the bridge. The 2 extreme cantilevers were so fixed at the viaduct ends as to prevent side play, but permit longitudinal expansion. The Inchgarvie Tower differs from the other 2 in having neither its north nor its south cantilever fixed, and both can therefore exert a twisting strain on the tower. Great care was necessary to make due provision for such movements in the attachment of the suspended girders in the middle of the 2 main spans. They are hung in such a manner from the cantilevers that longitudinal expansion is possible in both girders at their Inchgarvie ends through the medium of sliding blocks, while rocking posts or pivots are provided at both ends to enable them to adapt themselves to any lateral sway of the cantilevers. Inchgarvie Tower, on account of its splendid isolation, is also at a disadvantage with regard to live or train loads. If 2 heavily laden trains pass one another at the end of a cantilever, they exert a great pull on the central tower, tending to lift it from its further piers. In the case of the Fife and Queensferry towers, such a loss of balance is obviated by terminating the landward cantilevers in huge boxes, each containing 1,000 tons of iron and resting on the end viaduct piers. Such a provision was impossible for Inchgarvie, so the engineers increased its length by 115 feet to give the columns further from the live weight a greater counteracting leverage. It is interesting to notice, as an example of the thoroughness with which all the work on the 4th bridge was carried out, as a preliminary operation, 3 wind gauges were erected in the summer of 1882 on the top of the old castle on Inchgarvie, and daily records taken. 2 of these were fixed to face east and west, from which directions the wind would strike the bridge almost at right angles to its longitudinal axis. The 3rd revolved to meet wind blowing from all quarters. The largest windboard, 15 by 20 feet, or 300 square feet in area, had cut in it 2 circular openings of 1.5 square feet area, the one at the exact center and the other at the right-hand top corner, each containing circular plates registering pressure independently of the rest of the board. The fact that on March 31st, 1886, the upper opening recorded only 22 pounds per square foot, while the center pressure rose as high as 28.5 pounds, seems to show that great wind pressures are very unevenly distributed over a large surface. This is confirmed by the records of 2 additional revolving gauges set up on the central towers, where simultaneous pressures varied as much as 10 and 12 pounds between the different piers. The first thing to be done in the actual work of construction was to accurately fix the positions of the main circular piers. Direct measurements with tape and chain being impossible, the surveyors had recourse to triangulation. A baseline, 4,000 feet long, was laid on the south shore, an observatory built, 3 points taken on the center line of the bridge, and 20 other stations laid down as required. Careful trigonometrical calculations were made, but in order that there should be a minimum of error with regard to the distances apart of the 3 principal stations on the center line, the measurement of the north span of 1,700 feet from the center of the north circular pier on Inchgarvie to the south circular piers on Fife was checked in the following manner, as described by Mr. Westhoffen in his account of the 4th bridge. Footnote, to which account the author is greatly indebted for his information. End footnote. In a straight portion of the North British Railway, a distance of 1,700 feet had been carefully measured and marked, and transferred to high posts at the sides of the cutting. Upon these posts notched knife edges were placed at the two extremities. A fine steel wire, about 1/20th of an inch in thickness, was laid along the span and drawn over the knife edges with a certain amount of stress put upon it, previously agreed upon. Thus drawn up, the wire left a certain amount of sag in the center, which was carefully measured by level and noted. Two narrow copper tags were then soldered on to mark the endpoints. The wire was then coiled up and kept ready for use. The temperature was noted. On the two shores, immediately under the piers which marked the stations, places had been prepared for levels, by means of which the amount of sag in the wire could be fixed. On a calm, cloudy day, with the temperatures about the same, the wire was taken across the North Channel and laid down upon the prepared knife edges on the piers, and with the same amount of sag allowed, the two copper tags soldered on should have coincided with the notches in the knife edges, provided the distance was correct. The results showed a discrepancy. But after the main spans were completed and measurements taken along the girder, the difference was reduced to but 1 inch in the north span and 6 inches in the south. The amount of preparatory work to be done before building operations got into full swing was on a scale proportionate to that of the bridge itself. On the south shore, the high ground was cut into terraces, and on these were erected a shop for fitting the tubular parts of the bridge, another for the lattice work, a drill road, a carpenter's shop, a pattern shed, and a drawing loft, 200 feet by 60, in which, on a blackened floor, full-sized drawings and templates of the various parts of the superstructure were made. By the edge of the water, a sawmill was established. Houses for accommodating a small army of workmen had also to be built, and a water supply provided. Special services of trains and steamers were organized. An efficient system of handling, storing, and transporting materials for 140,000 cubic yards of masonry and 55,000 tons of steel, besides an equal weight of temporary appliances, was devised. A cable for telephonic communication between the various shops and offices at working centers crossed the bed of the Forth. And we may close a very incomplete list by naming the construction of a jetty, 50 feet wide and 2,100 feet long, extending from the South Queensferry shore to the piers of the Queensferry Tower. This jetty was a considerable piece of engineering in itself. It carried lines of rails for conveying stores and steelwork to the Queensferry piers, or to barges plying between it and Inchgarvie and Fife. 10 out of the 12 circular piers, carrying the 3 towers, were constructed by means of caissons and cofferdams. These may be described as contrivances for laying dry a space below water level or preventing a free flow of water over it. In soft ground, a cofferdam is formed by driving down 2 circles of long contiguous piles, leaving between them the circles a space of a few feet, which is filled in with watertight clay puddle. The dam thus formed is provided with sluice gates to let in water when required. In some cases, the water is excluded until half tide, when the rising pressure may make it expedient to admit water, so as to equalize the pressure on both sides of the dam. When the dam is strong enough to resist high water pressure, it is called a whole-tide dam, and the space inside can be worked upon continuously. On rock, recourse is had to steel-sided caissons, the sides being cut to fit the contour of the rock on which they rest, and their bottom edges made watertight by means to be presently described. In deep water, where outside pressure becomes very severe, an ingenious structure called a pneumatic caisson is used. This consists of an upright circular iron cylinder, resembling a gasometer in outline, built of stout plates closely riveted together. 6 or 7 feet from the bottom, a watertight metal diaphragm, or floor, shuts out the lower part of the caisson from the upper air, and so gives it, when the hole is sunk, the properties of an ordinary diving bell. Leaving for a moment a further description of the caissons, let us turn our attention to the following table, showing the depth of the deepest points of the 12 piers of the Forth Bridge towers below high water. Fife, northwest, 7 feet below high water. Fife, northeast, 7 feet below high water. Fife, southwest, 25 feet below high water. Fife, southeast, 37 feet below high water. Inchgarvie, northwest, 23 feet below high water. Inchgarvie, northeast, 26 feet below high water. Inchgarvie, southwest, 72 feet 1 inch below high water. Inchgarvie, southeast, 63 feet 9 inches below high water. Queensferry, northwest, 85 feet below high water. Queensferry, northeast, 89 feet below high water. Queensferry, southwest, 71 feet below high water. Queensferry, southeast, 73 feet below high water. As each of the piers rises 18 feet above high water, the total height of the structure at the northeast of Queensferry Tower is 300 plus 89 plus 18 equals 437 feet. No dams were required for the Fife North piers. The Fife South piers were built inside steel and wooden pile cofferdams. In the case of the Inchgarvie North piers, stagings were erected over the sites of the piers and soundings taken at intervals of 6 inches round the circumference of a 50-foot circle. An iron belt 3 feet deep and 60 feet in diameter was then constructed, and to this were attached vertical steel plates of a length corresponding with the depth of water immediately beneath. As soon as the hole had been completed, the shell was lowered into place, the uppermost part resting in a groove cut in the higher levels of the rock. Rows of concrete bags were then placed outside, and clay rammed between them and the plates until tight joints permitted the pumping out of water at half-tide, an operation entailing the removal of 590,000 gallons in less than an hour's time. From a reader's point of view, the remaining 6 caissons, the southern Inchgarvie and all 4 Queensferry, working on the pneumatic principle, will be of a special interest, and as such merit a more detailed description. The pneumatic caissons, 70 feet in diameter at the bottom, and of different heights, were erected on the South Queensferry shore, and when complete were loaded with concrete and tools and launched to be towed to their final resting places. These last had already been carefully surveyed by means of a circular raft of planking and timber box 70 feet across, having a central upright staff and a carriage running on a circular rail laid a foot from the outer edge. Attached to the carriage was a drum of steel wire, raising and lowering a 60-pound weight for taking soundings. The raft was moored in such a position that its central staff occupied a certain point determined by instruments, and soundings were made. At South Inchgarvie, where the foundation is sloping rock, piles of sandbags were arranged at the points of greatest depth, so that the caissons should settle on an even keel. These caissons, after being towed into position, were gradually loaded with deposits of concrete until they began to touch ground at low water. Additional piles of sandbags were then placed below in the air chamber, and the rock was gradually cut away on the high side to make a chase for the caisson to rest upon when loaded sufficiently to lose all its buoyancy at high water. The circular area of bedrock and the supports were then removed by degrees. Let us imagine ourselves furnished with the engineer's permission to visit the working face below a caisson. On reaching the deck of the caisson, we see a powerful steam crane raising loads of debris out of an airlock at the upper end of a tube communicating with the air chamber 60 feet below. We are ushered into the workman's airlock, a circular chamber with another circular chamber 3 feet 6 inches diameter in its center. The doors through which we entered are then closed tight, and a tap communicating with the air chamber opened until the pressure has gradually risen sufficiently to allow the opening of doors in the central tube. We descend ladders, experiencing a sensation of great oppression on the ears and eyes, and presently find ourselves among the workmen, mostly North Italians, with a sprinkling of Germans, Belgians, French, and Austrians, who have been brought over by Monsieur Coiseau, the contractor, for this part of the work, not as being better physically able to work under such circumstances than Britons, but as more experienced. Powerful electric lights of 200 candle power illumine the chamber, the sides of which slope outwards towards the bottom, ending in a stout steel cutting edge. 2 men, armed with heavy sledgehammers, are beating on the top of a crowbar held by a third. They are drilling or jumping holes for blasting charges. As soon as enough are made, the charges will be inserted and, when everyone has withdrawn, after carefully shielding the lamps, be fired from above by electricity. Then the men will descend again and remove the debris by means of the skips that pass up and down their own airlock and well. Under one side of the caisson, where piers of concrete bags support the edge, men are thrusting out sandbags that have served their purpose, and in the gaps we may perhaps see the startled visages of salmon, dogfish, and other denizens of the deep that from time to time are attracted to the glare of the lights within. In the Queensferry caissons, a somewhat different spectacle would present itself. The drills and cement piers are absent. There is no preparation for blasting, for we stand now on more or less stubborn clay. If the sinking of the caisson is still in its earlier stages, we make the acquaintance of the air ejector for discharging the silt that mixes readily with water. A man standing in the muddy mixture lowers to its surface the nozzle of a hose, and another man turns on a large tap that controls the passage of the compressed air of the chamber to the outer atmosphere. As soon as the tap is opened, a rush of air takes place, and the nozzle being dipped into the liquid, some of the latter is carried up by the hose by the momentum of the air and shot out at the farther end of the piping in intermittent spurts. The rate of ejection depends largely on the skill of the operator. On reaching the hard and stubborn clay below the silt, the workman's energies become unequal to the task of removing the spoil by mere muscular effort. The forces of nature are now called in. An hydraulic spade, the invention of Mr. Arroll, is set up. A word about this spade. It is, described briefly, an hydraulic ram working at a pressure of 1,000 pounds per square inch. To its lower end is attached a large spade, and to its top a headpiece. 2 men fix it vertically, with its head against the roof of the chamber, and another turns on the water, which with giant strength forces the spade into the boulder clay, detaching a slice 16 to 18 inches deep and 4 inches thick. The spade is then moved on a little, and the operation repeated until trenches have been cut all over the bottom. The air pressure under which the excavators had to work rose on occasions as high as 40 pounds to the square inch, yet not a single death can be directly attributed to these abnormal conditions. The principal bad effect produced by air pressure, says Mr. Westhoffen, appears to be that of severe pains in the joints and muscles of the arms and legs. as these have been in most cases traced to hard work and copious perspiration, and also to too long a stay under pressure, it has been suggested as a probable cause that small globules of air make their way through the skin, or between the skins, where they remain and, on the workman returning to ordinary atmospheric pressure, expand, and thereby cause the most agonizing pain in the joints, the elbows, shoulders, kneecaps, and other places. In seeming confirmation of this, the sufferers got instant relief on returning to high pressure. Thus it happened that many of those afflicted with this disorder spent the greater part of Saturday afternoon and Sunday under air pressure, and only came out when absolutely obliged to do so. Various researches were made by members of the medical staff in the endeavor to give relief or obtain a cure, but, so far, not with any degree of success. Owing to the nature of the river bottom, the sinking of the Queensferry caissons was a matter of much anxiety to the engineers. At low water especially, when the cutting edge bore down with greatest force, a sudden settlement was to be feared, and therefore the men were then generally withdrawn, a precaution that on one occasion at least was amply justified, for the caisson, without warning, sank 7 feet, filling not only the air chamber, but also part of the airlock shaft with mud and silt. The most serious accident that took place during the building of the bridge happened to the northwest caisson of Queensferry. It had been towed into position during the high tide, and at the ebb took the ground so firmly that, an unusually high tide occurring soon afterwards, it filled and canted over. The consequent pumping operations were conducted too fast, and before the caisson could be sufficiently strengthened on the inside, the water outside burst in the plates, making a rent about 30 feet long on the lower side. This unfortunate occurrence necessitated the construction of a heavy timber frame round the caisson, and nearly 10 months passed before it was afloat again. As soon as the caissons had reached their full depth, all tools and appliances were removed from the air chamber, and this last filled up with concrete shot down the shafts. Then the caisson above the chamber was filled to low water level, where the granite courses commenced, having at this point a diameter of 55 feet. At 18 feet above high water level, the piers terminate, and are carefully leveled to receive the lower bed plates, which are securely held down by bolts built into the masonry. Piers being ready, the erection of the steel superstructure commenced in the fixing of the skewbacks, or great steel tubes with one side flattened and attached to the upper bed plates. From the skewbacks ran out the lower members of the cantilevers and columns of the towers, the huge diagonal struts uniting the foot of one column with the top of its neighbor, and horizontal girders towards the other piers. As soon as the horizontal work immediately above the pier was finished, the vertical columns were taken in hand. Huge plates, already correctly drilled and shaped, 16 feet long and a half-inch thick, were placed in position by means of cranes. When columns and struts had reached a point 50 feet above the piers, stagings were built on girders 190 feet long in the Fife and Queensferry towers, and 350 feet at Inchgarvie, these girders resting in turn upon very strong box girders stretching east and west from column to column, and raised at each end by powerful jacks situated in the columns themselves. On this manner the need for continuous scaffolding was obviated, and a riveting cage, consisting of a riveting machine enclosed in a cylinder of stout iron wire to prevent loose rivets, tools, etc., from falling with disastrous effects on the workers below, followed the stagings up the column, making permanently secure all the work bolted in position by the men above. Pressure on the rams required to lift the stagings, which at Inchgarvie weighed 700 tons, was 3,920 pounds to the square inch. we read that the first lift of the Inchgarvey platform occupied 18 days, whereas the last, owing to the increased skill of the men, took but 5 hours. Great care was necessary in the erection of the towers to ensure that their lateral batter and center lines should be absolutely correct. From time to time, the structure was checked by means of theodolites, and when any deviation from accuracy had been observed, hydraulic rams were applied to force the tubes into their proper position. Anyone who has tried to bend or straighten the small tubes of a bicycle will have some faint idea of the power needed to master these giant 12-foot cylinders. On the completion of the towers, the lower and upper members of the cantilevers were commenced. The upper members, being in tension, are all straight and of lattice girder work, but the lower, or compression members, are of tubular construction and spring outwards in an arc of polygonal outline, as it was found inexpedient to curve the tubes. The tubes shrink in diameter and thickness as they leave the towers and approach laterally to the corresponding tubes of the nearly parallel member on the other side of the cantilever, so that at its end the cantilever has diminished in breadth from 120 to 34 feet, thereby gaining greatly in power to withstand wind pressure. Both top and bottom members were built out by the help of traveling cranes, which, starting at the foot and summit of the columns, raised material from barges in the river below, placed it in position, and then moved forward. On reaching the ends of the cantilevers, they climbed the upper bow-shaped surface of the suspended girders. These were built out from their ends in a manner similar to that of the cantilevers, and a junction was effected near their centers as soon as the temperature of the atmosphere had expanded the steelwork of the whole structure sufficiently to bring the final bolt holes opposite one another. The false work connecting the girders to the cantilevers was then cut, and the girders rode free in their slides and rocking posts. In the case of the north-central girder, an interesting episode took place. The junction had been made, and the men were cutting the rivets of the false work, when suddenly the remaining rivets, some 36 in number, were shorn by the contraction of the structure, and the plate ties parted with a noise like that of a large gun, shaking the bridge slightly from end to end. The incident caused a little temporary alarm, and lost none of its importance as reported in the papers, but so far from being a mishap was merely an instance of nature saving men a considerable amount of toil. The permanent way was laid on the internal viaduct traversing the bridge from end to end. 4 parallel rail troughs, 18 inches deep and 16 wide, were filled for 6 inches with teak and pine blocks, and on these the plate layers placed longitudinal teak sleepers, securely bolted down at intervals to the blocks. The rails, of bridge section, are exceedingly heavy, weighing 120 pounds per lineal yard. At the sliding ends of the central girders, where there is allowance made for a longitudinal expansion of 2 feet, special ingenious joints are provided which enable the rails to slide backwards and forwards without losing their gauge. On each side of the track is a 4-foot path for the exclusive use of the officials of the line employed in looking after the bridge. Before closing this chapter, which, for want of space, has not dealt with many interesting points of construction, we may notice some statistics, which will escape the charge of dryness in that they help the reader the better to appreciate the nature of the undertaking. Work on the bridge began in January 1883. On March 4th, 1890, the then Prince of Wales formally declared the bridge open to traffic, in a severe windstorm that impressed the company present by its impotence to shake the mighty framework of steel. The 7 years of work represented an expenditure in materials and labor of £3,177,286, the largest half-yearly payment being made in the last 6 months of 1887, when 253,500 pounds were dispersed. The piers carry a total weight of 50,958 tons of steel. Of this, Inchgarvie Tower alone weighs 7,036 tons, or nearly as much as the Eiffel Tower, which could be laid comfortably in either of the two main spans. And a column twice as high as St. Paul's, laid at its end, would barely fill the gap remaining. To sever the top ties of the towers, a strain of 45,000 tons would be required, and Sir Benjamin Baker himself assured his audience at a lecture that half a dozen of our weightiest ironclads could be safely suspended from the cantilever ends so far as the bridge was concerned. The total number of rivets is at least 6,500,000. Allowing an average length of 2 inches a rivet, they represent a bar 200 miles long, varying in diameter from 1 1/8 inch to half an inch. As many as 4,600 workmen were engaged on the bridge during the busiest times. Among these, accidents were frequent, but mainly attributable to the indifference and carelessness of the men themselves, who, in spite of repeated ocular proofs to the contrary, appeared to think that the fall of a carelessly thrown chisel or other tool would not be attended with disastrous results. We are not, therefore, surprised to learn that in 6.5 years no less than 57 fatal and 106 very serious accidents occurred, and it comes as a curious reminder of the unreasonableness of workmen to read that the principal strike was brought about by the fall of a riveting stage, which collapsed because those responsible for its management neglected ordinary precautions while hoisting it. Nothing that can be said will probably more vividly present to the reader the size of the bridge than the statement that the area to be painted once every 3 years, inside and outside, is 145 acres, or that of a good-sized farm. The whole of the outer surface was covered 5 times during construction, once with boiled linseed oil, twice with red lead, and twice with oxide of iron paint. A large staff of men is always at work putting on fresh coatings to withstand the corroding action of the salt sea breezes. The railway passenger is in a particularly unfavorable position to view the bridge as he passes. By putting out his head, he can only see a long vista of huge tubes and girders, foreshortened in such a way as to lose their full impressiveness. Moreover, he is at an elevation near the center of the total height. To get a just scenic idea, one should approach the bridge by boat on the 4th, so as to take it in flank. Then what a stupendous structure it is, a thing of huge lines and triangles, its geometrical repetitions out of keeping with the lovely landscape, and yet having a grandeur of their own. With what pride must the engineers have looked upon the finished structure, the child of their brains, remorseless consumer of steel and stone, reared amid the clash of monster machines, nursed by small armies of workmen. What were the 8 years of battle with wind and wave, and their trials and struggles, now that the last rivet had been driven in, and the track opened for the iron steed, a mere fly among the steel web of the bridge, yet the whole built for the passage of the fly. Surely the 4th bridge is the incarnation of engineering romance, in which brain and metal and stone have joined hands with the powers of nature to triumph over the obstacles placed in man's way by nature herself. Mr. Westhoffen, the engineer in charge of Inchgarvie, has an eye for the picturesque, and the author feels that he cannot do better than quote in conclusion his eloquent description of the view to be had from the bridge. The view from the summit of the central tower on a clear day is magnificent. The broad river itself, with craft of all sorts and sizes, in steam or under sail, running before the wind, cutting across the current on tack or lazily drifting with the tide, is always a most impressive spectacle, upon which one can gaze for hours with an admiring and untiring eye. And such it is, Whether viewed in the glory of sunrise or sunset, in broad daylight, with the cloud shadows flying over the surface, and 1,000 ripples reflecting the sun's rays in every conceivable shade of color, or in the soft haze of a moonlit night. The sunsets in summer are always magnificent, whether due to Krakatoan volcanic dust or to the vapors of the distant Atlantic, but there have also been many sunrises in early autumn when a hungry man could forget the hour of breakfast, and one could not find the heart to chide the worker who would lay down his tools to gaze into the bewildering masses of color surrounding the rising light of day. An unbounded view more than 50 miles up and down river. At night, too, a sight is presented not easily forgotten. The flashing lights of the Mleigh and of Inchkeith, and many others stationary, such as the harbour lights of Granton, Leith, New Haven, and Burnt Island, combine to form a beautiful picture. At times of continued east wind, when large and small craft run for shelter in the Forth, it is not unusual to see from 150 to 200 vessels anchored in the roads, and the long straggling lines of their masthead lights give the appearance of a busy town, of many streets having suddenly risen from the waters. On Jubilee night, 21st June 1887, although the atmosphere was somewhat thick, 68 bonfires could be counted at one time on the surrounding hills and isolated points, while the great masses of the central tower of the bridge, lighted up by hundreds of arc lights at various heights where work was carried on, formed, with their long-drawn reflections in the water of the Firth, 3 pillars of fire, and afforded a truly wonderful and unique spectacle. End of chapter 4.
Chapter 5 of The Romance of Modern Engineering. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Prajakta. The Romance of Modern Engineering by Archibald Williams. The Tower Bridge. Less imposing as a structure than the giant conqueror of the Forth is the new bridge that spans the Thames a short distance east of the Tower of London, from which it derives its name. The Tower Bridge is, however, of such importance and interest, both on account of the problems that it has solved and from the manner in which it has solved them, that this great framework of metal and masonry, so familiar to the Londoner, deserves inclusion among the chief engineering feats of modern times. The general outlines of the bridge, being so well known, need little detailed description. Technically, it is a 3-span bridge, the 2 outside spans of the suspension type carried on the stout chains that pass at their landward ends over abutment towers of moderate height to anchorages in the shore, and at their river ends over very lofty towers, themselves connected at an elevation of 143 feet above high water level. Extremely powerful ties, borne on the connecting girders, unite the 2 pairs of chains, making the suspension spans to support one another in a horizontal direction. The Tower Bridge. The central span has 2 footways and 1 roadway. The high-level girders bear the upper footway, reached by 2 hydraulic lifts situated in each of the main towers. The most notable feature of the bridge, unless we accept the unique combination of steel and masonry work in the towers, is the method of enabling traffic, pedestrian and vehicular, to cross the 200-foot space between the towers at the level of the roadway of the 2 outer spans. History repeats itself in engineering as elsewhere, and as an example, we see here a reversion to the idea of the drawbridge that shut off the medieval fortress or town from the hostility of the outside world. Principle apart, however, it is a far cry from the wooden platform heaved laboriously aloft by creaking chains to the massive 1200-ton steel leveraged noiselessly by the unseen energy of hydraulic engines. Before entering into details of construction, it will be interesting to glance for a moment at the antecedent of this latest born of Thames bridges, the reason for its erection, and the considerations that cast it into its present form. Let the reader take a map of London and fix his eye on Blackfriars Bridge. A line drawn due north and south through the bridge would approximately bisect the metropolis. A steamboat travelling westwards from this point passes in succession under Waterloo, Westminster, Lambeth, Vauxhall, Chelsea, Albert, Battersea, Wandsworth, and Putney bridges, 9 in all, open to vehicular traffic. On an eastward journey of equal length, it would, however, have to lower its funnel for but two, the southward and London, assuming the Tower Bridge to be still in the future. Yet both banks are thronged by some of the most densely populated districts of London, so near each other and yet so far for want of means of communication. A further reference to the map shows us why things should be so. This is a region of docks and wharves, the latter reaching up to London Bridge, from which we have often watched the unloading of cargoes. The engineer called into effect a compromise between the crying needs of road traffic on the one hand and the equally important interests of river traffic on the other, is able to suggest several methods of cutting the Gordian knot. First, a low level bridge with an opening for vessels through it. Second, a high level bridge with inclined road approaches. Third, a high level bridge with hydraulic lifts at each end. Fourth, a tunnel under the river with inclined approaches. Fifth, a tunnel with hydraulic lifts at each end. Sixth, a ferry. Of these, the first would be most convenient for the landsman but most inconvenient for the sailor. The second and fourth necessitate very costly approaches. The third and fifth, continual blocks in the traffic, and as regards ferries, they are at best but very poor substitutes for a bridge. Among the many plans submitted since 1867 for a bridge, one is particularly noticeable for its originality, that of Mr. C. Barclay Bruce. He proposed a rolling bridge to consist of a platform 300 feet long and 100 wide, which should be propelled from shore to shore over rollers placed at the top of a series of piers 100 feet apart. The platform would have a bearing at 2 points at least, and according to the designer's calculations, make the journey in 3 minutes with a freight of 100 vehicles and 400 passengers. Another engineer, Mr. F. T. Palmer, proposed a bridge which widened out into a circular form near each shore, enclosing a space into which a vessel might pass by the removal of one side on rollers while traffic continued on the other side. As soon as the vessel had entered the enclosure, the sliding platform would be closed again, and that on the other side be opened in turn. In 1878, Sir Joseph Bazalgette, engineer to the Metropolitan Board of Works, recommended the construction of a bridge that should give a clear headway of 65 feet above Trinity high water level, but a bill brought into Parliament for power to build it was thrown out on the ground that the headway would be insufficient and on account of the awkward spatial approaches. To avoid wearying the reader with a list of projects, we will pass straight on to that of Mr. Horace Jones, the late city architect, who in 1878 was asked to report upon the various projects of Sir Joseph Bazalgette and make suggestions on his own account. He maintained that as a high level bridge would not give satisfaction, a structure of the same level as London Bridge Opening at the center by means of hinged platforms or basculars might be advantageously employed. From his design has sprung that of the Tower Bridge, the joint work of him and Sir J. Wolfe-Barry, which provides a central opening of 200 feet clear and a headway of 135 feet. An act for its construction having been passed in the autumn of 1885, contracts were let for foundations of the piers and abutment towers up to the level of 4 feet above high water mark. On June 21, 1886, the then Prince of Wales laid the foundation stone. The masonry piers on which the main towers stand are remarkable for their size, 100 feet wide by 205 long, which exceeds that of any in the world with the exception of those of the Brooklyn Bridge. The piers being but 200 feet apart, the engineers who were under agreement to leave a clear way of 160 feet between them could not build both simultaneously as a whole, since the scaffoldings would have narrowed the opening beyond legal limits. They therefore adopted a system of small caissons which should be sunk so as to form a broad wall round the area of the pier and enclose a space of 34 by 124.5 feet to be dealt with as soon as the exterior caissons were in position. On the north and south sides of each pier, 4 caissons were sunk 28 feet square and 2.5 feet apart, each end of the rows being joined by a triangular caisson. While one pier was in course of construction, the shoreward row of caissons for the other pier was also sunk, thus saving time without obstructing the river. Reference has been made in the previous chapter to the sinking of caissons, so it need here only be stated that at the Tower Bridge no pneumatic caissons were employed but only the open variety. Divers cleared away the gravel and mud until a caisson had descended such a distance into the stiff London clay at which it was thought safe to pump out the water at low tide, and then navies were turned in with pick and shovel. At a depth of 19 feet, the caissons were undercut, that is, the workers burrowed beneath their lower edges into the clay for a distance of 5 feet horizontally and 7 feet vertically. The undercutting proceeded in sections filled with concrete in succession so that the caisson should not be left unsupported. When all the 10 external caissons had been sunk and filled in, the narrow spaces between them were also filled and the interior enclosure pumped dry and excavated. Finally, there emerged from the water a couple of gigantic piers of concrete, granite, and bricks able to withstand without settlement a load of 70,000 tons. Their cost was 111,122 pounds. The contract for the steelwork in the superstructure was let to Sir William Arroll and Company of Glasgow, who, as the reader will remember, had already taken an important part in the construction of the fourth bridge. Before any metal work could be placed in position, it was necessary to erect stagings from the shore abutments to the center piers. This work occupied some months, and when it was completed, operations at once commenced on the main towers. Each tower consists of 4 octagonal columns connected at a height of 60 feet above the piers by plate girders 6 feet deep, across which are laid smaller girders to carry the first landing. 28 feet higher is the second landing, similarly constructed, and above that, at an equal distance, the third landing leading to a high level footway. The columns each rested on massive granite slabs previously covered with 3 layers of specially prepared canvas to make the pressure even and the joint watertight. They were keyed to the bedstones by great bolts built into the piers. The first length of column plates having been riveted in position by hydraulic riveters, The second length was added by means of a crane placed on the piers, and when the crane had been raised aloft on special trestles, the third length followed. The first landing served as a platform from which to build upwards in like manner to the second, which in turn became the base of operations. All four columns in each tower were braced diagonally to resist the wind pressure, calculated at a maximum of 56 pounds to the square inch, or several times greater than has ever been registered in that locality. The columns finished and the top landing girders in position, the workmen attacked the high level footway. This was built out from the both towers simultaneously on the overhang principle. First, the portions of the cantilevers immediately over the towers were erected and anchored to the shoreward columns. Then, cranes were placed on the completed portions and moved forward to add fresh plates until the cantilevers had reached the point where the central suspended girders began. As at the fourth breach, this was built on the cantilever ends to which it was attached by temporary ties, and when the center plates had been made secure, the ties were cut, allowing it to ride free at each extremity. Throughout the construction of the upper footway, the greatest care had to be observed to prevent rivets, fragments, and tools falling into the river below the peril of passengers on passing vessels. Along the upper boom of the footway run the great ties connecting the suspension chains at their river ends. Each of the two ties is 301 feet long and composed of 8 plates, 2 feet deep and 1 inch thick, terminating in large eye plates to take the pins uniting them to the suspension chains. The construction of these chains was one of the most interesting and at the same time most delicate parts of the whole undertaking. Each chain is composed of two parts or links, the shorter dipping from the top of the abutment tower to the roadway, the longer rising from the roadway to the summit of the main tower. The links have each a lower and upper boom connected by diagonal bracings so as to form a rigid girder. They were built in the positions they had finally to occupy, supported on trestles, and were not freed until they had been joined by huge steel pins to the ties crossing the central span and to those on the abutment towers. In order that the reader may have a clear conception of the action of the ties and chains, we will personally conduct him from end to end of the series. At the north end of the bridge is a huge mass of concrete surrounding an anchorage girder 40 feet long, 4 feet wide and 4 feet deep, to which is attached a land tie springing up to the shore edge of the abutment top. At the anchorage end, the tie is joined by a pin 2 feet in diameter to the girder and at its upper end to the horizontal links crossing the abutment tower. The tie is built up of 12 plates 21 inches wide and nearly an inch thick. The link plates are 5 to 5.5 feet wide and 7/8 inch thick and 22 feet long. At each end, they rest on roller bearings moving over 3-inch steel plates very carefully leveled. Then comes the short link of the chain, attached by eye plates and a steel pin 2.5 feet in diameter to the tie and also to the lower end of the long link, at which point both are joined to the girders of the roadway. Passing up the long link, we reach the top of the towers and note the great pins and roller bearings at each end of the 301-foot ties. Then down the south long link to the roadway, up the short link and over more roller bearings to the last section of the series, 12 plates 35 inches wide secured by rivets to the south anchorage girder, which is of larger dimensions than its northern fellow. This arrangement of chains, links and ties permits a slight amount of horizontal motion to compensate the stresses of unequal loading on the two suspension spans and the alterations in the length of the metal connections in varying temperatures. Roller joints are also made in the flooring of the side spans at each end and at the junction of the links to allow for longitudinal expansion and contraction. The boring of the pinholes was a matter of great delicacy and considerable difficulty. The holes in the eye plates of ties and chains had been cleared to within half an inch of their final diameter before leaving the contractor's works at Glasgow, and the finishing touches were added when the plates were in position. The labor of expanding out the holes to their full diameter was equivalent to boring a hole 2 feet 6 inches in diameter through 65 feet of solid steel, and most of this boring had to be done in somewhat awkward positions at the top of the main towers and abutments, whither it was necessary to transport engines, boilers, and boring tools. The fixing of these generally occupied as long a time as the actual boring, since the greatest accuracy had to be observed throughout the process. The roadway of the suspension spans is carried on cross girders 61 feet long, weighing 22 tons. At each end, they are connected by 6-inch pins to the suspension rods hanging vertically from the chain links. The rods are from 5.5 to 6 inches in diameter and furnished with a screw coupling at their centers to enable the accurate adjustment of the girders to the true level of the roadway. Before leaving the works, each rod had been subjected to a tension of 200 tons, so that of their sufficiency there can be no doubt. Longitudinal girders of smaller section were then laid on the transverse girders, and on these again corrugated floor plates, afterwards filled up with concrete to form a slightly convex surface over which wood paving blocks were placed. We may now turn our attention to the central span of the roadway, which forms perhaps the most interesting part of the whole structure. Each bascule or leaf of the drawbridge consists of 4 parallel girders 13.5 feet apart and about 160 feet long. When lowered, it projects horizontally 100 feet towards the opposite tower, spanning exactly half of the opening. The point of balance is a solid pivot 1 foot 9 inches in diameter and 48 feet long that passes through the girders 50 feet from their shore ends. The pivot is keyed to the girders and rotates on roller bearings carried by 8 girders crossing the piers horizontally from north to south, themselves borne on the girders under their ends. The chief difficulty attending the erection of the bascules resulted from the condition compelling the contractors to leave a clear way to 160 feet between the towers. Under other circumstances, the girders might have been completed before being brought into line and connected together. As it was, the engineers first built the portions on the shore side of the pivot, added a short section of the riverside steelwork, and launched the incomplete girders from the main stage close to the piers into the bascule chambers. A temporary steel mandrel was inserted to carry their weight while they were turned into a vertical position, and then withdrawn to make room for the permanent pivot weighing 25 tons. The outer ends were added to until a point 53 feet from the pivot had been reached, and work in this direction then stopped until the raising and lowering of the leaves for purposes of adjustment had been concluded, after which the girders were completed vertically. The leaves are moved by means of pinions or cogwheels engaging with racks fixed to the edge of 2 steel quadrants riveted to their 2 outside girders. The accurate attachment of the racks was a somewhat difficult business on account of the confined space in which the main had to work. To preserve the balance of the bascule, it was necessary to load the shorter or inner arm with counterpoises consisting of 290 tons of lead and 60 tons of iron enclosed in ballast boxes at the extreme ends of the girders. The function of the raising gear is merely to overcome the inertia of the 1200 tons of the leaf and the friction caused by wind pressure on the exposed surface. In designing the hydraulic machinery, allowance was made for a wind pressure of 56 pounds to the square foot, which would produce a force of 140 tons acting with a leverage of 56 feet. The source of power is a building on the east side of the southern approach where are stationed two large accumulators with 20 each rams loaded to give a pressure of from 700 to 800 pounds per square inch. An accumulator is the hydraulic counterpart of the reservoir bellows in an organ. It ensures a steady pressure as its capacity is greater than that of the engines it operates, and since the pumping engines can be constantly at work filling it, there is always a plentiful supply of energy stored against the periodical opening and shutting of the bascules. The water is laid through two 6-inch pipes provided with flexible joints at points of movement to the two sets of engines on the south pier and to those on the north pier through continuation pipes passing up the south tower, across the footway, and down the north tower. After use, the water is returned through a 7-inch pipe to the pumping engines placed in two of the arches forming the southern approach to the breach. The engines are duplicated on each pier to avoid the inconvenience that would result from the breakdown of a single installation. The power of the engines is transmitted to the racks through a series of cogwheels which increase the effective pressure of the pistons almost sevenfold. Hydraulic energy is also used to work the two hydraulic lifts in each main tower and to shoot home and withdraw the four locking bolts at the outer extremity of the southern leaf. In this connection, the following extract from Mr. J. E. Tute's fine book on the breach will be of interest. Every precaution has been taken so that the operation of opening and shutting the breech shall be rendered as safe as possible. By an automatic arrangement attached to the hydraulic engines on the piers, they are caused to close the valves which admit the high pressure water just at the end of the operation of raising or lowering the leaves, so that even if the man in charge were to make a mistake through an error of judgment or be prevented from attending to his duties, the leaves would gradually bring themselves to rest either in a vertical or horizontal position without the least chance of any catastrophe. As a still further precaution, however, hydraulic buffers are fixed in such positions that if the man in charge lost control of the bridge and at the same time the apparatus above alluded to for bringing up the motions of the leaves were to fail, their impact would be taken by these buffers, which would bring them to rest in the same manner as that in which the hydraulic cylinders that are attached to heavy guns take up the recoil. In cabins at the east and west ends of each pier are indicators to tell the man in charge whether the accumulators are full before starting the engines and whether the locking bolts are in their proper position. Further provision is made to prevent the raising of the bascules before they are cleared of traffic. The policemen in charge have to stretch a chain across the entrance to each pier. As soon as the chain is fixed, the man carrying it will be able to turn on the water to a small cylinder that draws it tight and at the same time releases the locking arrangement of the levers in the cabin, so that until the chain has opposed a barrier to the traffic, it is impossible to draw a locking bolts at the center of the span. The masonry of the towers is independent of the steelwork that it encloses. In fact, great care has been taken that there shall be no adhesion between the two substances. This part of the structure, carried out by Messrs. Perry and Company, calls for no special attention here, though it impresses itself favorably on the eye of the spectator. Objections have been raised to the external masonry on the ground that it is a hollow sham, but we fancy that were the covering suddenly stripped away, so as to expose the steel skeleton beneath, many objectors would be silenced. The general opinion is that with so many metal structures exposing the nakedness of their outlines, the London Corporation is to be congratulated on having thus boldly made a concession to the aesthetic tastes of the community, which does not detract from the value of the bridge as a utilitarian erection. The cost of construction was enhanced, but the result is one of which Londoners will be proud in years to come. The Tower Bridge, typical of modern engineering skill, has an interesting connection with the old London Bridge, itself a mechanical triumph considering the science of the time. Built towards the end of the 12th century, that bridge, which stood the wear and tear of nearly 700 years, was endowed with certain lands which, with the growth of London, became extremely valuable and are now known as the Bridge House Estates. The revenue from them has enabled the Corporation of London to rebuild the London Bridge, throw another across the Thames at Blackfriars, and also to construct the subject of this chapter. We may conclude the account by a few figures. The bridge is exactly half a mile long, including the approaches, the side spans each occupying 270 feet clear. Its extreme height, measured from the bottom of the foundations to the summit of the main tower ridge tiles, is 293 feet. The roadway of the side spans is 35 feet wide, flanked on each side by a 12.5-foot paved footway. In the central span, the widths are reduced by 3 and 4 feet respectively. Its construction, which occupied 8 years, consumed 235,000 cubic feet of granite and stone, 20,000 tons of cement, 70,000 cubic yards of concrete, 31 million bricks, and 14,000 tons of iron and steel. The columns on the main piers and abutments required 5 miles of steel plates. The total cost was estimated at £750,000, of which the bridge itself represents rather more than £500,000. Sir J. Wolfe Barry, the engineer responsible for the construction, includes among his other important works the Great Barry Dock near Cardiff and the completion of the Inner Circle Railway between the Mansion House and Aldgate stations. End of section 5.
Chapter 6 of The Romance of Modern Engineering. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Romance of Modern Engineering by Archibald Williams. Chapter 6. American Bridges. The second place among monster bridges is held by the Brooklyn Suspension Bridge, connecting Manhattan Island, on which stands New York proper, with Long Island. Previously to 1883, New York, with its population of 2 millions, and Brooklyn, counting 1 million inhabitants, were kept in communication across a narrow strait, 12 miles long, opening into Long Island Sound, known as the East River, by a number of steam ferries, one of which alone transports 22 million foot passengers and 1,100,000 vehicles annually. With the growth of population, the absence of some permanent connection between the two islands was so severely felt that it was determined to link the two with a bridge of such a height above the water as to offer no obstruction to the shipping passing down the Sound to New York Harbor. The spot selected for the bridge is at the southern end of the East River Strait, where it narrows down to a width of rather more than 1/4 of a mile. In deciding on the suspension type, American engineers had two good precedents: the Ohio River and Clifton suspension at Niagara, which then held the record in point of span. The Ohio Bridge at Cincinnati had a clear leap of 1,000 feet, while that at Niagara measured 1,268 feet between the centers of the towers, standing on either side of the gorge below the falls. This bridge, opened to traffic in 1869 as a result of but 12 months' work, hung from two cables 1,888 feet long, passing over rollers on the summit of the towers, which were built of wood strengthened by massive iron frames. The cables each contained 931 wires, 1/7 inch diameter, twisted into 7 ropes. When loaded with an average amount of traffic, the bridge weighed 360 tons. To prevent excessive lateral oscillation, strong steel guy ropes were strung from various points on the structure to anchorages on the side of the gorge. After standing and doing useful service for many years, the bridge was destroyed by one of the tremendous hurricanes that periodically sweep down the Niagara Gorge as through a funnel. There remained, however, the Niagara Railway Suspension Bridge, completed in 1855. This has a span of 821 feet, the track passing 245 feet above the river. It should be explained that the lower chord of the bridge is a girder with 2 floors, the upper of which carries the railroad, while the lower serves for foot and ordinary vehicular traffic. As originally constructed, 2 masonry towers bore the weight of the 4 cables, each containing 3,640 iron wires that support the girder. After 26 years of wear, it was discovered that these towers had been bent inwards to a dangerous extent, owing to the rollers on which the cable saddles work at the tower tops having become clogged with cement. The engineers therefore built iron skeleton towers outside the masonry, and without in any way interrupting the traffic of the bridge, transferred the cables from the stone to the iron supports by means of powerful hydraulic jacks. This is a most interesting feat and probably unique. When the bridge was in course of construction, Robert Stephenson, engaged on the Victoria Tubular Bridge at Montreal, said to the designer of the Niagara suspension, Mr. John A. Roebling, "If your bridge succeeds, mine is a magnificent blunder." The light American structure did succeed. The Brooklyn Bridge, like that at Niagara, is carried on 4 main cables. The supports are 2 huge towers rising 272 feet above high water. At the river level, they measure 140 feet broad by 50 deep, which dimensions decrease to 120 by 40 feet at the summit. On the New York side, the masonry is carried down to rock 78 feet below water level, giving the tower a total height of 350 feet. The masonry built into the 2 towers aggregated 85,000 cubic yards. The central span is 3,640 feet. Between the towers and the anchorages are two 930-foot spans, and beyond these approaches that add 2,534 feet to the total length, 5,989 feet, or about a mile and a furlong. The most interesting feature of the bridge is the cable work. Each of the four cables anchored at either end to massive 23-ton plates embedded in huge masses of masonry, each representing more than 44,000 tons, contains 5,296 galvanized steel wires, which were carried separately from tower to tower and bound up together in a parallel formation into a cylinder 15 3/4 inches in diameter. The breaking strain of a cable is 12,000 tons, as each strand is 3,572 feet long. About 1,200 miles of wire were used in the cables. These support 6 parallel steel trusses, on which is laid the roadway, 85 feet wide, divided into 2 carriage tracks, 2 tramways, and 1 footway. The bridge rises towards its center on a gradient of 3.25%, the headway increasing from 119 feet at the towers to 135 in mid-channel. The bridge cost $15 million, 2/3 of which was contributed by the Brooklyn municipality and 1/3 by that of New York. It was begun in 1870 and opened to the public in 1883. Upwards of 250,000 people cross the bridge daily, but so great is the traffic between Manhattan and Long Island that 3 more bridges are in course of construction across the East River. These will, when completed, be in the first rank of such structures and formidable competitors in regard to size with the Brooklyn Bridge. A traveler to the United States is struck by the versatility of the American bridge builder, whose genius develops most happily towards the erection of light, airy viaducts spanning many of the valleys through which the great network of railways run. The states have now nearly 200,000 miles of track laid, and on the average there is 1 span of metallic bridge for every 3 miles of railway, giving a total of over 63,000. The increase in weight of locomotives and rolling stock has led to the renewal of many of these bridges by the substitution of more substantial work, and the rapid extension of existing systems constantly demands the manufacture of new bridges. Consequently, the demand has driven manufacturers to standardize their patterns and arrive at a distinct understanding with the railway engineers that, except in special cases where divergence is unavoidable, all bridges ordered shall conform to certain stereotyped designs, which have been decided upon after much experimentation. The American bridge building companies, thanks to this scientific arrangement and the large number of orders that they are called upon to fill, have advanced the practice of bridge making to a point that enables them to compete favorably with the manufacturers of other countries. The Yankee railway engineer gives measurements to the bridge company, which by long practice knows just what is required to meet a particular case, and turns its mechanics, armed with all manner of labor-saving tools, on to cheaply made steel. In a few weeks or months the bridge is ready for delivery, the makers confident that when the pieces are assembled in situ they will come together like a clock. Very probably the company does the erecting as well, so that after the order is given, the railway board's part of the work is confined to handing over a check to the proper amount when the bridge has been passed by their engineers. On American railroads, the trestle bridge is a very common object, often towering to a giddy height that dwarfs the giant locomotives passing overhead. In 1890, there were in the States 147,187 wooden trestle spans, aggregating 2,127 miles of track. These, as liable to insidious decay and danger from fire, are being replaced by steel structures as fast as is possible. A notable instance is the Portage Viaduct on the Erie Railway, New York, crossing a river 234 feet above the bed. The old viaduct contained more than 1.5 million feet of timber arranged in piers formed of 3 grouped trestles. This was burned in 1875, and in its stead now stands a remarkably slender-looking viaduct of wrought iron, weighing but a small fraction of the wooden structure. The same railway boasts another remarkable viaduct, the Kinzua, 2,400 feet long and 305 feet high. It was built by Messrs. Clark, Reeves and Company in the short space of 3 months, without the use of any staging or ladders. The original spider-like supports have recently been replaced by steel trestles of a more solid nature, better calculated to sustain the great increase of rolling stock weight. Outside the country of its birth, the American bridge is making headway. In recent years, British builders have several times felt their inability to compete with their transatlantic cousins when creation and erection has to be hurried through. To take 3 notable examples, the Atbara Bridge, 7 spans of 147 feet, was tendered for by American makers at £10, 13 shillings, 6 per ton, construction to take 6 weeks and erection 8 weeks. The nearest English tender showed £15, 15 shillings per ton and 26 weeks. The Uganda viaducts, East Africa, also fell to American makers, since their price was but 3/5 of the English figures. And in the third instance, that of the Gokteik Viaduct, Burma, their price was little more than half that of British makers, and the contract time 1 year as against 3 years. These examples show how unequal is the competition, owing largely to the conservatism of English methods and the imbecilities of trades unionism in the British Isles. To keep his end up, the British manufacturer will need to consign much of his machinery to the scrap heap, adopt standard designs, and instill a spirit of greater enterprise into his employees. The Gokteik Viaduct, as the loftiest trestle erection in the world and among the latest born, deserves special notice. It affords a typical illustration of American methods. The Burma Railway, running from Rangoon to Mandalay, a distance of about 400 miles, has lately been extended in an easterly direction through the Shan states to Lashio en route to the Kunlun Ferry on the Salween River, following the track over which in Marco Polo's time the Chinese armies marched to Mandalay. 80 miles east of the latter town is the Gokteik Gorge, with an average depth of 1,300 feet, eaten out by the Chengzhou River. It was first proposed to cross this formidable obstacle by means of short rack railways on the apt principle, which should lower trains from the high ground to a point in the gorge where huge blocks of limestone have fallen into the glen to form a natural bridge 500 feet above the river. A viaduct 80 feet high and 500 feet long would suffice for the crossing. Eventually, it was decided to flatten the grades of the approaches to 1 in 40 and raise the viaduct level to over 300 feet above the natural bridge. It should be said of the approaches themselves that they pass through very rough country where the gradients are too steep to admit of curves. By means of switchback reversing stations every 2 or 3 miles, the train clambers slowly upwards in a zigzag course on the edge of awful precipices. On the eastern side of the gorge, the line still sticks to steep hillsides, passes through 2 tunnels and heavy cuttings, and then twists upwards by help of 3 semicircular loops. The viaduct was designed by Sir Alexander Rendell and Company, consulting engineers to the Burma Railways Company. The contract fell to the Pennsylvania Steel Company of Steelton. Our American cousins, said Sir Frederick Fryer, Lieutenant Governor of Burma, at the opening ceremonies, obtained the contract because they were able to submit a far more favorable tender than any English firm, both in point of cost and of time. Within 4 months of the signing of the contract, the first shipload of material was dispatched from New York. 2 months later it arrived at Rangoon. The transport of 4,332 tons of steel over a line that had suffered severely from the 15-foot rainfall of the wet season was much delayed, but in spite of obstacles, erection commenced in October. To facilitate the classification and separation of the various parts and the handling of them by ignorant natives, each truss, girder, and column was painted a distinctive color, and the joints, when shop assembled, were streaked with special combinations of stripes on each adjacent piece. Along with the bridge material came pneumatic reamers and riveting hammers, hoisting engines, derricks, telephones, and last, but by no means least, 35 American workmen. To aid in the erection, a temporary line was laid in zigzags down the side of the gorge. This carried material to the foot of the viaduct and also helped the transport of rails, sleepers, and even 2 locomotives in pieces to the further side, where 35 miles of track were laid during the construction of the viaduct. From Steelton to Gokteik is 10,599 miles, an almost, if not quite, unprecedented distance to send the ready-made-up parts of so large a structure. As fast as the metal arrived at the bridge end, it was whipped out of the meter-gauge cars by great steam derricks, which handed them over to smaller derricks for sorting and storage. At times, the press of work was so heavy that the trucks, immediately they were emptied, were picked up by the 15-ton crane and set down on the bank in piles many feet below the track to make way for loaded cars. As soon as sufficient stuff had accumulated, the traveler was erected at the south end of the bridge. This machine, which plays so important a part in American bridge building and is largely responsible for the celerity of operations, is a large framework, the rear end of which is anchored to a completed section of the structure, while the forward and larger part overhangs and acts as a crane through which parts of the next section are lowered into place. The Gokteik Traveler was 24.5 feet wide, 60 feet high, and 219 feet long, with an unprecedented overhang of 165 feet. Cars running along the track transferred joists and trusses to the running tackle, which quickly let them down and held them in position while the riveters, mostly natives, fixed them. Some British and German sailors proved very useful on the Traveler and topmost points of the rising towers, and set a very wholesome example to the 350-odd coolies engaged. Now for a few figures about the bridge. Its total length from abutment to abutment is 2,260 feet. For 281 feet at one end and 341 at the other, it is curved to a radius of 800 feet. The intermediate 1,638 feet runs tangentially in a straight line at a height varying between 130 and 320 feet above the natural bridge and valley slopes. There are 17 spans, 10 120 feet long, 7 60 feet long. The 15 trestles or towers, each of 4 columns with one exception, are 24.5 feet broad at top and widen towards the bottom with a batter of 5 and 24. The trestle is 40 feet long and is divided into stories 35 feet high, which are braced diagonally. At the highest point of the viaduct over the natural bridge, there is a double tower 80 feet long with 6 columns 320 feet high. The 120-foot girders are of the lattice type, the 60 and 40-foot plate-sided, 42.5 and 60.25 inches deep, respectively. The viaduct will eventually carry a double track besides a footwalk for pedestrians. At present, accommodation for the footwalk in one set of rails only has been provided. The other girders and trusses necessary for completion will be added at some future time. The men worked from 7 to 12 a.m. and 1:45 to 6 p.m., except on such days as the furious monsoon blew through the gorge, or the heavens emptied themselves in deluges of rain. Under favorable conditions, the structure rose with astonishing speed, some of the 200-foot towers going up in 3 or 4 days. The double tower consumed a month, as its immense height rendered construction more dangerous and consequently less easy. As soon as the tower was finished, the big girders for the space intervening between it and that on which the traveler rested were swung out and fixed. Then followed horizontal stringers, cross-floor beams, ties, and rails. These placed, the huge 100-ton framework rolled forward to the end of the new span and commanded another masonry pier whence a new tower soon began to rise. On November 1st, 1900, after 9 months' labor, the last of the 200,000 field rivets was driven, and the Gokteik viaduct stood complete. As 800,000 rivets had already been closed in the shops, the total shows just 1 million. It is a striking testimony to the thoroughness of American workmanship that 232,868 separate pieces shipped from Steelton fitted with wonderful accuracy when assembled in the gorge. The bridge cost the railway company £60,125, and it is considered that they have received good value for their money. Englishmen naturally regret that so important a contract should have passed into alien hands. but they will not grudge the praise due to the pushful American for a fine work, skillfully and quickly performed. End of Chapter 6.
Chapter 7 of the Romance of Modern Engineering. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Sonia. The Romance of Modern Engineering by Archibald Williams. Chapter 7. The Trans-Siberian Railway. On the 9th of November 1901, the following telegram flashed along the wires from Mr. Witt to his Imperial Master the Tsar. On May 19th, 1891, Your Majesty at Vladivostok turned with your own hand the first sod of the Great Siberian Railway. Today, on the anniversary of your accession to the throne, the East Asiatic Railway is completed. I venture to express to Your Majesty, from the bottom of my heart, my loyal congratulations on this historic event. With the laying of the rails for a distance of 2,400 versts from the Trans-Baikal territory to Vladivostok and Port Arthur, our enterprise in Manchuria is practically, though not entirely, concluded. Notwithstanding exceptionally difficult conditions and the destruction of a large portion of the line last year, temporary traffic can, from day to day, be carried on along the whole system. I hope that within 2 years hence all the remaining work to be done will be completed, and that the railway will be opened for permanent regular traffic. To which the Tsar replied, I thank you sincerely for your joyful communication. I congratulate you on the completion within so short a time, and amid incredible difficulties, of one of the greatest railway undertakings in the world. 10 years, 4,000 miles of railway laid down, more than a mile a day, a record. Europe and Western civilization at the one extremity, China and Eastern civilization at the other. In between, the greatest of the continents, and across that continent the unbroken, save for a few miles, band of iron. A huge country, covering 5 million square miles of swamp and forest and rich cornland, and mountains and deserts. A country of intense cold and great heat. A country outwardly wretched, but hiding in its bosom treasure incalculable. A country of mighty rivers, flowing from the central mountains of Asia to the Arctic Ocean, frozen solid half the year, but at certain seasons among the most magnificent waterways of the world. A country that was once inhabited by a great population, and then for ages the abode of a few wandering tribes, now receiving fresh life from tens of thousands of emigrants who pour into it from Russia over the Iron Way. A country, in short, of which but a few years ago we knew little whatsoever, even less that was enticing or creditable or propitious. We regarded it as a mere dumping ground for Muscovite criminals, chained to the deadly labor of the mines, or cast abroad to fare as best they might in the great solitudes. But now it has suddenly leapt into notice as a new land of promise, to which are turned the eager and inquiring eyes of half the world. The story of Siberia begins with the picturesque figure of Yermak, the millstone, a boatman who plied his trade on Little Mother Volga, as the Russians fondly term their mightiest river. He fell into a bad habit of piracy, and after a series of murders was forced to flee for his life to the Urals, where he met a family of traders who were preparing an expedition to Siberia, the land of the precious sable. He entered their service as trapper, and in 1581 started for hunting grounds far away in the heart of North Asia. Many doughty deeds were wrought by Yermak and his followers in their struggle with the Tatar tribes, and his victories over the savage tribes brought him pardon and great honor. But his enemies killed him at last, and other leaders took his place, penetrating further and further eastwards in search of sable, suffering terribly at times, but still pushing on the limits of the empire to Tobolsk, Yeniseisk, Irkutsk. In 1650 the gallant Khabarov conquered the territory of the Amur and brought the Russian standard to the Pacific Ocean. Then followed a period of rest for 200 years, at the end of which General Muravyov formally annexed the district, which by the Treaty of Pekin, 1861, passed into Muscovite hands forever. The Russians now had an important province in the Far East, washed by the waters of a great ocean and traversed by a noble river. They determined that it should be joined to their European possessions by something more commodious and more safe than the ill-made, bandit-infested post road that wound its muddy or frozen length across the steppes and mountains. America had been spanned by the Iron Way. Why not Siberia? The engineering difficulties arising from natural configuration would not be insuperable. Jogging the Russian elbow was the Anglo-Saxon engineer. It is interesting to note that the scheme of laying a ribbon of steel across the Asiatic continent first matured in English and American brains. As far back as 1857, an American named Collins offered to connect Irkutsk to Chita, some hundreds of miles east of Lake Baikal. The following year an English syndicate proposed a railway from Moscow to the Sea of Japan, and undertook its construction for a price. But the Russians preferred to wait until such time as their own engineers could cope with the Herculean task. For 40 years they planned and surveyed, gathering experience from the great railway pushed eastward to Merv and Samarkand. So strong was their faith in the potentialities of the great lone land of Asia as a dwelling place for their teeming millions, that when at last the work was taken in hand, they faced an enormous expenditure despite the financial straits in which their country was sometimes involved. The sum of £40 million was voted for the construction of the line. In order to expedite its progress, its total length, from Chelyabinsk on the European frontier to Vladivostok on the Japan Sea, was divided into the following divisions. 1. Chelyabinsk to Obi, the Western Siberian section, 800 miles long. 2. Obi to Irkutsk, the Central Siberian section, 1,137 miles. 3. Irkutsk to Mysolvaya, on the southeast shore of Lake Baikal. 4. Mysolvaya to Stretyansk, the Trans-Baikal section, 686 miles. 5. Stretyansk to Khabarovsk, on the Ussuri River, the Amur section, 1,326 miles. 6. Khabarovsk to Vladivostok, the Ussurian Railway, 478 miles. The first sod was cut and the first barrow load wheeled at Vladivostok by the present Tsar, who in 1891, as Tsarevich, made a grand tour of the East. A start was made at the Chelyabinsk end in the following year. Ever since, construction has steadily progressed, in the face of physical and other difficulties, at a pace which eclipses the laying of the great trunk lines of the United States and Canada. In December 1895, the Trans-Siberian was completed to Omsk, in 1896 to Obi, in 1896 to Irkutsk, 3,371 miles east of Moscow. Simultaneously, the Ussurian section had reached Khabarovsk, so that in 7 years 2,503 miles of rail had been opened to traffic. Stretyansk was reached in July 1900, and there the original scheme terminated. To avoid carrying the line along the Amur, an arrangement was come to with the Chinese government in 1896, by which the engineers were given rights to drive the track across North Manchuria in an almost straight line to Vladivostok, and in 1898 the Russo-Chinese Bank, alias Russian government, obtained a concession to make a branch due south from the Manchurian section to Port Arthur on the Gulf of Petchili. These sections were pushed forward with the greatest possible speed, owing to political events in the Far East, which demanded the presence of large bodies of troops to protect or extend Russian interests. The Trans-Siberian Railway, as measured from Chelyabinsk, has a length to Vladivostok of 3,967 miles, and to Port Arthur of 4,242 miles. If we add to this the Ussurian system and the section running northeast from Chelyabinsk to Kotles on the northern Dwina, we arrive at the grand total of nearly 6,000 miles, or about double the mileage of the Canadian Pacific. The railway in its course crosses the upper waters of the Obi, Yenisei, Lena, and Amur, at points where they begin to be easily navigable by vessels of considerable size. These rivers, each between 2,000 and 3,000 miles long, exclusive of tributaries, are being connected by canals, which will form the most splendid system of water communication in the world, and act as feeders to the great railway at many points. Their utility during the construction of the latter has been incalculable. 3 names are conspicuous among the many connected with this gigantic undertaking. Those of the Tsar, who is president of the railway committee, of Mr. Witt, the Minister of Finance, and of Prince Hirkov. Of these, the second was once a station master on the southern Russian railways, and the third worked under an assumed name as a paid employee on the railroads of the United States, where, in the shops and elsewhere, he gained the great store of practical knowledge that he is now turning to such good account. The chorus of admiration evoked by the successful termination of their labors has been unanimous. Yet questions have been raised about 2 points, on which criticism has laid a finger. To the outsider it is a matter of surprise that the railway should have given a wide berth to Tobolsk, the capital of western Siberia, and to Tomsk, the capital of the central provinces. These towns will be served by branch lines, but it is open to doubt whether in the future their importance will not decline, and new towns situated on the main track take up the mantle that has fallen from their shoulders. Engineers of other nations also wonder why rails of such lightness at 18 pounds to the foot have been used, while 20 to 25 pound rails are the common practice in Russia, and 28 to 33 pound rails the rule in Europe and other countries. We must, however, remember that the need for economy was most pressing, and that in using the lighter rails the committee have precedence in the United States, where in many instances heavy metals are laid down only when traffic has assumed certain proportions. Already sections are being relaid with 70-pound rails, those they replace being relegated to the sidings, which occur at frequent intervals throughout the system. To gain an adequate idea of the immensity of the Great Siberian, we should undoubtedly travel over it. A map, even on a large scale, is but a poor aid to the imagination. Omsk and Obi, to take an instance, seem but a few miles apart on paper, whereas a journey equal to that from London to Edinburgh separates them. Place one point of a pair of compasses at Chelyabinsk and the other at Berlin. Describe a circle, and it passes through Lake Baikal, some 1,500 miles from the journey's end. We will nevertheless endeavor to gain some conception of what the traveler sees, by calling Aladdin's genie to our aid, and transporting ourselves to the terminal station at Moscow, the finest station of the old capital, from which a train is about to start on its 4,000-mile trip. A fashionable throng fills the waiting rooms and buffets, for the departure of the Siberian Express is still a novelty, and attended by more than the usual amount of bustle and leave-taking connected with a long journey. Russians are very proud of their express, which is indeed worthy of our close attention. In it the travellers will be confined for a fortnight at least, so we will see how their comfort has been provided for. First we notice that the train is lit throughout by electric light, generated in a special compartment by a separate boiler and engine. Even the head and tail lights are fed from this source. One car is fitted up as a drawing room, with luxurious chairs and couches, upholstered in soft leather, writing tables, a piano, maps. Another contains a restaurant, where a first-class meal may be had at all hours of the day, a beautifully fitted bathroom, and an exercising machine. When you wish to retire for the night, press the electric bell button, and a servant appears to make up the comfortable bed that is cunningly folded away during the daytime. Above the bed are levers to admit fresh air or hot water to the heating apparatus as you wish. The corridors that traverse the train from end to end are provided with filter ventilators, which keep out the dust and let in oxygen. This train de luxe is put on by the International Sleeping Car Company, a guarantee for everything being all that the heart of the traveler could wish. At 9 p.m. the engine gives a deep whistle and draws out into the night, and on to the rolling steppes that stretch away monotonously east and west and south and north for hundreds upon hundreds of miles. Yet these are some of the greatest granaries of Europe. Large stretches are checkered with the green of the growing crop, or the gold of the harvest, or the grey of the stubble. Giant straw stacks proclaim an abundant harvest past, threshed by the trampling ponies of the peasant, and winnowed after the manner of the Israelites. On, over the steppes to Batraki, where a splendid bridge, named in honor of Alexander II, crosses the Volga, with 13 spans of 350 feet each, a total of nearly a mile. Then we roll into Samara, a city of 90,000 souls, whence a branch line runs south to Orenburg, with Tashkent as its ultimate objective. This region some years ago was swept by a fearful famine that carried off the population like flies and covered the steppes with their graves. 200 miles and we reach Ufa, a town of many churches and schools, hospitals and asylums for poor and aged, libraries and museums, a town of which the poorer classes are sunk in deep ignorance like their fellows in the rest of the empire. This is one of the anomalies of Russia, utter illiteracy hand in hand with splendid equipment for learning. The train has now begun to taste the Urals, which heave themselves up between the vast plain of Russia and the vaster Siberian plain beyond. The hillsides bristle with broad expanses of fir and birch forest, but the grey rock breaks through at the summit. We pass Zulea, the famous iron district, whence have come millions of tons of metal, and reach Zlatoust, on the summit of the range. A few miles further on is the far-famed Stone of Parting, one of the most pathetic landmarks ever reared by the hand of man. A simple triangular obelisk, on one side the word Europe, on another Asia. How many tear-stained, heartbroken partings has this dumb stone witnessed? How many thousands of chained convicts have defiled here, urged by the whip of Cossack, torn from the arms of the friends that gaze sorrowfully after them from beyond the limit of Europe. We are soon on the downgrade. The scenery merges once more into that of the steppes, here covered with high grass, birch trees, and small swampy lakes. Chelyabinsk, the first station on the Siberian line proper, the junction for the line that runs northwards through Yekaterinburg, Perm, Vyatka to Kotlas on the Dwina, from which port goods are seaborne to England. This outlet of Siberian trade will be hugely developed in the future. Before passing into Siberia, let us endeavor to form an idea of that country, hitherto of darkness, now being brought to the light by the magic of the engineer. Physically, Siberia is divided into three great zones. The tundra, or frozen swamps of the north, abode of almost perpetual frost. The taiga, the most wonderful belt of forest on this earth, stretching for 1,000 miles and more, east and west between the tundra and the most valuable belt of all, the steppes, deeply covered by stoneless dark earth, which with proper cultivation will become one of the greatest granaries of the world. Were Siberia but blessed with a warmer climate, there would be no land to compare with it, such is its extent and variety. So intense is the cold, reaching to 50 degrees below zero in many places, that even during summer the earth is still frozen hard, but a few feet below the surface, while crops wave above. In winter the rivers are not merely covered with ice, but actually frozen solid. On account of the climatic conditions, the engineers met with many and great hardships and difficulties. While constructing the Trans-Baikal section, they had to blast the cuttings with dynamite, as the earth was congealed to the consistency of rock. At the stations, water supply pipes had to be laid in culverts provided with a heating apparatus, and masonry could be built only in artificially warmed shelters. The Usurian Railway was driven with the greatest difficulty through virgin forests of cedar and larch, intertwined with wild vines and creepers, and when made the track often suffered severely from the heavy floods that occurred during the best working season. Plague wrought havoc among the beasts of burden, and fever swept off many of the workmen. In the Kirghiz steppes, too, water and coal taxed the utmost exertions of the constructors. No less than 30 miles of bridges cross the many rivers over which the railway passes, and for hundreds of miles the track is protected from flood only by being raised on a 5-foot embankment above the surrounding country. In the mountainous districts of the Altai and Yablonoi, the engineers had to overcome difficulties comparable to those encountered in the Rockies and Andes. To return to Chelyabinsk, the quarantine station, where all emigrants must show a clean bill of health. Our train progresses at a leisurely 15 miles an hour through the monotonous landscape, which the iron way traverses with mathematical straightness for several leagues at a stretch. Every verst we see the watchman, an ex-convict, step from his little hut and wave his flag to show that all is right on his length. Every 20 versts or so we pass a wayside station, generally on a loop to give a clear passage to express traffic. As a rule, the stations are well built and clean, surrounded by neat palisades. each with its water tower and storehouse, earthed up to the roof to keep out the cold. Now and then in the sidings we see a third or fourth class train full of settlers on the way to their new homes, crowded like sheep into windowless trucks. Or perhaps there are windows, gridded with bars, from behind which peer the faces of convicts, bound for the prisons and mines of the interior. A fine bridge, 2,400 feet long, leads us across the Irtish into Omsk, founded by Peter the Great. It has been prophesied of Omsk that some day it will be the chief town of Siberia, as the center of a great system of waterways, and near important gold fields and copper mines, and the even more valuable coal deposits of Pavlodar, where is said to be a seam 300 feet thick, extending for miles. Vast quantities of coke will be produced here, shipped down the Irtish to Tyumen, and thence transported to the Urals for the ironworks, a supply the importance of which will be appreciated by those who know anything about the iron industry. A railway has been projected to run from Omsk southwards to join the system of Central Asia, which is also being pushed forward vigorously by the Russian military authorities. This would complete an enormous triangle with corners at Samara, Omsk, and Tashkent. 300 miles of trek through the great corn-growing steppes bring us to Obi, the end of the West Siberian section, opened in October 1896, which in 3 years has sprung from zero to a population of 14,000. Our next stopping place is Taiga, another example of rapid growth, owing to its being the junction for Tomsk. This latter town, despite its fine university, electric light, and 50,000 inhabitants, may in a few years be eclipsed by its southern newborn neighbor. The word taiga tells us what to expect in our progress. The scenery changes. The steppe gives way to mile after mile of forest, one of the most valuable assets of the Tsar, in an age when the world's timber supply has sensibly diminished. We drop down into Krasnoyarsk, the city of the Red Rock, the chief town of the Yenisei government, possessed of the finest gardens in Siberia, where imported trees fare badly. Like Omsk, it is situated on a mighty river, the Yenisei, which rises in Mongolia and takes its broad course for 2,500 miles to the Arctic Ocean. Ships come hither direct from London. On the east of the town, a fine bridge of 6 spans, each span 474 feet, clears the river. The separate spans were put together on the bank and launched into position by means of rollers and a special crane. We now rise to breast the Altai Mountains, which passed, we soon reach Irkutsk, the terminus of the Central Siberian. Irkutsk, on the Angara, the great tributary of the Yenisei, is a curious mixture of new civilization and barbarism. It owns a fine theatre that cost £30,000 and a good museum, a telegraph office whence messages may be sent all over the world, an organized telephone service stretching 50 miles into the country, an excellently equipped fire service, a noble cathedral, shops in which you may buy all the luxuries of the West, and a bank. It is also one of the 3 centers to which all gold mined in the district must be sent for tests in the government laboratories. Since its erection in 1870, the laboratory has passed £60 million worth of gold. But owing to the presence of escaped convicts, Irkutsk has been described as the one place in the Russian Empire where a man cannot feel safe. To go alone in the streets after dark is risky, as the police cannot cope with the ruffians of the place. Consequently, people retire indoors early, closely bar their doors, and before going to bed fire a revolver out of the window to warn would-be marauders and housebreakers what to expect. A short journey from Irkutsk brings us to the most interesting spot on the railway, Lake Baikal. The Holy Sea, as the Russians call it, is one of the largest freshwater lakes of the world, yielding place in size only to Superior, Huron, Michigan, and Victoria Nyanza. It has an area of 14,500 square miles, and so great is its profundity that, though its surface is 1,500 feet above sea level, its lowest depth descends several thousand feet below the bosom of the Pacific Ocean. On all sides, mountains gird it in with frowning cliffs and indent it with 80 capes. For the native it is an object of worship and superstition, since on the island of Olkhon dwells Bigdozi, the evil spirit, who must be appeased by sacrifice. From the north end flows out the Shilka, a tributary of the Lena. From the southwest the Angara, the main feeder of the Yenisei. The waters are much vexed by storms, which raise waves 6 or 7 feet high. In November the lake begins to freeze, and for 4½ months is held in the grip of winter under an ice coating 9 feet thick, traversed by huge cracks that make sleigh traffic risky and uncertain. The lake is the most serious obstacle that the engineers had to face, for the mountainous nature of its setting renders the circuit of the south end a very arduous and costly task that will not be completed for several years to come. For present purposes, the gap in the line is served by a train-carrying steamer, the Baikal, specially built for forcing a passage through the ice. Jetties supported on caissons project into the lake at the termini, separated by 42 miles of water, and by means of a platform adjustable to the varying level of the lake, transfer the train to the boat, where it is accommodated on one of the 3 tracks that are laid along the axis of the middle deck. The Baikal is a vessel of 4,000 tons, driven by 3 engines of 1,250 horsepower each, working 2 screws in the stern and 1 in the bow. The vessel was built by Sir William Armstrong, Whitworth & Co. at the Elswick Works, Newcastle on Tyne, then taken to pieces and the parts delivered at St. Petersburg. Wagons transported the pieces, the heaviest weighing about 20 tons, to Krasnoyarsk, and sleighs continued the journey to Irkutsk, whence the parts were floated down the Angara to the lake. Russian workmen, superintended by English engineers, there assembled the parts and added the boilers, pumps, and other machinery. The icebreaker is 290 feet long and of 57-foot beam. Ballast tanks, distributed in the double bottom, hold 580 tons of water. At the waterline she is protected by a belt of steel plates, reinforced with heavy wooden beams 2 feet thick. On the upper deck are spacious and comfortable saloons for the accommodation of 150 passengers. In clear water the Baikal makes 13 to 14 knots an hour. Ice 3½ feet thick gives way to her. The forward screw scoops out the water ahead, and the stern propellers force the vessel up onto the ice until her weight breaks through, her advance being 3 to 6 miles an hour. A second icebreaker, the Angara, is 195 feet long and 34 in beam, and of equal speed, but smaller ice-cleaving power. Like the sister vessel, she was transported to the lake in pieces and there assembled. While on the subject of icebreakers, among the most interesting of steam vessels, we may glance at the Yermak, built in 1898 for service in the Baltic. She has a displacement of 4,000 tons, length 305 feet, beam 71 feet, depth 42½ feet, 8,000 horsepower, speed 15 knots. Her shape is such that, when pinched in ice, she tends to rise after the manner of Nansen's Fram. On her trial trip among Arctic floes, she easily dealt with ice many feet thick, and in the Baltic she has been of the greatest use in extracting frozen-in vessels, including a warship. East of Lake Baikal, the line rises into the Yablonai Mountains, attains a maximum elevation of 3,412 feet, and descends to Naidalova, the junction of the Stretians branch and the main line, which reaches the Russian frontier at Nagadan. This is a little explored country, inhabited by Mongols, of which the chief traffic is the tea-carrying trade. The line is well laid here on heavy rails, supported by ties bedded in cement. Beyond Hailar, a town of 3,000 inhabitants, it crosses an elevated plateau to the great Khingan Range, and then drops once more to Harbin, on the Sungari River, which is the engineering headquarters of the Chinese railway. To this district legend assigns the birthplace of Genghis Khan, who in his many wars and invasions is said to have destroyed 5 or 6 million human beings. In the beginning of the 13th century he overran Western Asia with steel and fire, and today the same elements have invaded his land in turn. But the steel is in rails and the fire in the furnaces of mighty locomotives. At Harbin we can take our choice of Port Arthur or Vladivostok, the former 500, the latter 350 miles away, though on the map we appear almost at the end of our travels. Selecting Port Arthur, we jog slowly along past Mukden, the largest town yet encountered with its 200,000 souls. A short branch of 20 miles links it with the main line. Dalny, on the Gulf of Korea, is our next halting place, and a unique city. For though streets and squares have been laid out, schools and churches provided, electric light and cars installed, there is as yet no population. It is a town quickly built for the future, one that may become a great port, thanks to its situation on an open harbor which never freezes. At Port Arthur we end our roaming on the Iron Way. Here we see the mailed fist of Russia in the batteries bristling with cannon of all sizes, from the 12-inch monster to the 4-inch quick-firer, in the barracks to shelter large bodies of troops, in the torpedo boats darting in and out of the harbor under the shadow of the huge man-o'-war, in the dockyards, and in the military carriage and accoutrements of everyone we meet. 100 miles north of Port Arthur the Pekin branch diverges. Russia has thus a hold on the very throat of China. Today a regiment may be in Moscow, in 3 weeks' time its officers may issue their orders within the walls of Pekin. This then is one of the real issues of the Siberian Railway. The immense leverage that it will give to the Muscovite in any struggle with the Mongolian. Over the iron track will roll all the martial arts and engines of the West. Is the time ever coming when the Mongolian will reverse the order of things and pour his countless hordes again towards Europe, now so much nearer than in the time of great Genghis? The Russians have spent, or will have to spend, upwards of £100 million before their great line is in first-class running order. Honor to whom honor is due, the railway is a magnificent scheme, carried through with indomitable perseverance. But will it pay? This is the question asked by Russians, English, Germans, Americans, the world. There are those who are ready to utter Cassandra prophecies of broken finances, climatic deterrents to immigration, frontier troubles with the Chinese. But a far larger number see in the railway returns a promise of a bright future. It has been mentioned that the line was laid with light metals, this because the initial traffic was expected to be but moderate. What happened? Scarcely were the sections declared open than a rush set in. In 1898, 100,000 tons of goods accumulated on the western and central lines, waiting months to be forwarded to their destination. The line was utterly unable to cope with the immense body of merchandise thrust onto it. In 1899, the same thing recurred, 7,000 wagons blocking the line. Consider these figures. In 1896, the Western Siberian carried 160,000 passengers, 69,000 emigrants, 169,470 tons of merchandise. In 1897, 236,000 ordinary passengers, 78,000 emigrants, 242,000 tons. In 1898, the figures increased respectively to 535,000, 133,000, 449,000. The Central Siberian in the first year named carried 14,700 passengers. In 1898, 407,680. Merchandise increased from 16,350 tons to 250,816 tons. Since 1898, the augmentation has continued. How could it be otherwise? On the one hand, a new country, richer in gold than the Transvaal, richer in coal than any other country, richer in graphite than Ceylon and Cumberland, the greatest timber-growing country, a great future granary, bountifully stocked with valuable fur animals, a Midas treasure house of iron, copper, tin, lead, silver, salt, precious stones, the coming paradise of the hunter and tourist, a present well-developed grazing and cereal country. On the other hand, a vigorous government bent on making room for the millions that in European Russia live in a wretched state of semi-starvation, capitalists of all nations eager to invest their wealth in enterprises that may yield a huge return, a world that finds in the Trans-Siberian the shortest and quickest route from Europe to the Pacific. The Russians promise that, when their grand line is in full working order, the journey from London to Shanghai will be possible in 15 to 16 days, made up as follows: London to Moscow, 3 days; Moscow to Vladivostok, 10 days; Vladivostok to Shanghai, 3 days. This at a cost of about £50, food included. By sea the same journey costs at present nearly double this sum, and occupies rather more than double the estimated time. The following will then be the shortest route between the United States and the Far East via Siberia, New York, Havre, Paris. London passengers will go via Dover and Ostend to Cologne. Cologne, Berlin, Alexandrova, Warsaw, Moscow, Tula, Samara, Chelyabinsk, Irkutsk, Sretyensk, Mukden, Port Arthur. And the total length of this journey, excluding the Atlantic, about 7,300 miles, of which 297 miles will be in France, 99 miles in Belgium, 660 miles in Germany, 2,310 miles in European Russia, and about 4,000 miles in Asiatic Russia. These are the official figures. Another quotation bears on the same subject. From January 1905, a train de luxe composed solely of first-class carriages will be run by the company from Warsaw to Moscow and Port Arthur. The train will be run as many times weekly as the company may deem advisable. The value of the new concessions obtained by the company may be inferred from the fact that its Northern Express, its Southern Express, its Eastern Express, etc., unite all the capitals of Europe and Warsaw, where passengers will find Trans-Siberian carriages. The reason why a more thoroughly effective service of international train de luxe will not be commenced by the company before 1905 is that it is not until that year that a line running round Lake Baikal will be completed. When this line has been opened for traffic, and when the permanent way of the Trans-Siberian line has also been improved, an acceleration of the train service will be practicable. The Trans-Siberian line will not only be a means of transit between Western Europe and Japan and the north of China, but it will also be the shortest route between England and Australia. It is expected, indeed, that it will eventually be possible to reach Australia from London via Siberia in 22 days. We may here bid farewell to the great Siberian, but before leaving the confines of the Russian Empire, a word should be said of the great water schemes which are playing, and will play, as important a part in its development as the far-reaching tracks of the Iron Horse. For more than 100 years after the time of Peter the Great, Russia depended for the transportation of her population and commerce on the 60,000 miles of natural waterway with which she is endowed. Her physical configuration is such that all her large rivers rise in the plateau of the Valdai Hills, thereby affording the engineer a unique opportunity for using his arts to the immense advantage of the country at but a small comparative expense. A total of 1,000 miles of canals unites the headwaters of the Volga, Don, Dnieper, Dwina, and Duna, enabling boats to pass from the Caspian to the White Sea, from the Black Sea to the Baltic, and from St. Petersburg to the foot of the Ural Mountains. With the growth of the railway system has come a great expansion of canal mileage. It is today recognized that the era of the canal and canalized rivers, so far from being of the past, is but entering its period of greatest usefulness as the handmaid of the metal track. The Manchester Ship Canal, the Kiel Canal, the Corinthian Canal for sea-going vessels, the network of smaller channels for smaller craft that wrinkles the face of America, China, India, and Europe, are witness to this. Huge schemes are in the air, on paper, in progress. The greatest of all these in Russia is the Baltic Black Sea Ship Canal, some 2,000 miles in length. A syndicate of French and Belgian engineers offered to cut a channel 28 feet deep from the Baltic to Kherson, an important port on the Dnieper, of such amplitude as to float a heavy warship from one end to the other. The price asked was £140 million, too great for the present means of the government, though in the future the plan will probably be carried out, and so pass into the greatest of all engineering feats. Further schemes connect the Black Sea with the Sea of Azov by a canal through the narrow neck joining the Crimea to the mainland, and the Black Sea with the Caspian by uniting the Don with the Volga. A company has already offered to effect the connection for the sum of £8 million. The attempt was made 200 years ago by the great Peter, and frustrated by the physical difficulties. These include the shallowness of the Don, which at its mouth is beset with shifting sandbars. Here the powerful and effective steam dredger will have a fine field open to it in clearing away these troubles to navigation. The canal made, what possibilities would unfold themselves? The Volga, which, with its tributaries, numbers 8,000 miles, is the home of great steamers of 6,000 tons capacity, huge floating tanks of Baku petroleum, enormous timber rafts, 15,000 come down annually, barges and small vessels innumerable. On its banks are Astrakhan, Kazan, Nizhny Novgorod, where 40 million pounds changes hands at the great fair in a few weeks, and the old capital, Moscow. The Caspian is flanked on all sides by districts that will flourish by and by, and lies on the north of Persia, which country would be connected directly to the Mediterranean Sea by the proposed canal, and so obtain a northern outlet to supplement the Persian Gulf on the south. Nor do Russian plans stop at the Caspian. The conquerors of Turkestan would bend to their will the mighty Oxus, one of the most storied rivers in the world, and divert it from its present to its ancient bed, so that instead of seeking the Aral Sea, it may empty itself into the Caspian, inasmuch as the Oxus, or Amu Darya, is in places over a mile wide, has a volume 3 times that of the Danube, and draws its waters from the eternal snows of the Pamirs. The project is one that may be described as sensational. The deflection would lower the level of the Aral Sea, but would open a waterway from the whole world to the borders of Afghanistan, whither steamers already ply on the river itself. Mention has already been made of the canal that links St. Petersburg with the Urals, which oppose a wall between the Russian and Siberian waterways. On the eastern side of the range are the Obi and Yenisei, joined by a canal which renders navigation of large boats possible from the Urals to Lake Baikal, and thence to the very borders of China. Some years ago, a syndicate of private individuals tried to cut a canal through the Urals to supply the missing link between the Baltic and Mongolia. When a few miles had been finished, the fatherly government stepped in and declared that such a work was for the state to direct, and must wait for its completion until finances permit. There is a prospect that at no far distant time we shall be able to float our houseboats on a holiday trip for 6,000 miles in Russian territory through the hearts of 2 continents. These projects and feats are indeed startling proof of the new leaven that is working in that wonderful mass of despotism, militarism, officialism, guiding, grinding poverty, and benighted ignorance with the tenacious enthusiasm and genius of master minds. At present the official commands, and the moujik, poor downtrodden machine, obeys. But when the leaven has leavened the whole lump down to the poorest peasant, what will the empire that has the Trans-Siberian, Trans-Caspian, Trans-Caucasian railways to its credit, not to mention 100 works of comparable difficulty, have to fear from comparison with the mightiest nations that have ever been? End of chapter 7.
Chapter 8 of the Romance of Modern Engineering. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by BettyB. The Romance of Modern Engineering by Archibald Williams. Cairo to the Cape. What's in a name? Little, perhaps, but unite a couple of names into a catchword that neatly expresses the political wishes of a large body of people or a nation, and their influence may be great. Petersburg to Pekin has been heard in Russian circles for years, and lo, the Trans-Siberian Railway. Berlin to Baghdad, cried the German, and we learn of schemes for a railway from the Prussian capital to the Persian Gulf. We shall see what will happen. Of late years, Englishmen, too, have not lacked their alliterative phrase. The Cape to Cairo, or Cairo to the Cape. Either way it tickles the ear and is very suggestive. One sees in one's mind's eye the locomotive puffing through the terra incognita on which some little light has been thrown by Livingstone, Stanley, Grant, Speke, Grogan, and other intrepid explorers, puffing steadily ahead through forest and swamp, mountain and lofty plateau, beside great lakes and over mighty rivers, till it emerges on the sands of Egypt, or the more hospitable plains of Rhodesia. Who first conceived a trans-African railway, it is at this time hard to say, but we know who first brought the idea into prominence and took decisive steps toward its realization. That man was the great empire builder, Cecil Rhodes. Essentially a man of vast schemes, he treasured the conception of a metal highway from one end of Africa to the other, on English soil throughout almost its entire length. The railway to Khartoum grew from military necessity. The Cape lines developed to keep pace with the needs of colonization. Cecil Rhodes added Rhodesia to the British possessions and strained every nerve to traverse the new country with a line that should form an important link in the great chain, and, after vainly seeking aid from the English government, started a company to carry through his ideas. Furthermore, he approached the German emperor and obtained concessions, for a price, to carry his line through German territory to join the system of British Central Africa. His untimely death has stilled the guiding hand, but the work is carried on, and doubtless in due time the word "Fini" will be written to this important chapter in continental engineering, and we shall be able to book direct from Cairo to the Cape for the grand tour of Central Africa. The work is stupendous, and the difficulties are great, especially the political. Through unlucky want of foresight, the red portion of the map of Africa is severed by German and Belgian territory for a distance of some 350 miles. But for that break all would be plain sailing, hence, if need bids, the engineer will not be denied, as this volume endeavors to show. Owing to this foreign element in the path of the Cape to Cairo, it cannot serve strategical ends. Starting as it does from the east end of the Mediterranean, it will never be able to compete against the direct sea route from England to the Cape in point of speed. Its object is commercial. Like a gigantic backbone, it will carry the nerves of commercial life along the continent, promote local traffic, and by means of branches to the oceans on east and west, furnish outlets for the great future trade of Africa's wealthiest regions, the Central. Until a railway comes, it is impossible to judge the capabilities of those tropical countries round the Great Lakes. But let the iron way pass through, and then what wealth of cattle, grain, rubber, cotton, sugar, spices, and minerals of all sorts may reward the capitalist who has risked his money. Africa is a country to be conquered by the railway. Already the Uganda line, of which more presently, has dealt deadly blows to the slave traffic, and given us such a grip on the country as nothing else, not even the constant incursions of disciplined troops, could give. The same story will soon be told of the Cape to Cairo line. The first stage of the scheme was completed long before Mr. Rhodes had touched it with the magic of his name. In 1859, Mr. Rhodes was then 6 years old. A line was begun between Cape Town and Wellington, 58 miles away. The discovery of diamonds in Griqualand West, 1867, caused a sudden extension to Worcester, through very difficult country, where heavy gradients and sharp curves are the rule. The terminal station quickly changed its name, Matchies-Fontein, Kimberley-Vryburg, as the rail passed over the rolling Karroo. In 1885, the first train steamed into Kimberley. In 1890, Vryburg stabled the iron steed. Mr. Rhodes now came in. In 1893, the Rhodesia Railways Company was formed for driving a line through Mafeking to the Zambesi. The British South Africa Company advanced the money, and Messrs. Pauling and Company undertook the contract, with Sir Charles Metcalfe and Sir Douglas Fox as engineers. The going is easy through Bechuanaland, and consequently railhead advanced very fast. By June, 1895, Gaborone was reached. On November 4, 1897, a decorated locomotive slid into Bulawayo, 1,360 miles from Cape Town. The engineers have not halted there. To the northeast the line stretches a farther 250 miles to Salisbury, where it joins the track running southeast to Beira on the Portuguese coast. Another track runs northwest from Bulawayo to the wonky coalfields en route to the magnificent Victoria Falls. As Cecil Rhodes wished it, the spray of the falls will soon pass over the carriages. From the Zambesi the rail is destined to pass through northeastern Rhodesia, rich in minerals and rubber, to the southern end of Lake Tanganyika. From this point the route is a matter of discussion. Some people urge making use of the string of Great Lakes, Tanganyika, Kivu, Albert Edward Nyanza, the Albert Nyanza, joining them by short lines and so attaining the Nile, which would float the traveler and his merchandise down to Khartoum, where he may take his choice of river or rail. Major General Sir Rudolph von Slaten, an authority worth quoting, is entirely in favor of utilizing the Nile waterway between Khartoum and Uganda. With reference to the Cape to Cairo railway, he says, "In my opinion, it will be quite useless, and only a waste of money, to continue the railway south from Khartoum. From Khartoum to Uganda is practically impossible for a railway without the expenditure of immense capital, and in any case, during the rains, there would be so many interruptions that a line would be practically useless. As you have a waterway in this direction, and a river navigable the whole year, it would seem a waste of time and money to build a railway which could never be relied on. As the line will serve commercial purposes, it is therefore probable that for many years it will terminate at or near the Albert Nyanza. About the middle section, i.e., from the south end of Tanganyika to Albert Nyanza, Mr. E.S. Grogan, the first white man to traverse Africa from south to north, has made the following suggestions: to utilize Tanganyika from Kituta to Usambara near the north end. From that point a light railway could be laid along the flat valley of the river Rusisi to the south end of Lake Kivu, then steamer again for 60 miles to the northeast corner of the lake, whence another short line would pass through the mountains and drop gradually to Lake Albert Edward, which it would skirt on the right bank until the main stream of the Nile is reached. Except in the neighborhood of Mount Ruwenzori, the country does not afford any great physical obstacles to the engineers, whose deadliest foe probably would be the fevers that breed so freely in the swamps of Central Africa. The first feeders of the main line will, on account of geographical conditions, run in from the east coast. Already we have the Durban-Pretoria and Delagoa Bay-Pretoria railways stretching toward the backbone. Farther north is the Beira-Salisbury connection. North of that again is projected a German line from Dar es Salaam to Ujiji on Tanganyika, with a branch to the Victoria Nyanza, to which English engineers have driven the now famous Uganda Railway. A short track from Berber to Suakin would place the Cape to Cairo in communication with the Red Sea. The Uganda Railway, running from the island of Mombasa to Port Florence on the Victoria Nyanza, is 580 miles long. That is, it covers a distance 50 miles greater than the journey from London to Aberdeen. Surveys for the line were begun in 1891 and completed by 1895. The following year operations commenced at Mombasa, which was connected with the mainland by a temporary bridge, while the fine Salisbury Bridge was in course of construction. The road passes through hilly country that rises steadily for the first 360 miles, with occasional dips to an elevation of 7,800 feet. It then sinks nearly 2,000 feet into the Great Rift Valley, preparatory to a precipitous climb to Mau, 8,300 feet above sea level. Then follows a continuous drop of 4,500 feet to the lake. The engineers were much troubled with labor questions. The country is sparsely inhabited, and the natives are among the laziest folk on the earth. Mr. Grogan says in this connection, "The natives of the country, alas, were skin and bone. A 2 years' drought had driven them through starvation to death by the thousand. I saw grown men and women scrambling for grains of rice that had accumulated on the filthy ground sheets or bare floor of the Indians' tents, and women carrying huge planks by a strap round the forehead in order to earn a handful of food from the 2 hulking coolies whose work it was. All because you can't get a day's work out of an African buck nigger, even though he be starving." As a result, Indians had to be imported in large numbers. An army of 20,000 workers had to be fed, provided with water in an almost waterless country, and protected by stockades against man-eating lions which committed severe depredations among the working parties. The presence of the dreaded tsetse fly, fatal to cattle and beasts of burden, necessitated the transport of material from railhead to advance parties on men's backs, a very laborious and tedious process. Add to this the prevalence of fevers, jiggers, ulcers, and sores resulting from contact with the poisonous thorn bush through which the pioneers had to cut their way for miles at a stretch, and risings and rebellions among the natives. There is but one tunnel on the line at a point about 50 miles from the lake terminus, but there are many bridges, some half a mile long and over 100 feet high. Gradients are heavy, especially in the Rift Valley, where some very clever engineering has carried the rail down the precipitous escarpment. The chief stations are Mombasa, Kilindini, Voi, 100 miles from Mombasa, Makindo, 205, Nairobi, 345, and Nakuru, 450. Nairobi is the headquarters of the line, with workshops, engine sheds, and administrative offices. On December 19, 1901, the first locomotive reached the lake, which is now 2½ days' journey from the coast. Over the old caravan route the time was 70 days. The railway, which is of meter gauge, laid on iron and wooden sleepers, cost the government £5,206,000. In 1901, the rolling stock included 69 locomotives, 150 passenger cars, and 850 goods wagons. Now that the road is completed, a great opening up of trade may be expected. 2 steamers of 600 tons displacement are being conveyed in pieces to the lake, where they will be assembled and initiate a regular service. The Victoria Nyanza, with its 500-odd miles of coastline, taps a huge area, the trade of which will naturally gravitate to the Uganda Railway, and make it, as first in the field, the established trade route. It is therefore expected that after the year 1910, the railway will begin to give substantial returns in addition to paying its own way. Of its beneficial effect on the country there can be no possible doubt. Sir Harry Johnstone has instanced as a tangible proof of the pacific influence of the Iron Way the fact that the erstwhile cattle-raiding, man-hunting Masai has consented to lay aside his murderous assegai for the navvy's pick. The southern sections, Cape to Bulawayo, is extremely up to date. After what we have read of railway traveling in South Africa during the late war, we may be inclined to regard it as a thing to be avoided. In cattle trucks it is so, no doubt, but if you choose to lay down 15 guineas on the counter, you may travel from Cape Town to Bulawayo in a train that will compare favorably with anything to be found in England or on the continent. The train de luxe contains dining and sleeping cars, lounges, kitchens, pantries, lavatories, and bathrooms, in fact all the conveniences of modern life. Already an arrangement has been made with the Cape Government Railways, under which circular tourist tickets, available for 1 month, will be issued for all stations on the Cape and Rhodesian railways. When the tourist begins to be considered, a country is pretty well advanced. The sportsman, too, will be provided for. He will be able to hire saloon carriages by the month and travel whithersoever he wishes on the South African railway systems, keeping the saloon on a siding to act as headquarters for a shooting trip. For the sightseer, the great magnet will be the Victoria Falls, eclipsing Niagara in their grandeur. The water power running to waste will be harnessed in part before many years are out, and then we may expect to see an industrial town rising on the banks of the Zambesi, in which will be treated the copper, lead, zinc, and iron known to exist in vast deposits in central Rhodesia. Victoria Falls will thus become one of the great stations on the Cape to Cairo line, and the center of a civilization eclipsing that which has left behind it many imposing ruins at Zimbabwe and elsewhere. Side by side with the railway, but not entirely on the same route, another gigantic enterprise is being steadily pushed forward, the Transcontinental Telegraph. Work of this kind is not heralded by such a flourish of trumpets as is blown over plate laying, but its difficulties are often comparable and in many cases even greater. Here again the genius of Cecil Rhodes has been the mainspring of action. He obtained the necessary permission from the German authorities to push the slim wire through their territory. The price was heavy: a separate line at his own cost between Rhodesia and British East Africa, to be owned and used exclusively by the German government. The Rhodes section of the telegraph extends from Bulawayo to Ujiji on Lake Tanganyika, the present terminus. The following particulars of this great scheme have been kindly supplied to the writer by Mr. J. F. Jones, Joint Manager and Secretary of the British South Africa Company. At the annual meeting of the shareholders of the British South Africa Company in November, 1892, Mr. Rhodes propounded his scheme for the construction of a telegraph line to Egypt, and asked for assistance to enable him to extend the company's existing line from its terminus at Salisbury to Zamba in Nyasaland, and thence via the lakes Nyasa and Tanganyika, the ultimate object being to connect with the terminus of the Egyptian government system of telegraphs, thus placing Cape Town in through communication with Cairo and thence to England. Steps were at once taken toward the accomplishment of this design, and the African Transcontinental Company Limited was incorporated on December 27, 1892. It was decided to build the Zamba Salisbury portion from both ends simultaneously, meeting at Tete in Portuguese territory. The Mashona rising of 1896 stopped the work on the Salisbury Tete section, and when the country was pacified, it was found that the line had been practically destroyed. Mr. Rhodes therefore decided to abandon the old route, and a much better and healthier one was discovered to Tete from Umtali on the Salisbury-Beira line, passing over the high plateau of northeast Mashonaland. Whilst this line was being constructed, the line north of Tete was steadily progressing towards Abercorn at the southern end of Lake Tanganyika, which was reached at the end of 1899. It was found that the most practicable route thence to the head of the lakes was on the eastern shore in German East Africa, and an agreement, referred to above, was entered into between Mr. Rhodes and the German government, dated March 15, 1899, by which the African Transcontinental Telegraph Company was permitted to construct the line through German territory. Notwithstanding the difficult nature of the country to be traversed, the great scarcity of labor, and in many parts of water, the work was proceeded with as fast as possible, and during the month of September, 1900, the line from Abercorn to Kituta at the south end of Lake Tanganyika was constructed and opened, and in the same month the construction from Kituta into German territory was commenced, the first German telegraph office being opened at Kasanga, now called Bismarckburg, a distance of 22½ miles from Kituta. The extension of the line has been continued to Ujiji, a distance of 300 miles from Bismarckburg. Beyond this point construction is for the moment suspended, awaiting developments in the Marconi system of wireless telegraphy, which it may be expedient to adopt for certain portions of the route between Ujiji and Entebbe, owing to the very great constructional difficulties presented by the nature of the country lying to the north and east of Ujiji. In July, 1898, the British South Africa Company took over the maintenance and working of the African Transcontinental Telegraph line under an agreement with the company, and the whole line is now under the supervision of the Postmaster General of South Rhodesia. It is possible to send telegrams to any point within Rhodesia at the rate of 1 pence a word, to the Cape Colony, Natal, and Transvaal for 2 pence a word, to European countries at 2 shillings 8 pence a word. At present, 4,000 out of the 5,600 miles between the Cape and Cairo have been covered by the wire. Of the difficulties encountered, Mr. E. S. Grogan says: "The work of construction," he is here speaking particularly of the west coast of Lake Nyasa, has been attended with the greatest possible difficulties, from the precipitous and densely wooded nature of the country and the pestilential climate. These had, however, by superhuman efforts, been overcome in the stipulated time by the handful of men engaged on the work. A wide track, straight as an arrow, uphill, down dale, across abysmal chasms, and through swamps, had been cleared. An iron post set in iron shoes supported the wire. No one at home can realize the stupendous difficulties that have been overcome. But I, from observation, know, and take off my hat in awed admiration of that gallant band who, quietly, relentlessly, and without a murmur, have accomplished the seemingly impossible. It stands out in bold relief as a colossal monument of what the Anglo-Saxon can do. The general routine of construction was to send ahead of the main body a small party of surveyors to decide the path of the wires. Behind them, at a distance of anything up to 200 miles, followed an army of natives, marshaled by English engineers, who cut a broad path through jungle and forest, in the center of which the posts are placed. Each pole is 20 feet long and in two sections, the top of wrought iron, 15 feet 4 inches, gradually tapering, the lower a cast iron driving base, 5 feet long, into which the top section fits. The poles are fixed in the ground by means of an iron plate and spike and steadied by stay wires. It would of course be useless to employ wood or any material not impervious to the attacks of the white ant. The transport of the poles, which weigh 160 pounds each, was a most difficult matter. Along with wire and other material, they were shipped up the rivers in shallow draft boats to the farthest available point, and then carried by porters or beasts of burden to the scene of operations. In connection with the Tanganyika section, vessels were built in England and transferred to the lake in pieces, reassembled and loaded with material to accompany the march of the pioneers on the neighboring shore. In spite of the breadth of the clearings, the rate of vegetable growth requires constant vigilance on the part of the line tenders to prevent short circuits. A regular system of patrolling has to be employed to combat the rank vegetation. In the section from Shiroma to Chickawawa, on the Shiré River, through the tract of swampy ground known as the Elephant's Marsh, it is practically impossible to keep the grass in order, owing to the number of crocodiles with which the swamp is infested. The result is a great loss of current. Elephants cause considerable trouble by selecting the poles as their rubbing posts. When a 4-ton animal leans against a frail iron post and begins to sway backwards and forwards, something is bound to go in spite of the wire stays. The line is now so well guarded, however, that any failure is quickly remedied. Curiously enough, very little annoyance has been given by the natives. At first, indeed, some of the tribes were inclined to pull down the wires, but a few powerful electric shocks inspired them with due respect for the iron thread, which has now become fetish, even in districts where wire is the chief form of currency and therefore an object of general desire. One of the most serious blows to the expedition was the appearance of smallpox, which rages with great severity among the blacks. Panic stricken, the porters threw down their loads by the wayside and made for the bush in hundreds. The rate of construction varied greatly according to the nature of the country. In some parts the line advanced 20 miles a week, but in others, especially along the shore of Lake Nyassa, where the engineers encountered a series of marshes and dense forests, progress was very slow. In the same region, owing to the mountainous character of the country, abnormally long lengths of wire have to be used to span the deep ravines. For the present, construction is at a standstill. Whether the wires will continue their northward march to meet the Egyptian line depends on the success of Mr. Marconi's system. The distance to be traversed is great, 1,600 miles, and to flash messages plant of great power will be required, the maintenance of which may prove somewhat troublesome in the heart of Africa. Were Mr. Rhodes alive, he would doubtless urge an all-metal connection for political reasons, just as he championed an unbroken railway track from Cairo to the Cape. The English are essentially a practical nation, and both these great schemes will certainly be completed in the most practical manner, leaving sentiment on one side. End of chapter 8. Chapter 9 of The Romance of Modern Engineering. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by BettyB. The Romance of Modern Engineering by Archibald Williams. Chapter 9. The Loftiest Railway in the World. Change here for Mont Blanc. What a ridiculous thing, the reader will say, to talk of a railway journey to the summit of Europe. Well, Mont Blanc is inviolate at present. It is still a feat to reach the snowy top, and to win a head guide's diploma to show that you have attained the mountaineer's desire. But engineers are very persistent, and acting on the principle that where a man can make a path, he can make a railway, have attacked Snowdon and the Rigi and Pilatus and the Jungfrau herself. It seems a daring thing to attempt a steel track to the topmost peak of one of the loftiest Alps, over which the tourist shall roll in comfort to altitudes hitherto attainable only by sweat of brow and the exercise of iron nerves. The days are fast passing when the ascent of the Jungfrau will be considered an achievement, for electric drills are busy at work in the mountain side, scooping out a tunnel through the calcareous rock. The Jungfrau line, starting from Scheidegg, will bore its devious way upwards for 8 miles, until a point 200 feet below the summit is reached. The track will be almost entirely in tunnel. The motive force, electricity, is derived from 2 stations at Lauterbrunnen and Grindelwald, where water turbines driven by mountain streams yield an aggregate of nearly 5,000 horsepower. Urged by powerful currents, the cars will slowly climb, unseen, to the limit platform, 14,000 feet above sea level. An electric lift will transport the tourist to the very summit, which commands one of the finest views in the world, including the Finsteraarhorn, the Weisshorn, Monte Rosa, etc. That science may wait upon pleasure. An observatory will be erected for meteorological ends on the crest of the Jungfrau. This is the latter-day style of mountaineering. The Mark Twain, or Tartarin of another generation, will be mainly occupied in chronicling a series of railway journeys. How many people know where to look for the highest railway in the world? Not in Switzerland, nor in the Himalayas, where the Sibi and Darjeeling lines push far up towards the clouds, nor in the Rockies, crossed by several marvels of engineering, nor yet in Mexico, a land of great elevations. No, go to Peru. There you will find the loftiest lines hitherto laid by the engineer. Peru has 2 chief tracks, one from Callao on the coast to Arroyo on the Montana or eastern slope of the Andes, a second from Molendo on the Pacific to Lake Titicaca, throwing off a branch northwards to Santa Rosa on the road to Cusco. Both these lines pass right over the Andes. The former has a total length of 140 miles, the latter of 420 miles. Both are remarkable engineering feats, but if a comparison be instituted, the Arroyo-Lima line easily bears off the palm. In about 100 miles it rises from sea level to an altitude of 15,665 feet, or to about that of the summit of Mont Blanc. In a few hours the traveler is transported from tropical surroundings to the neighborhood of eternal snow, where for a time he falls a prey to the soroche, or mountain sickness. The line is the first section of a transcontinental route, partly by rail, partly by water over the tributaries and main stream of the Amazon. Between 1868 and 1872, the Peruvians discovered a great store of wealth in the enormous deposits of guano on the islands off the coast. Huge fortunes were made. Money was eagerly borrowed by Peru and lent by England and other countries, the greater part of which loans were spent in a lavish, almost reckless manner upon harbors, piers, and railways. Fancy prices were paid for work Costly piers and docks were constructed, and railways were projected and carried out through mountainous and desert regions, the plans of which might well have struck dismay into the most courageous engineers and investors. The construction of the Arroyo line was commenced in 1870 by Mr. Henry Meigs, the well-known American railway contractor. From Callao to Arroyo, as the crow flies, the distance is only 80 miles, but the line has a length of 140 miles owing to the multitudinous twistings and turnings, zigzags and tourniquets that distinguish its course. To its highest point, the Galera Tunnel, the railway follows the river Rimac, which it crosses repeatedly. So steep and difficult is the country that in places the line runs in galleries cut in the face of precipices by men lowered from above in boatswain's chairs, sailors proving especially useful. The rail crawls up the side of most awful chasms, every now and then plunging into the rocks to emerge perhaps onto a bridge that spans the foaming Rimac, roaring seaward hundreds of feet below. Two of the most notable crossings are those of Verrugas and the Infernillo. The first is cleared by a bridge 575 feet long, in 4 spans, and is supported by iron towers, the central one of which is 252 feet in height. This viaduct, which contains 662 1/2 tons of iron, was put together by runaway sailors accustomed to work at considerable heights. A temporary wooden staging was erected on the solid rock at each end of the viaduct, and 2 steel ropes were stretched across the valley between the towers. The various parts necessary for the erection of the piers were brought from Lima, hung on running tackle, and thus conveyed along the ropes to their destination. In spite of the difficult conditions under which the work had to be carried out, the total time occupied was but 48 days, a truly remarkable feat. At the Infernillo, where the main stream breaks through 2 perpendicular walls of solid rock 1,500 feet high, the train crosses from wall to wall, out of the tunnel on one side into the tunnel on the other over a bridge of 160 feet long, 165 feet above the seething waters. Many were the dangers to be encountered by the engineers and workmen. The work of triangulation for locating the course of tunnels and cuttings could often only be carried on from niches cut in the rock, to which the adventuresome engineer and his instruments were swung in baskets. Not less dreaded than the slippery cliffs was the verrugas fever that took a heavy toll of the laborers. This disease is peculiar to the neighborhood of the Verrugas stream, from which it gets its name. The patient is covered with large disfiguring warts, and often afflicted with them internally, in which case they usually prove fatal. It was reported that in one cutting alone, no fewer than 700 died from this loathsome fever. The difficulty of getting material up to the railhead may be imagined. Roads there were none, except such as were specially cut out of the solid rock for the passage of mules. Frequently a detour of miles had to be made to reach a point but a few yards farther along the course of the railway. But in spite of almost incredible difficulties, the engineers pushed on among the rocky fastnesses to the summit of the pass at Galera, whence the track falls away gradually to the terminus at Arroyo. Travelers who have journeyed on this remarkable line and made friends with the engineers to the extent of securing a coast on a hand car from Galera to the terminus at Callao are one and all enthusiastic over their experience. Most of us have known the delights of flying down a hill on a cycle, or perhaps we have tasted the more sudden joys of a switchback or water chute at the exhibitions. But 100-mile coast, unbroken, over steel rails, among most terrific precipices, through yawning tunnels, over giddy bridges at a speed that severely tries the nerves of the novice until he settles down to a fatalistic apathy, or, catching the infection of rapid motion, suggests a higher speed. Mr. Gallenga, in his interesting book on South America, thus describes his sensations. The hand car, a light, small, and low railway truck with 2 low-backed seats, and room for 2 in each, moving with the ease of a chariot in the so-called montagne russe, upon a gentle push from behind, acquires, after a few yards' slope, a momentum of which it would be awful to foretell the consequences were it not for the brakes with which it is supplied like an engine, and by which the driver has power to pull up in a few seconds and within a few yards of any point he may reach in his headlong career. But the driver himself, being human, delights in that entrancing rapidity of motion, and is soon almost unconsciously swayed by the fiery instincts of a racing horse. Away you go along this curve, away you tear round that corner, away you rush and dash from turning to turning, through this cutting and that tunnel, with your face barely 1 foot from the hard jagged rocks of the cutting on your right, and your knees barely 1 foot from the brink of the dizzy precipice on your left. Down you plunge into the pitch dark tunnel, yourself without a light, without a cow catcher, without a bell or whistle to scare away the stray cattle that often run to it for shelter. Away you go, neck or nothing, till all your terrors are shaken from you and you become a convert to the perfect safety doctrine, or till with a fatalist's sullen courage you set your teeth hard, you fold your arms on your breast and almost urge the driver to more speed, as if thinking that, if there is to be a smash, it may just as well be now as by and by. There are of course dangers in such a headlong rush. The curves are very sharp, and the inside rail is not sufficiently depressed to resist more than a certain amount of centrifugal force. Also rocks and stones often fall into the track, and at the sudden turns it is almost impossible to see an object a few yards ahead before the car has reached it. The ubiquitous dog, too, is found in the Andes, with its everlasting antipathy to things of swift motion. Sometimes he carries his hostility too far, and there is a collision. Well, if nothing serious results to anything except the dog. This Arroyo Railway is a very wonderful line indeed. It not only climbs higher than any other railway in the world, but provides the only road in the world down which a man on wheels can travel for over 100 miles by his own momentum, and practically at any pace to which the fiend of recklessness may urge him. You start under the eye of the eternal snows, and you finish among hummingbirds and palms. You start sick with the unspeakable sickness of soroche, and you finish in the ecstasy of an exultation too great for words. On the Darjeeling Railway the would-be scorcher may experience the same delights for a more limited period, and on the Great Divide of the Trans-American lines. End of chapter 9.
Chapter 10 of the Romance of Modern Engineering. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Prajakta. The Romance of Modern Engineering by Archibald Williams. Chapter 10. City Railways. Among the problems that perplex the civic authorities of the world's great cities, none is more difficult of solution than that which arises from the increasing congestion of traffic in the main thoroughfares. In every large town, vehicular traffic is confined to a comparatively few routes. As the town grows, the streets which do not expand their width in proportion becomes less and less adequate to pass the thousands of vehicles that crowd into them. Nowhere has the congestion become more serious than in London, where the sight of huge strings of omnibuses, cabs, and carts brought to a standstill by a block is too common to cause much comment. Travel through London streets is notoriously slow, and the delay, besides being vexatious to the individual, has been calculated to cost the community several million pounds sterling per annum. The difficulty of moving swiftly from point to point has a further bad influence as being productive of overcrowding, since the poorer classes of workers are prevented from living at a reasonable distance from the scene of their daily toil. Patent as are the needs for freer communication between the center and suburbs of large cities, the means of meeting them are restricted. Old towns, where the congestion is most acute, are often cursed with narrow streets the widening of which would be ruinously expensive. Electric trams, by monopolizing the roadway, would, in many cases, practically block all other vehicular traffic and cause great inconvenience until such time as competition in fares has driven other public vehicles off the road. It also happens that in great commercial centers such as London and New York, a large area is given up almost exclusively to offices, which at night are deserted but must be filled rapidly each morning and emptied as rapidly in the evening. Thus, to take the city of London proper, although but a square mile in area, with a day population of about 300,000 and a night population perhaps 30,000, in a single day, more than 1,250,000 persons and 100,000 vehicles enter and leave the limits. Vehicular traffic on the surface can be eased only by providing more or wider streets or by removing the necessity for the existence of a large proportion of the vehicles. The object of modern systems of communication is to replace the thousands of independent vehicles that block our streets by some ordered arrangement of transport running at regular intervals on its private tracks, out of the way of ordinary traffic. Two main methods may be distinguished: the elevated railway, which is carried aloft over the streets, and the subterranean railway that runs under the streets. In both cases, the prime object is to keep as near the main roads as possible. The states are the home of the elevated railway. The first was built in New York in 1870 on a single row of columns. By 1878, there were four such lines parallel in New York, and since that date similar tracks have been laid in Boston, Chicago, Berlin, and Liverpool. Railways of this type are especially suitable where the traffic is light and the construction of the line does not injure neighboring property. For really heavy traffic or where a line must be built at any cost, the engineer resorts to the underground railway. This may take one of three forms. It may be just under the street, separated from surface traffic by but a foot or two of steel girders and cement, as in the Budapest and New York rapid transit railways. The latter has four tracks, upraised in as many tunnels, the inner pair of fast, the outer pair for local traffic. These lines, as easily accessible from the street, are very convenient when made, but their construction entails the pulling up of the roadway, the displacement of water, gas, and sewage pipes, with all the attendant drawbacks. The second type is illustrated by the London Metropolitan and District Railways, constructed by cut and cover and shallow tunnels at such a depth 30 to 40 feet below the road level as to obviate the necessity of lifts, though deep enough to be inconvenient. The third and most modern type is the electrically worked deep level tube driven 40 to 120 feet below the roadway. Such a line is economical to build as it entails no interference with existing structures but has the disadvantages arising from the constant employment of lifts for the transport of passengers to and from the surface. For London needs, however, the tube is particularly suitable. The inner circle, completed in 1884, is most useful as furnishing a connecting link between most of the London termini of the great lines. But for the city man hastening to business, it leaves much to be desired, since it skirts the area in which his business lies and often drives him eventually to the cab or omnibus. London's crying need is for radial lines to intersect the area enclosed by the inner circle from east to west and north to south and extend into the suburbs. Already three tubes are in operation: the Central London from Shepherd's Bush to the Bank, the Waterloo and City, and the Stockwell Monument. Others are in course of construction, from Baker Street via Charing Cross to Waterloo and from the city to Finsbury. In addition, powers have been granted for new railways between Brompton and Piccadilly, Charing Cross, Euston and Hampstead, Brixton and the City, the Marble Arch and Cricklewood. A few years hence, there is every prospect of the clay on which London stands being honeycombed by tubes. From the tube to the teredo or shipworm is a far cry, yet there is an interesting connection between them. Sir Isambard Brunel, the famous builder of the first Thames tunnel, employed a shield to pierce the soft ground under the river. It is said that he derived his idea of a shield from observation of the shipworm which digs its way into wood by means of a boring apparatus in its head, and as it advances lines the hole behind it with a secretion thrown out from its body. Taking the hint from nature, he patented in 1818 a device consisting of an iron cylinder furnished at its front end with an auger-like cutter. As the cylinder advanced, the hole behind was to be lined with a spiral sheet iron plating faced on the interior with masonry. Brunel's crude idea has been immensely improved upon by himself, Mr. Peter W. Barlow and Mr. J. H. Greathead, who has given his name to the shield employed on the London tubes. The Greathead shield consists of three parts: the front, the body, and the tail. The shield is perfectly circular and cylindrical and is built up of steel plates riveted together with countersunk rivets so as to give an absolutely smooth surface on the outside. To stiffen the cylinder, a diaphragm or bulkhead in which is cut a hole for working through is fixed transversely. The front end extends forward from the diaphragm to the cutting edge, which is formed of a strong cast iron ring divided in halves, on which are secured steel knives made in short segments and forming a true circular cutting edge. The knives are arranged in such a manner that if necessary, they can be adjusted to cut a hole slightly larger than the shield. At the back of the bulkhead comes the body, in which are located the jacks, pumps, and motors for manipulating the shield. At the back end is a powerful cast iron ring to which are attached at regular intervals round the circumference the hydraulic rams for forcing the shield forward. The united power of these hydraulic jacks is immense, as even in stiff and stable clays, where the friction is at a minimum, a pressure of 4 or 5 tons for every square yard of the external surface of the shield is required, and in sticky material, the power must be increased to 18 or 24 tons per square yard of exterior shell. Each jack can be used independently of the rest, and by suitable combinations, the course of the shield is steered to a nicety. The tail of the shield serves to support the earth while the lining is being placed. For this reason, its diameter is such as just to clear the outside of the lining, which is added inside it. The details of the shield vary with the nature of the stratum penetrated. In very stable material, where caving and water inroads are unlikely, the diaphragm may be omitted, while in treacherous waterlogged materials, such as were encountered in the bed of Mersey, see page 73, and Thames during the driving of the Waterloo Baker Street tunnels, means must be provided for closing the shield entirely and converting the front end into an airtight chamber accessible through airlocks. After this short description of the boring apparatus, we will turn our attention to the sphere of its operations. The City and South London Railway, extending under the Thames from the monument of Stockwell, a distance of 3.5 miles, was begun in 1886 by Greathead. Its promoters originally intended to operate it by an endless cable, but during its construction, electric traction developed sufficiently to be applied to this first of tube railways. The tunnels running parallel are 10 feet 2 inches in diameter. The Waterloo City Tube was next constructed, and in 1896 the engineers commenced the most important of the lines at present open, the Central London Railway. The construction of the tube is very unostentatious and attracts little attention. All the public sees is a series of enclosures surrounded with hoardings, in and out of which carts pass laden with earth or strangely shaped masses of iron. A steam crane or two tells of work in progress, but there is little for the inquisitive passerby to watch. The scene of active operation is far down below his feet, where shields are steadily eating their way through the stiff London clay. Excavation proceeds from several points simultaneously. At the site of each station, a shaft is sunk and lined with cast iron segments bolted together. As soon as the shaft is completed, temporary cages are provided for bringing up the excavated material. A chamber is then cut out in which the smaller shield for driving the track tunnels is erected. Its diameter is 12 feet 8 inches. Several rings of lining, each 20 inches long, are placed and the shield adjusted so that its 6 ramps get a push off from the most advanced of them. Water power is then applied and the shield moves forward through the clay, which has been partially removed in advance. Taps are turned on and the rams retire into their cylinders, making way for the next ring, which in turn takes the pressure off the rams. The annular space left outside the lining by the tail of the shield is now filled in with liquid cement squirted through holes in the lining under pneumatic pressure. The rate of progress varies from 2 to 4 rings every 10-hour shift. For removing the clay, an ingenious form of electric excavator was used on several sections of the tunneling. The machine is a dredger ladder, the working end of which can be moved vertically, horizontally, and longitudinally. 37 buckets on an endless chain scrape the working face and carry the spoil back into the small wagons that roll under the rear end of the machine. It was found that this contrivance removed so much of the face that the shield could cut away the remainder, so obviating the need of handpicking. As soon as the men came to thoroughly understand it, the rate of advance increased rapidly and eventually 4 rings were placed in the shift. With the machine, only 6 men were required at the face, without it, 14. For clearing the stations, a large shield, 22 feet 10 inches diameter, was used, driven by 22 hydraulic rams. The stations are 325 feet long. The iron segments are filled in with cement and lined with white glazed tiles, which materially aid the illumination of the platforms. The tunnels, as a rule, run side by side, but in one or two places, for example at Newgate Street and Notting Hill Gate, where the roadway is narrow and the line must keep under the road, the tunnels curve upwards and downwards until they pass one over the other. The depth of the line varies considerably. At the bank, the metal lie 60 feet below the surface, at Oxford Circus 80 feet, at Notting Hill 92 feet. The engineers have arranged the stations on the summit of gradients, which assist the train to stop and also to start. On leaving a station, the tunnel drops at a gradient of 1 in 30 or 300 feet, and when approaching rises 1 in 60 for about 600 feet, so that the stations stand about 10 feet above the general level of the line. The most difficult part of the construction was at the bank station, where a regular network of subways cuts the existing gas and water pipes. The station space here is entirely underground, a few feet below the surface. But the station, lift shafts, and sea were made without in any way disturbing the traffic overhead. The Central London Railway was opened on July 29, 1900. It cost £3,500,000. The engineers were Sir John Fowler, Sir Benjamin Baker, and Mr. Basil Mott. The need for its construction is proved by the passenger returns, which in 1901 showed 41,188,389 tickets taken. Two objections have been raised to the tube: the vibration, which seriously annoys the occupants of houses on the route, and bad ventilation. The first could be largely removed by the employment of what is known as the multiple unit system of traction, in which every car or group of two cars is furnished with its own motors and may be cut off from the rest of the train. The displacement of the heavy pounding locomotive by motors distributed among the cars will not only lessen the vibration but render the handling of traffic much more elastic. Trains can be lengthened or shortened according to the varying requirements of the traffic at different times of day. In America, the multiple unit system is generally used on about 3,000 cars, aggregating 375,000 horsepower. Mr. Frank J. Sprague, whose name is so well known in connection with electrically operated rails, says the ideal service, so far as the passenger alone is concerned, would be by single cars operated at high speeds and following each other at the shortest possible intervals. The conditions of tunnel service, however, and the heavy character of the traffic at certain hours prohibit this ideal condition. So there must be, to get the most practical results, an expansion of the car into a train varying in length according to the time of day and a lengthening of intervals to meet the requirements of operation at high speed. Such a system radially lends itself to every condition of congested service. The similarity of equipment ensures flexibility of train operation and provides a motive power proportion to the requirements. Briefly put, one car, one motor appears as a principle better adapted to the requirements of rapid travel between frequent stations than one train, one locomotive. Two main steam lines, the Northeastern and Southwestern, have recognized the expediency and placed single motor coaches on their medals to run at short intervals between the regular train service. In course of time, we shall see the metropolitan and district railway electrified and also some of the suburban lines. In fact, it is not overbold to prophesy that the competition of tubes and trams will drive all local and suburban lines to the electric current with its far greater range of train load than is possible economically with the steam locomotive. To quote Mr. Sprague again, the electric railway has become a modern necessity and the greatest of philanthropic agents. It is a distributor of the masses and the most effective agent in solving the housing problems of the metropolis. Every minute taken from the time of transit to and from business is a minute added to the fireside and home. Every increase of speed adds to available dwelling space, increases taxable areas, augments traffic, and betters the morale of the people. The days of doubt and hesitation have long passed. Within 13 years, in the United States alone, electricity has been adopted on more miles of street, elevated and suburban track, replacing horse, cable, and steam equipments than there are miles of steam railway in Great Britain. It needs but a practical survey of all that has been accomplished in this connection to realize the immense benefits possible by an intelligent adoption of electric propulsion. The Baker Street Waterloo line, in course of construction, will be of an importance second only to that of the Central London, as it affords the much needed link from north to south along the route between Regent's Park and Charing Cross, which is at present served only by omnibuses. The extension to the south side of the Thames will also prove most convenient. This line, which commences at Baker Street, where it picks up passengers from the St. John's Wood branch, passes along the north side of the Metropolitan to the north end of Portland Place, under which it runs to Oxford Circus. Here, passengers will change on to the Central London. The line then follows Regent Street to Piccadilly Circus and doubles down the Haymarket to the east side of Trafalgar Square, passing close to Nelson's Column. Then under Northumberland Avenue to the Thames, beneath which it passes a little west of Charing Cross Bridge. As an engineering feat, this line has proved more difficult than the Central London on account of the several curves and the passage of the Thames. The first constructional work on the line was conducted from a stage built on the north of the Thames. Two vertical shafts were sunk into the bed and from them parallel tunnels driven to meet borings working southwards from Piccadilly Circus. In spite of the curvature of the route, the tunnels made so accurately that an error could scarcely be detected. The frequency with which this feat is performed shows that tunnel ranging has become a very exact science. As on the Central London, the gauge is standard, weighs 4 feet 8.5 inches, and the tunnels have an equal diameter, 11 feet 6 inches. It is expected that the line will be opened for regular traffic in 1904. Eventually, it will extend to Bishop's Road, Paddington, and so place the Great Western Railway in direct communication with the South Western via the West End. Future tube railways will have a large diameter than that of the existing systems. Expert opinion suggests 13.5 feet as affording better ventilation, facilitating repairs, and minimizing the effects of an accident. The Great Northern and City Tube is 16 feet in diameter to accommodate the steam railway's ordinary rolling stock. It may be regretted that this size was not adopted as the standard for all the tubes. If the various companies will only work in partnership and organize the various systems into an harmonious whole, London should in a few years' time be one of the best served cities in the world. End of chapter 10.
Chapter 11 of The Romance of Modern Engineering. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Romance of Modern Engineering by Archibald Williams. Chapter 11. The Severn Tunnel. Quote, "The Severn Tunnel, which is a little over 4 miles in length, is by far the most important subaqueous work yet accomplished," end quote. Mr. J. E. Tuitt in The Tower Bridge. In the west of England, the broad Severn estuary offers a serious obstruction to traffic between South Wales and the southwest counties, Cornwall, Devon, Somerset, and Dorset. At Weston-super-Mare, the channel, still several miles broad, makes a sudden turn in a northeast direction to a point some distance beyond Gloucester, thus forming a natural obstacle on the southerly flank of Wales across the main roads from the thickly populated coal fields of Wales to the great metropolis. Thomas Telford, 100 years ago, linked up the turnpike road at Gloucester by a bridge of 100-foot span so that coaches might travel unimpeded, and in 1879 was completed an iron bridge 3/4 of a mile long, which crosses the Severn 26 miles below Gloucester, enabling the midline to Bristol to tap the coal fields of the Forest of Dean, and putting the Great Western also in more direct communication with the same district. Owing to the configuration of the country in the Stroud Valley, the branch of the Great Western that passes through it towards Gloucester is characterized by very severe gradients and sharp curves that detract seriously from speed while adding considerably to the cost of haulage. To avoid this route became the policy of the enterprising directors of the Great Western. They constructed a single line from Bristol to New Passage, a point a few miles above Portishead and the Avonmouth docks. On the opposite bank, the South Wales Railway terminated near Portsmouth, a small agricultural parish. On each bank a large jetty was thrown out, and a steam ferry supplied a means of transporting goods and passengers across the Severn. This, however, was far from satisfactory. The Severn, by presenting a funnel-shaped cul-de-sac to the strong tide running in from the Atlantic, is subjected at spring tides to a rise of 50 feet, rivaling in height that of the Bay of Fundy, and surpassing anything to be witnessed elsewhere in England or on the continent. The strong currents resulting from the sudden rise and fall of the river produce a continual shifting of the sandbanks, most prejudicial to navigation, and render the embarkation at pier heads a troublesome proceeding. The Great Western directors, therefore, thought it would be to the company's interest to incur a further expense to avoid quote-unquote breaking bulk in transshipping passengers. The bold project was set on foot of driving a tunnel under the bed of the Severn from New Passage to Portsmouth, where the river is more than 2 miles wide. The lowest point of the tunnel must necessarily be under the deepest part of the channel, and unfortunately that point was within a few furlongs of the Welsh bank, where the currents have eaten out a depression known as the chutes, to a depth of some 50 feet below the general level of the bed. So that though the New Passage end of the tunnel would only be 700 yards from the river edge, the Portsmouth face would be 1 3/4 miles inland, in order to preserve an easy gradient of 1 in 100, and at each end it would be necessary to make large cuttings of a maximum depth of 80 to 90 feet, the tunnel itself to have a total length of 4.5 miles. In November 1871, Mr. Charles Richardson deposited plans for the tunnel in Parliament, and in the following year an act was passed for its construction. The Great Western Railway Company at once set to work, after obtaining the services of Sir John Hawkshaw as consulting engineer. Sir John had already gained valuable experience of tunneling in the completion of the East London Railway from Brunel's Thames Tunnel under the London docks through Wapping, Shadwell, and Whitechapel, a work of extreme difficulty. A start was made in 1873 by sinking a shaft, afterwards known as the Old Shaft, 15 feet in diameter and 200 feet deep, on the Monmouthshire side, and lining it with brick. From the bottom of the shaft, a heading, or horizontal excavation, was made riverwards in the line of the tunnel, to act as a drain that should tap the tunnel at its lowest point under the chutes. It had an upward gradient of 1 in 500, and in section was 7 foot square. Matters progressed so slowly, however, through want of a sufficient staff, that by the latter half of 1877, or after 4.5 years' work, the company who were carrying on the excavations decided to ask for tenders for the completion of the whole work. 3 estimates were sent in, one by Mr. T. A. Walker, who afterwards took so important a part in the construction of the tunnel. But the estimates being considered excessive, the company decided to continue a heading right under the river, in order to ascertain the nature of the strata to be pierced before going to the contractors. Small contracts were, however, let for the sinking of 1 shaft on the Gloucester side and 2 on the Welsh side, known as the marsh and hill shafts, and for the driving of horizontal headings both ways from the bottoms of the shafts. The company then completed a second shaft for pumping near Old Shaft and lined it with iron to within a few feet from the bottom, where it was connected to its neighbor by a short tunnel closed at the iron shaft end by a small trapdoor. On October 18, 1879, an incident took place which marked the date as a black day in the history of the tunnel. In order that the reader may understand clearly what follows, it will be necessary to explain that 40 feet above the drain heading running under the river from the bottom of Old Shaft, headings were being broken in both directions from the same shaft for the traffic tunnel, which at this spot would have risen some distance above its lowest point. Men were working in the western heading when suddenly a large body of water was tapped, and after valiant but vain efforts to stem the tide, the excavators had to fly for their lives. The water, leaping from the heading face a sheer 40 feet to the bottom of the old shaft, began to fill up the long sub-river heading, and the men there would have had all means of flight cut off but for the cross-tunnel to the iron pit, through which they escaped. In 24 hours' time, the whole of the workings in connection with Old Pit, that is to say, by far the largest portion of the excavations, were full to tide level, and the result of 7 years' labor appeared a melancholy failure. Hitherto the general opinion had been that danger from water, that untiring, wakeful foe of the tunnel driver, was to be apprehended while piercing the strata below the river. But inasmuch as the water that had burst in was fresh and sweet, it became evident that the engineers had to reckon with some subterranean supply fed by the neighboring hills. The directors decided on drastic measures. They appointed Sir John Hawkshaw engineer-in-chief, giving him powers to place a contract with someone whom he might consider to be a fit person to carry out the work. He selected Mr. T.A. Walker. This gentleman had already won his spurs as a railway surveyor and contractor in Canada, Russia, and Egypt, and under Sir John had completed the East London Railway extension referred to above. He now made a contract to finish the tunnel, cuttings, and approaches, a total length of 8 miles 26 chains. The tunnel to carry a double line of rails and be 24 feet high inside from top of arch to lowest point of invert, with a maximum width of 26 feet at the spring of the arch. In signing the agreement, he entered upon an undertaking not to be matched in engineering, unless, perhaps, we accept the driving of the Kilsby Tunnel by Robert Stephenson. A digression for a few lines will be excusable in order to remind the reader of Stephenson's famous feat. When the North-Western Railway was in course of construction, the promoters proposed to carry it through Nottingham, but the Nottinghamians would have none of the newfangled iron horse, and a detour must be made through the hills near Rugby. Stephenson faced the gigantic task of cutting a tunnel 1 1/3 mile long, after he had, by means of trial shafts, ascertained, as he thought, the exact nature of the strata to be encountered. A contractor was let to build the tunnel for £99,000. Before work had proceeded far, the unfortunate contractor ran against a large waterlogged quicksand. He died soon afterwards, heartbroken, though the company generously waived the terms of the contract. Robert Stephenson stepped into the breach, declaring that he was quite able to master the quicksand by the simple, even if expensive, method of pumping it dry. The pumps threw out water ceaselessly for 9 months at the rate of 1,600 gallons a minute, but without any apparent benefit, until the patience of the directors gave way. They said that to go on flinging good money after bad would be madness. "Give me another fortnight," replied Stephenson, and if by the end of that time matters are as bad as ever, we must abandon the tunnel. We may imagine the anxiety with which the work was watched. Every hour measurements were taken of the water flowing to the pumps. The end of the fortnight came perilously near, and still no improvement. How poor Stevenson must have despaired inwardly while keeping a brave front to his men. How deep must have been his feelings of gratitude and triumph when at the 11th hour the word went round that the water was not gaining. The quicksand was almost dry, the tunnel was saved, and completed at a cost of £300,000. Mr. Walker at once set about erecting pumps to battle with the Great Spring, as it came to be called, and to clear the flooded workings. Before these could be emptied, it was necessary to block the heading into which the spring had broken at its opening from the old pit. Accordingly, 2 shields were made of the same curvature as the shaft, sufficiently ample to cover the mouths of the headings on either side. Unfortunately, the depth of water from the surface to the headings, 140 feet, produced so great a pressure that divers could not work in it, and it became necessary to lower the water 50 feet to reduce the strain. Great trouble was experienced with the pumps, which gave way first in one part of their mechanism and then in another. But in spite of these untoward incidents, the shields were fixed by the 24th of January, 1880, and made watertight in a few days more. The Great Spring had now been cut off, but water still leaked in at the bottom of the iron pit in greater quantities than the working pumps could cope with, and there was nothing to be done but wait for the arrival of additional pumps. A new 18-foot shaft was put in hand close to the old shaft and over the line of the tunnel to act as a pumping pit. At last a long-expected pump of large capacity arrived and was fitted in the iron pit, which had been cleared to within a few feet of the bottom, when the pump burst with terrific violence, and in an hour or two the shaft was full again. The pump was repaired and replaced by October 14th. On that day, at 11 a.m., began the final struggle with the water. In 24 hours, the water had been lowered 121 feet, enabling a damaged pump to be repaired and brought into action. These 2 pumps, being able to do no more than hold the water that came in from the long sub-river heading, Mr. Walker determined to close, if possible, a door in a head wall that had been built across the heading at a point 1,000 feet from the bottom of Old Shaft. The task was one for a diver, and a brave diver too, to say nothing of the 30-foot head of water giving a pressure of 13 pounds to the square inch. He must walk up the heading, drawing 1,000 foot of hose after him, go through the wall door, close the flap of one sluice, return through the door, make it fast, and screw down a 12-inch sluice in the other side of the wall. A diver named Lambert undertook the job. 3 other divers accompanied him part way to help pass the air hose, the friction of which against the roof of the heading would have been too great for his tractive powers. He set out on his dangerous expedition armed with a short crowbar and groped his way in darkness over the debris, skips, tools, lumps of rocks, until within 100 feet of the door, when the weight of hose prevented farther progress, he was obliged to retrace his steps. 2 days afterwards, Lambert made a second attempt, wearing a flounce dress, which replaces the air hose connection by a cylinder of oxygen carried on the diver's back, but remained under water only half an hour. A third attempt was more successful. Lambert reached the door, but did not close it. The 4th trial, which lasted 80 minutes, resulted in the closing of the door and the sluices. With great anxiety, the floats that told the level were watched after pumping recommenced, but to the disappointment of all, the subsidence amounted at the most to 3 inches an hour, and at high tide to nothing at all. By the 7th of December, however, the use of additional pumps had cleared the iron pit, and the foreman was able to reach the cross wall to which Lambert had made his venturesome and perilous expedition. It was then discovered that the screw-down valve traversing the wall had a left-handed screw, so that Lambert, while closing it down as he thought, was in reality opening it to its full extent. But for this mechanical vagary, the work of pumping would have been a simple matter after the door was closed. The next thing to do was to tackle the western heading, into which the great spring had burst. The door in the shield at its pit end being open, the engineers explored the scene of the inrush. A great quantity of matter had been washed in by the water, partially blocking the heading, and it was therefore decided to keep out the water by building a wall across the heading at a point where the ground appeared firm. This work reached completion in January 1881. For 2 years the spring gave no more trouble. The year 1881 was marked by 3 notable incidents. First came the great snowstorm, still notorious, that worked havoc throughout the British Isles. It cut off communication between the tunnel and the outside world, reducing the contractors to all sorts of shifts to supply their pumping engines with steam, in the absence of a regular supply of coal from South Wales. In May, a strike broke out among the workmen, which for a few days brought the works to a complete standstill, but ended in the men returning to work as before. A month previously, the sea had found an entrance into the Gloucester sub-river heading from a shallow reach called the Salmon Pool. Fortunately for the fate of the tunnel, the long heading from the Sudbrook or Portskewett side had not quite joined that from the Gloucester bank. Otherwise, the water would have poured across the bottom of Old Pit, scouring the whole of the long heading with disastrous effect. At low water, Mr. Walker made a number of men join hands and wade into the Salmon Pool, until the sudden disappearance of one of them for a moment betrayed the whereabouts of the inlet. A schooner load of clay, dumped overboard at the spot, checked further leakage. The remaining months of 1881 and 1882 passed without any serious accidents to delay the work, which proceeded apace. The method employed in making the tunnel was to securely timber the headings, driven at what was to be the bottom level of the completed work, and from them to break up at intervals to the level of the crown of the arch. Each breakup, timbered in turn, became the end of a top heading, 6 feet high and 5 or 6 feet wide, running a few feet above the lower heading for a distance decided by the nature of the ground, technically known as quote-unquote length. The top heading finish groove is cut along the top of each side wall to receive a bulk 12 or more inches in diameter of the same length as the quote length itself. Vertical grooves are then cut in the sides, and into these are inserted props to support the longitudinal bulks. The excavators then dig into the sides farther and cut 2 more horizontal grooves rather farther from the axis of the tunnel, but lower than the first 2 crown bars. Into these, a second pair of crown bars is rolled and similarly secured by uprights, and the operation is continued until the top heading has been widened into the outline of the tunnel arch. The floor has now to be cut away, and a support provided for all the props at the end of the crown bars. A deep groove is therefore sunk across the heading to a point a little lower than the inferior ends of the props, and a massive beam, 12 to 15 inches square, let into it. A second set of props is then wedged between the sills, as the cross beams are called, and the crown bars. The lower heading is then widened and sills fixed top and bottom, separated by tightly jammed props. And then, the matter between the 2 headings being removed, a middle tier of props set between the bottom sill of the top heading and the top sill of the lower heading. If, then, the reader imagines himself to be in a length timbered ready for masonry, he will see overhead a number of horizontal and parallel balks, reaching from the highest point of the arch down each side of the tunnel to within a few feet of the bottom. Each end of the length is shut in by 2 tiers of short upright beams bearing sills, and above these again rises a third fan-shaped tier of supports taking directly the weight of the crown bars. The invert or concave tunnel bottom is then bricked, and after it the 2 sides to the spring of the arch. It now is time to set the centers, semicircular wooden frames, across the arch parallel to one another at a distance of 3 or 4 feet, and line them on their inner and outer sides with stout boards. They act as a support over which the masons can lay their bricks. Sometimes the arch is built inside the crown bars, sometimes outside them, and sometimes between them, the bars being withdrawn horizontally in turn to make room for the bricks. As soon as a length is completed, the excavators drive top headings from each end, removing the debris and bringing in timber and lining materials through the bottom heading, which acts as a common feeder to a succession of breakups, each of which has 2 working faces. This system enables the work to be pushed forward rapidly, as in the confined space of a tunnel only a limited number of men can be advantageously employed on one face. And a great economy of time results when heading, driving, chambering, timbering, and lining are in simultaneous progress at different points. The care exercised by foremen and miners is evident from the fact that out of the 1,500 links taken out, in only 1 was the timbering unequal to the strain placed upon it by the superincumbent mass. The strata encountered were of many kinds, starting from the Welsh bank, alluvium, sand, white sandstone, marl, conglomerate, millstone grit, coal shale, blue shale, clay shale, red sandstone, gray sandstone, marl, and gravel. In some places, pick and shovel work was able to cope with the strata, but in many, rock drills and blasting became necessary. When a large number of breakups were in operation, the amount of material to be transported to and from the working faces became so great that in the Gloucester half of the long heading, Mr. Walker laid down a double line of rails, between which worked a continuous steel rope, actuated by an engine at the top of seawall shaft. The rope, or bond, was carried by horizontal rollers placed on the sleepers of the road a few feet apart. When the engine was started, the rope traveled at a uniform speed of 2 miles an hour, round a large pulley situated rather more than a mile from the foot of the shaft. Men called hookers-on attached full skips to the rope, flanking the up-line or detached empty ones from the down-line rope. At the shaft bottom, the skips were placed in cages, and after being hoisted, discharged, and lowered again, returned for another load. The system works so smoothly that at times as many as 200 skips were in motion at once, and the cost was reduced to a fraction of that of the pony haulage employed at the Welsh end. The reader must bear in mind that in the early 80s the engineer was not nearly so well equipped as he is today. Electric lighting, for instance, was still in its infancy, and not only were candles largely used in the workings of the Severn Tunnel, but those electric lamps installed gave a considerable amount of trouble, and only a very inadequate amount of light according to present ideas. Rock boring machinery also was not nearly so perfect as it is today, and explosives not so effective. And not until 1882 was the telephone established in the works. Mr. Walker considers that on the very first day of its installment, it averted a strike, since a ganger in the cabin at one end of the wires overheard a man saying mutinous things in the other cabin, and by dismissing him prevented further mischief. The mining engineer is now able to apply electricity in many other ways that were unknown at that time. And last but not least, the pneumatic shield for penetrating waterlogged strata has since then become a much more efficient machine. On the 2nd of December, a curious panic seized the workmen in the long heading under the river. Mr. Walker found about 300 to 400 men at the top of the main Sudbrook shaft, all breathless and excited, some partly naked. On inquiring what was the matter, he was told that the river had broken in, but nobody appeared to be able to give any definite statement as to where it had burst through. There was no more water than usual in the pumping pit, and its color was unchanged. Accordingly, Mr. Walker and 2 foremen descended the shaft and found the heading perfectly dry, except for the ordinary drainage from small leaks. In several places, hats, kerchiefs, waistcoats, and leggings strewn the floor of the workings, marks of a hurried flight. It afterwards turned out that some water, imprisoned by an obstruction in a heading on the Gloucester side, had, on the removal of the obstacle, flowed down the long heading and topped the edge of a chute that carried any leakage. The men at the Welch end, not knowing the cause of this sudden increase in the flow, acted on a miner's advice to fly for their lives, rushing to the Sudbrook winding shaft. When passing through links of finished tunnel, says Mr. Walker, they spread out in a disorderly crowd, running perhaps 20 feet wide. Then they would come to a short length between 2 breakups, where there was only a 7-foot heading. Here they threw each other down, trampled upon each other, shouting and screaming, and then to add to the disorder, the ponies in the various breakups took the alarm and galloped down in the direction of the winding shaft, trampling on the prostrate bodies of the men. When the men reached the top of the pit, the night shift, which would go below at 2 o'clock, had already received their pay and were gathering ready to descend. It may be imagined that these men cruelly chaffed the others who had come up as soon as it was known that there was no danger below, and I have reason to think they reaped quite a harvest of neckties and other things thrown away by the others when they went down to their work. Thus ended an incident which, comical enough in itself, must have given the men concerned, no more than the contractor, a very bad quarter of an hour. Real troubles were about to occur again. At the close of May 1883, an attempt was made to open the door in the wall keeping out the great spring, but the debris behind rendered all efforts vain, and eventually a hole a foot in diameter had to be bored through the door with augers, and through this hole the men tried to clear away the impediment. This method proving impracticable, a heading was driven below the blocked heading, and a break-up made to allow the water to pass that way and permit an examination of the upper heading. The men found that the roof had fallen in for a length of 50 to 60 feet, and that there was an enormous cavity overhead. An inclined heading was therefore driven from the top heading into the cavity, and quantities of timber and other materials thrown into it to protect the bottom heading. 3 new doors were then built, one in each of the 3 headings, as a precaution against further eruptions of water. But the great spring had only been scotched. On October 10, 1883, the unwelcome news reached Mr. Walker that it was pouring into the lower heading in a larger volume than had yet been met with. He found, on descending the shaft, a river of 16 feet wide and 3 feet 6 inches deep, roaring down the 40-foot drop to the bottom of the shaft. The heading door could not be closed. The pumps could not check the inflow, and in a short time the men in the long heading were making for the Welsh shore. The next day, 52 feet of water stood in the works. The services of Lambert were again requisitioned, and this intrepid diver managed to close the door through which the water flowed. By November 3rd, the tunnel was again freed of water and the great spring in check. As though the lot of the engineers and contractors had not yet been sufficiently hard, the sea next showed its malice. The shore on the Welsh side is at the water's edge, the site of the old, iron, and new shafts, considerably above the high tide level. But farther inland there are flat, low-lying marshes, once fertile meadowland protected by a seawall, liable to be swept by spring tides. In the center of the marshes, the marsh shaft had been sunk. On October 17, 1883, the night shift had descended to their work in the headings opening from this shaft. It was a tempestuous night, the wind blowing southwest, and an unusually high tide was known to be due. Previously, no tide had ever reached the site of the shaft, and there appeared to be no reason for anxiety. But the wind working with the tide, as it did in November 1897 on the East Coast, piled up the waters in the Severn estuary to an alarming height. A great tidal wave advancing in a solid wall burst over the marshes. Some houses belonging to tin plate works were invaded by the flood to a depth of 5 or 6 feet, and the children had to be placed for safety on piled tables or shelves. The wave next attacked the pumping station and extinguished the fires. Then, meeting the shaft, it roared down a fall of 100 feet. What must have been the feelings of the unhappy miners below? A few managed to climb the ladders and escape, but one poor fellow, when halfway up, was torn off by the violence of the water and hurled into the gulf below. There remained 83 men in the shaft. As the water rose, they retreated farther up the gradient, waiting for the end. Meanwhile, others, at the ground level, were making desperate efforts to form a circular dam round the mouth of the shaft. Sacks, timber, and even clothing were used. Fortunately, the first fury of the tide was soon expended. The dam served its purpose, and preparations were made for going below with a small boat to explore the tunnel. At the bottom of the shaft, the water had risen to within 8 feet of the tunnel crown. The men were finally rescued from the breakup in which they had taken refuge and brought safely to the top. Had the tide been a few inches higher, it is probable that not one would have survived the catastrophe. The position of affairs was now indeed lamentable. Flooded headings, flooded cuttings, and a spring of unknown copiousness to reckon with. The clearing of the sea water was only a matter of time, and the workings were soon emptied, but the delays, meaning extra wages, the continually recurring need for new pumps and engines to meet some fresh catastrophe, and the huge bill for fuel had already put the contractor £100,000 out of pocket. Still, he must persevere with his arduous and wearing task. The tunnel must be finished, even if it ruined him. To the big spring, Sir John Hawkshaw and Mr. Walker now turned their earnest attention. As a preliminary to underground operations, the bed of the small river Netterne, suspected of feeding the spring, was lined with a concrete invert for nearly 4 miles. A heading was then driven parallel to the center line of the tunnel, but 40 feet to the north of it, so as to drain the spring from the flank and leave the site of the tunnel dry. The plan succeeded so well that it was possible to push on the top heading towards that running from the next shaft, and October 17th, a way lay clear from one end of the tunnel to the other. The chambering out of the spring length was, however, a difficult business, as small fissures crossed the line here and there. But at last the masons completed their work and the tunnel lining was finished. On September 5, 1885, A train passed through the tunnel from end to end, carrying the chairman of the Great Western Railway and a party of friends. Mr. Walker shortly afterwards quitted the scene of his labors for South America, where other work awaited him. His old enemy soon called him back. The great spring was giving trouble, squeezing the tunnel lining with such force that bricks flew from their settings. In order to relieve the pressure, it was decided to erect a pumping station for permanent use. Every day, water to the average amount of 24 million gallons is emptied by the pumps into the Severn, a supply sufficient, as Mr. Walker has calculated, to form annually a lake 1,000 acres in extent and 30 feet deep. The passenger whose lot it is to be plunged for some minutes into the darkness of the Severn Tunnel will, after reading these lines, be able better to appreciate the magnitude of the work needed to make his swift passage a possibility. Here are a few points for him specially to ponder upon. That the construction of the tunnel occupied 14 years and consumed over 77 million bricks. That the water pumped out during those years represent a lake 3 miles square and 30 feet deep. That though the working was conducted from more than 40 breakups, the calculations were made so accurately that when the sections joined, no deviation from absolute straightness in the 2 3/4 miles of straight tunnel could be detected by instruments. Among submarine tunnels, the Severn holds first place on the score of difficulty in construction. Mr. Walker himself confesses in his book that one such tunnel was sufficient for a lifetime. End of chapter 11.
Chapter 12 of The Romance of Modern Engineering. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Availle in September 2022. The Romance of Modern Engineering by Archibald Williams. Chapter 12. The Simplon Tunnel. An entertaining volume might be written on the conflicts between the snow-clad, storm-swept Alps and man, the soldier and engineer. How stirring is the story of Hannibal and his Carthaginians, fresh from the burning sands of Africa, pushing through the icy horrors of the little Saint Bernard. And of Napoleon, snatching a shovel from the numbed grasp of a pioneer, to lead the attack on the drifts of the pass that lay between him and the famous field of Marengo. Admirable as was the courage that enabled Carthaginian, Gaul, Goth, Hun, and Frenchman to triumph over the resistance of nature, we must not let the fascination which attends the clash of arms blind us to the romance of the later phases of the struggle, still being waged, though time has changed the fashion. Now no longer is seen the train of elephants or baggage mules, and the glitter of spear and sword and bayonet. In their place we have the iron steed climbing steadily through the rocky fastnesses, and those wonderful weapons of the engineer, the theodolite and persistent mechanical drill. Armies occupy the glens, but they are armies of workmen. Generals issue orders and direct the march, but the march is one of peace, more fraught with the good of mankind than was the passage of invading hordes. What patience and skill is represented by the great tubes that pierce Mont Cenis, Mount St. Gotthard, the Arlberg, and the Simplon. Yet the names of the men who planned and executed such deeds are unknown to the world at large, though every schoolboy is familiar with Hannibal and Napoleon. The dash into the darkness of a tunnel is so frequent an occurrence on a railway journey that we reck little of it. Perhaps sometimes, after losing sight of the sunshine for several minutes, we have a dim consciousness that there has been wonderful work done on that part of the line, and we return to the perusal of our books and papers while our train speeds on over or through other engineering triumphs. Having eyes, we see not. Think of the task that an engineer sets himself when he undertakes to burrow through a mountain for several miles. To save time, he must commence the work at both ends simultaneously. To make sure of the headings meeting, he must not put tool to rock until all his calculations have been made most carefully by compass and theodolite, and verified time after time. To deal with the water springs possibly lurking in the mountain's heart, he must drive the tunnel on a rising gradient to the center, a much more complicated feat than a perfectly rectilinear course. To give his men an atmosphere fit to breathe, special apparatus for ventilation must be installed that will force the outer air deep into the very heart of the rocky mass. All this entails years of anxious and unremitting toil. At any moment he may find himself face to face with an obstacle that threatens the ruin of his enterprise, the fall of a stratum, the inrush of a subterranean reservoir. There are many foes waiting for him. In short, so great are the uncertainties and difficulties of tunnel driving that the engineer, when confronted by a range or mountains of hills, decides in favor of burrowing only when calculation has shown that the longest way round is not the shortest way home. In adding up the total advantages of an open road in cutting and of a tunnel, there are many things to be considered and weighed one against the other, economy controlling the balance. A detour costs less in construction and is sooner open for traffic. A tunnel is shorter, less expensive to maintain, and avoids the heavy gradients of the open way. But its initial cost is enormous, both in time and money. Fortunately for international communication, the great advance in the art of tunnel building has done much to remove the principal objections to tunnels, and when the choice lies between a tunnel and a long detour with stiff gradients, the former generally wins the day. Hence some of the most remarkable engineering triumphs. The story of Mont Cenis and St. Gotthard tunnels has been told so often that it will be here but briefly recapitulated as preface to an account of an even greater undertaking still in progress beneath the Simplon. Between Italy and France runs the range known in its different portions as the Graian and Cottian Alps. Prior to 1871, the Fell Railway, laid on the road built by the first Napoleon, transported travelers across the frontier. This track proving insufficient, Italian engineers began their surveys for a tunnel under the Grand Vallon that should connect the Paris-Marseille railway system by means of a branch from Mâcon with the Italian lines that converge on Turin. The work, commenced the same year, was, thanks to the aid of the newly invented air drills of Sommelier, completed in 1871 at a total expenditure of £3 million. The following year witnessed the inauguration of a similar scheme for piercing the Mount St. Gotthard and linking up Belgium, Germany, and Switzerland with Italy via Bâle and Lucerne. Nearly 300 million francs were guaranteed by the countries most interested in the undertaking, and after the changes and chances of 10 years, marked by labor and financial difficulties, the death of Monsieur Favre, the contractor, and the Franco-German War, the tunnel was opened to traffic. In addition to the main tunnel, 9 1/3 miles long, the engineers constructed several wonderful helicoidal, that is, corkscrew-shaped tunnels on the approaches, in which the track doubles back and over itself in a manner most bewildering to the traveler. Length for length, the St. Gotthard was driven almost twice as fast as the 8-mile Mont Cenis, or more properly Grand Vallon Tunnel. The cry was still for more. A glance at the map of Switzerland reveals a railroad running from Lausanne along the north shore of Lake Geneva and on through the Rhone Valley to a terminus at Brieg. On the Italian side of the neighboring Lepontine Alps, the northern lines throw out the feeler to Arona at the south end of Lake Maggiore. Between these termini, the only present means of communication is a daily service of coaches, running over the fine mountain road. But this will soon be a thing of the past, as a tunnel is fast penetrating the Simplon in a straight line from Brieg to Izel, a small town on the upper waters of the Diviera, a tributary of the river Toce. A new railway is being built from Arona up the Toce Valley via Domodossola to complete the connection and provide a new route from Paris to Genoa by way of Dijon, Portalier, and Lausanne. The Simplon Tunnel will have an ultimate length of 12 1/3 miles, of which 12 are on the straight, the line curving away at the ends to join the open tracks. At the center there will be a level stretch of about 750 yards. From this the line falls gently on a gradient of 1 in 500 to Buffy at the Swiss end, and by a more sudden descent of 1 in 143 to Iselle in Italy. The highest point being but 2,314 feet above sea level, or 1,474 feet less than in the case of the St. Gotthard, the cost and difficulty of haulage will not be nearly as great as that of the more easterly route, and only one helical tunnel, on the Italian side, is necessary for the approaches. The Simplon differs from the Mont Cenis and St. Gotthard undertakings in that the tracks will run in separate parallel tunnels, the axes of which are 56 feet apart. At present, only one of these is being completed to full section, 19 feet 6 inches by 19 feet 6 inches. The other will be enlarged from its temporary dimensions, 10 feet by 8 feet, as soon as the need arises, at a much smaller cost than the first. Every 220 yards, cross passages are cut between the two tunnels, the most recent only remaining open to promote the proper ventilation of the workings. This subsidiary work, which for distinction's sake may be styled Tunnel No. 2, has also proved most useful for drainage, the storage of material, and as a conduit for the compressed air and water pipes. The determination of the center line of so long a tunnel running under a series of lofty peaks is no easy matter. It being impossible to pick out a straight line immediately over the proposed path of the tunnel, mark it, and guide the operations by observations of these marks from time to time, the surveyors, after setting 2 fixed points, one at each end of tunnel No. 1, had to calculate the path of the excavations by means of triangulations struck from 11 peaks, of which Monte Leone holds the central position. On the top of each summit is placed a signal, consisting of a small pillar of masonry founded on rock, and capped with a sharp-pointed cone of zinc, 1 foot 6 inches high. An observatory was built at each end of the tunnel in such a position that 3 of the summits could be seen, a condition very difficult to fulfill on the south side owing to the depth of the gorge, the mountains on either side being over 7,000 feet high. Having taken the angles to and from each visible signal, and therefrom having calculated the direction of the tunnel, it was necessary to fix, with extreme accuracy, sighting points on the axis of the tunnel, in order to avoid sighting on to the surrounding peaks for each subsequent correction of the alignment of the galleries. To do this, a theodolite 24 inches long and 2 3/8 inches in diameter, with a magnifying power of 40 times, was set up in the observatory, and about 100 readings were taken of the angles between the surrounding signals and the required sighting points. Thus, at the north end, 2 points were found about 550 yards before and behind the observatory, while on the south side, owing to the narrowness of the gorge, the points could only be placed 82 yards and 176 yards in front. One of these sighting points consists of a fine scratch ruled on a glass in an iron frame, behind which is placed an acetylene lamp. Corrections of alignment are always done by night, the whole being rigidly fixed into a niche cut into the rock, and protected from climatic and other disturbing agencies by an iron plate. The direction of heading No. 1 is checked by experts from the Government Survey Department at Lausanne about 3 times a year, and for this purpose a transit instrument is set up in the observatory. A number of three-legged iron tables are placed at intervals of 1 mile or 2 miles along the axis of tunnel number 1, and upon each of these is placed a horizontal plane, movable by means of an adjusting screw, in a direction at right angles to the axis along a graduated scale. On this plane are small sockets, into which the legs of an acetylene lamp and screen, or of the transit instrument, can be quickly and accurately placed. The screen has a vertical slit, 3 inches in height, and variable between 13/16 inches and 3/16 inches in breadth, according to the state of the atmosphere, and at a distance shows a fine thread of light. The instrument, having first been sighted on to the illuminated scratch of the sighting point, is directed up the tunnel, where a thread of light is shown from the first table. With the aid of a telephone, this light is adjusted so that its image is exactly coincident with the crosshairs, and the reading on the graduated scale is noted. This is done 4 or 5 times, the average of these readings being taken as correct, and the plane is clamped to that average. The instrument is then taken to the first table, and is placed quickly and accurately over the point just found, by means of the sockets, and the lamp is carried to the observatory. After first sighting back, a second point is given on the second table, and so on. These points are marked either temporarily in the roof of the heading by a short piece of cord hanging down, or permanently by a brass point held by a small steel cylinder, 8 inches long and 3 inches in diameter, embedded in concrete in the rock floor, and protected by a circular casting, also sunk in cement concrete, holding an iron cover resembling that of a small manhole. From time to time the alignment is checked from these points by the engineers, and after each blast the general direction is given by the hand from the temporary points. The accuracy of the surveyor's calculations is one of the greatest marvels of modern engineering. In the Mont-Cenis tunnel the error was but a matter of 1 inch in 8 miles, in the St. Gotthard about a foot in 9 miles, quite negligible quantities. The contractors, Messrs. Brandt, Brandau and Company of Hamburg, signed in May 1898 the contract for the entire completion of the work by May 13, 1904, or within 5½ years of the commencement on November 21, 1898. For every day in excess of that period, a fine of 5,000 francs, £200, will be imposed, and for every day less the contractors earn a premium of equal amount. Epidemic, war, or mutual lassitude of Italy and Switzerland are fixed as the only causes for the cessation of work. Should the operations continue for more than a year beyond the stipulated time, the contractors will hand over the execution to the Jura Simplon Company. The contract price is 69,500,000 francs, or about £2,780,000. The progress of the tunnel is shown in the following figures. In 1898, out of a total of 21,564 yards, 447 were completed. By the end of 1899, 4,227 yards. By the end of 1900, 7,947 yards. By August 1901, 10,790 yards. By June 1902, 13,345 yards. Since then, the rate of advance has been steady, and we may expect that, unless some unforeseen obstacle of unusual proportions presents itself, the work will be successfully concluded in contract time. A simple calculation shows that the average advance from November 1898 to June 1902 was 31 feet a day. During part of this period, Sunday was considered a dies non by the workmen, and the yearly holidays being also subtracted, the average then rose to 33 or 34 feet per diem. Compare this with the average 7 3/4 feet of the Mont Cenis, and the daily 13½ feet of the Mount St. Gotthard, and the rapid development of the art of tunneling is evident. In justice to M. Favre, we must, however, admit that the total section of the two Simplon tunnels is not equal to that of the single St. Gotthard, but even when due allowance has been made on this head, the contrast in speed is marked. One of the greatest difficulties in tunnel driving through mountains arises from the need of proper ventilation at the working face. The heat of a tunnel increases with the altitude of the superincumbent mass. At the center of the Simplon, where 6,000 feet of rock cover the workings, the heat would be unendurable but for artificial means of cooling, while the fumes from the explosive would render the air unfit for respiration, were it not constantly replaced by fresh supplies from outside the tunnel. The plant for ventilation and transmission of power, shops, hospitals, laundries, and other establishments for the convenience of employees are practically the same at Buffy and Inkell. It will therefore suffice to describe what is seen at the Italian end. The first thing that attracts our attention is the powerhouse, containing 3 Escher-Wyss turbines, 2 of 250 horsepower and 1 of 600 horsepower, running at 170 revolutions per minute. To these are attached 10 pumps for supplying water to hydraulic accumulators at a pressure of 1,764 pounds to the square inch. From the accumulators, the water passes through 4-inch pipes up the tunnel to the working face, where it actuates 6 rock drills to be described presently. It is fortunate for the contractor that he can, at comparatively small cost, harness the force of the Diveria to his drills. The river has been dammed about 2½ miles above the powerhouse and turned into 2 reservoirs connected with the turbines by large pipes, cast iron for the first 1,440 yards, and then built up of steel plates 1/4 inch thick. At the powerhouse, the pressure of the water is about 250 pounds to the square inch. A special pair of 200 horsepower turbines does all the ventilating of the Italian excavations. Each drives a fan 12 1/4 feet in diameter and 3 tons in weight, which forces air through a 14-inch pipe to the working face. The pipe is carried along close to the roof of the tunnel and is added to as the excavation proceeds. We noticed the 2 electric light stations, each supplying current for 32 arc lamps of 500 candle power and 116 candle power bulbs. Passing the machine tool shop, where are installed lathes, planing machines, saws, etc., all worked by turbines, we come to the smithy and foundry, a most important part of the workshop. Their principal function is to make and repair cutters for the brandbohrer, invented by and named after the contractor. Footnote. Sad to relate, the same fate overtook Messieurs Favre and Brandt, death from apoplexy before the completion of their great works. End footnote. The welfare of the employees has been provided for in the bathhouses, where every miner can have a bath or douche when he leaves the tunnel at the end of his shift, and in the laundries and drying rooms, where the dirt and moisture is removed from his clothes. Instead of a locker, each man has a numbered cord supporting 3 hooks, and a soap dish, which, when loaded with their owner's belongings, are hauled up to the ceiling out of the way and into the warm upper stratum of air. At the restaurants, excellent food is provided, for the very moderate sum of 11 pence a day. 2 pence more ensures the miner a comfortable bed in rooms lit by electric light, so that his bodily needs are well cared for. Debris is removed from and material carried into the tunnel by trucks and engines running on a line of 31½ inch gauge. The engines are of 2 types, steam and hot air. The steamers have very large boilers, so that when steam is once up, they may make the journey to and from the working phase without any need for stoking and the consequent fouling of the atmosphere. Their height to the top of the boiler is but 6 feet 6½ inches, and the short 14-inch funnel is provided with a hinge for lowering it in confined spaces. The air locomotives are used chiefly in the headings. Their freedom from fire and steam fits them for haulage in the farthest interior, where coolness is of great importance. The compressed air, driving a single cylinder that actuates the 2-foot road wheels through intermediate gearing, is stored in 27 cylinders, at a pressure of 1,030 pounds to the square inch, the supply being renewed when necessary from an air valve situated 1¾ miles from the entrance, and connected by piping with compressors at the power station. For the following description of the southern or Italian end of the excavation, the writer is largely indebted to an account that appeared in the columns of The Engineer. The men work in 3 shifts of 8 hours each. Their days reckoned, Jewish fashion, from 6 p.m. till 6 p.m. 7 days a week the operations go on, as soon as the boundary line between the 2 countries has been passed, for the Italian workmen, who obey their priests in the matter of Sabbath-keeping while in Italy, declare that they have no religion when once they enter Switzerland. This is the only blot on the undertaking, for, in the opinion of tunnel experts, no loss of time, but rather gain, is secured by allowing men, horses, and machinery to rest for the 1 day in 7. As it is, work goes on incessantly from one year's end to another, with the exception of 4 or 5 days which are particular feasts, or are days on which the special government engineers appointed for verifying the access of the tunnel require cessation of work for getting their lines into the tunnels from their telescopes and theodolites. The men are encouraged to exert themselves by a system of premiums. Each gang benefits by any daily advance over the average. The work is so unpleasant and exhausting that but for some such arrangement there would be flagging, with loss to the contractors. Trains running to a regular timetable convey men and materials in and out of the tunnel about 30 times a day, punctuality in starting and arrival being strictly observed. The air at the entrance is described by a visitor as a more sulphurous edition of that of the London Metropolitan Railway. As the face is approached, the temperature falls until we enter the comparative comfort of the fresh air supply. The tunnel is well lined with Antigorio gneiss, the spoil of the excavations. Every 100 meters a refuge is let into the southwest wall, and at every 1,000 meters small cellars have been constructed for the storage of supplies and signaling apparatus. At the tunnel station, passengers quit the train and proceed on foot to the scene of excavation, where springs of water are unpleasantly in evidence. The temperature of these inflows shows that they are due to leakage from the surface, and not to the proximity of a subterranean reservoir. On the Italian side of the mountain, the first 4,350 meters pierced were through gneiss, hard but comparatively free from moisture. Then followed a short section, 40 meters long, of micaceous schist that has proved to the contractors much what the Great Spring was to Mr. Walker in the Severn Tunnel. The schist, being softer than the rock, is squeezed into any excavation piercing it. So great was the pressure that timbers 16 inches square, packed closely together, broke up like matchwood and blocked the boring. After 6 months of hard work, the engineers succeeded in replacing the wooden with iron frames, formed of girders 15 3/4 inches deep, 6 1/8 inches wide across the flanges, and 5/8 inch thick in the plates. Stout timbers bolted to each side of the frames greatly increased their strength. In the first portion of the fault, 32 frames were placed contiguously, but in the farther part spaces of 16 to 48 inches, filled in with concrete, separated then according to the plasticity of the schist. The difficulty of erecting these frames was, as may be imagined, very great, at one time apparently insurmountable, if the engineer's vocabulary admits such a word. The delay, in addition to the extra work, entailed a great increase of speed in the boring beyond, where the rock is more amenable, to make up for lost time. The frames allow an internal passage, 8 feet 2 inches by 9 feet 2 inches. The material all round them had to be cleared away for a generous distance to emit an unusually thick lining of masonry. The removal of the schist has proved a very tedious business, since care must be taken not to leave the frames unsupported for more than a few feet at any one place. Excavation commenced by cutting a hole through one of the side posts sufficiently large to pass workmen and materials. The men chiseled a short shaft downwards, and then drove a heading under the base of the frame to the center line, and the half of the invert, or arch, with the concave side upwards, or gentler curvature than the tunnel roof, was built in. Meanwhile, other hands tunneled below the farther side of the frame, and when they too reached the center line and put in their half of the masonry, a section of the tunnel bottom was finished. The work proceeded after this manner in rings a few feet apart. The sides and upper arch have next to be dealt with. It has been proposed to build these in when the interval between the outside of the frames and the inner side of the tunnel lining has been cleared and filled with temporary masonry, which will serve as a support for the timbering in the space actually occupied by the lining. The completion of this short length will probably require a total of nearly 2 years' work. It was found impossible to drive the smaller tunnel forward through the fault, so the engineers abandoned No. 2 heading for a time, and when No. 1 heading was lined, cut a cross passage and burrowed backwards. At the working face, 3 Brandt hydraulic drills, mounted on a beam wedged across the heading, are eating holes into the rock for the reception of the blasting charges. A short description of these drills is pertinent, as they have played so important a part in the excavation. On the Mont Cenis and St. Gotthard tunnels, the holes were bored by percussion air drills, making 200 strokes a minute. During the driving of the Arlberg tunnel, 1880 to 1884, a trial was given to Brandt's invention, which revolves a hollow cutter, 2 3/4 to 3½ inches in diameter, held against the face of the rock by a hydraulic ram exerting a pressure of about 10 tons. A couple of small cylinders drive the mandrel holding the cutter through worm gearing, and the exhaust water issuing from them is shot up the center of the drill, serving the double purpose of cooling the metal and removing the detritus. The severity of the work soon wears down the 3 fangs at the cutting edge, which must be reformed in the smithy, where 300 to 500 cutters are treated daily, according to the nature of the stratum encountered, and in addition 1,000 to 3,000 hand chisels. The drills are tended by 14 or 15 of the smartest miners, capable of sustained work under most trying conditions, and supervised by a foreman and engineer. The slowly revolving cutters having made 11 holes 3 feet 3 inches to 4 feet 7 inches deep in the face, the drill beam is twisted round on its truck and run into a place of safety. Then the dynamite truck advances with its deadly load. Special workmen place 6 pounds of explosive into each hole, fix the detonators and fuses, and ram in fine borings behind as tamping. When all is ready, the fuses are lit, and everyone quickly withdraws into shelter. From their refuge the men count the reports, which are accompanied by a violent rush of air and dense fumes. The last are precipitated by jets of water from the high-pressure hydraulic main, let loose after each explosion. 10 minutes having elapsed since the last discharge, the men return to the heading to pile the debris into trucks, which are hauled out by small ponies to the air locomotives, which pass them on to the steamers. Each lift, or advance, of the drills removes 264 cubic feet of rock. In hard rock, only 3 or 4 lifts are made a day, but in soft the number rises to 8 or 10. The general method of clearing out the workings to full section is similar to that already described in connection with the Severn Tunnel. The blasted passage serves as the lower heading from which shafts are chiseled upwards to the elevation of the tunnel crown to act as starting points for the upper galleries. As soon as the arch has been quarried out, the floor separating the 2 headings is cut away, and the lower portion enlarged. Wherever necessary, an elaborate system of timbering ensures the safety of the workmen and prevents the caving in of the sides. The masons follow hard behind the excavators and put in the lining of stone. When the tunnel is completed, special attention will be paid to its ventilation. At Brieg and Iseille, the entrances are to be provided with stout curtains to turn the air from one tunnel to the other through a cross passage at the extremities. Air forced in from Brieg will travel to Iseille through one tunnel and return through the other. The same effects will result from suction. The curtains are of a material which will not offer sufficient resistance to damage a train if by accident they are not removed in time for its transit. Marseille is a long way from the Simplon, yet the Marseillaise will feel the effects of the tunnel. On the opening of the Mont-Cenis route, the eastern mail services were transferred from Marseille to Brindisi, and passengers also largely used the same means of shortening the journey to India. Another serious blow at the prosperity of the great southern French port was struck by the St. Gotthard Tunnel, which places Bâle 135 miles nearer an important harbor, Genoa, than it is to Marseille. Consequently, all the merchandise sent from England, Belgium, Holland, and German Switzerland now goes to Genoa by rail for shipment to the Mediterranean seaboard. The completion of the Simplon project will still further increase the commercial importance of Genoa at the expense of Marseille, and the position has become so serious that plans have been proposed for connecting the latter town with the Rhône at Bras-Mort by a canal 34 miles long, skirting the Gulf of Lyons for part of its course. The work is estimated to cost 8 million francs. A canal 20 feet deep would enable vessels of 1,000 tons displacement to reach points 300 miles up the river, and if the cargoes were transshipped to 300-ton barges, they could pass over the existing system of internal waterways to Nancy, Paris, Havre, and Lille. The cost of water transport being but one-half of that by rail, especially in the case of heavy merchandise such as coal and other minerals, Marseille may win back to herself much of the traffic that has been diverted by the far-away tunnels in the Alps. End of chapter 12.
Chapter 13 of the Romance of Modern Engineering. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Romance of Modern Engineering by Archibald Williams. Chapter 13. The Manchester Ship Canal. A stranger dropped suddenly among the quays and wharves of Manchester, seeing around him the great ships upwards of 9,000 tons burden, great cranes unloading cargoes, and hundreds of wagons and railway trucks receiving the same from towering warehouses, would at once exclaim, surely this is not far from the salt sea waves, and might imagine that the breezes rippling the broad expanse of water before him are blowing fresh from the open ocean. But let him board yonder vessel, just casting off her moorings for an outward voyage, and follow her fortunes for a few hours, and he will understand that the road to the true home of all this shipping is a long one, and that Manchester has lured these shapely masts and smoking funnels far into the heart of old England by a waterway that stands among the foremost of the world's engineering romances. Let us accompany our passenger, and through paper and ink see what he sees. As we pass by the long wharves lining the water, the channel gradually contracts to a width of some 250 feet, but widens to 400 as we approach the mowed wheel locks. These are two in number, the one 600 feet long by 65 broad, the other 350 feet by 45. Our vessel enters the smaller, and in 5 minutes has descended 13 feet towards sea level. We proceed for 2¼ miles over what was once the bed of the Irwell, until our attention is arrested by a curious sight. A barge, borne aloft in mid-air, and a gigantic iron trough, known as the Barton Swing Aqueduct. How did the barge get there? Look to left and right, and you behold, far above canal level, 2 iron gates. Behind these the Bridgewater Canal is bent, while a section of it is calmly swung round, also enclosed by shutters at each end, with its floating freight that we may pass. As we drop into Barton Lock, the hydraulic machinery on the mid-channel pier slowly brings the trough athwart our pathway, and in a few minutes the bargeman is urging on his horses en route to Worsley. The country north and south of us is studded with the numerous towns that make this the most thickly populated district of England. Had we but ears to hear, the whir of innumerable spindles would speak to us of the great cotton industry of which Manchester is the heart, and into which the canal is pouring the lifeblood of commerce, to be distributed by the lesser arteries and veins of waterway and railroad. A few miles, we slow up once more for the passage of Earlham Lock, which lowers us another 16 feet, and when freed we pass under a great railway bridge, and note on our left the entrance of the Mersey into the canal. Our voyage is unbroken for 7 miles. Inland-bound vessels pass us at a stately pace of 5 to 8 miles an hour. There is no need to make for a siding to give the other room, as the canal has a generous width, 120 feet at bottom, increasing to nearly double near the locks. At Rixton Junction, the canal leaves the riverbed and becomes purely artificial for the remaining 24 miles of its length. At Latchford, 14½ miles from Manchester, we again enter a lock, and drop from comparatively fresh into salt water, for at certain states of the tide no barrier is interposed between Latchford and the sea. We are now 60 feet lower than our starting point, having descended in 4 bold steps. Sailing with a straight course, we come to Runcorn, an important town on the now broadening Mersey. The river is within a stone's throw of our boat, but it will be a long time yet before we enter its waters. The canal now makes 2 sweeps, the first southwards from Runcorn, the second gradually northwards along the southern bank, behind great embankments dividing the canal from the river. Eastham reached, we pass the open lock, for the tide is up, and pass out into the Mersey at a point 35½ miles from the great cotton town. We may now glance at the history of this undertaking. As early as 1721, the necessity for efficient water communication between Manchester and Liverpool, then a rising port, caused Mr. Thomas Steers, an engineer of repute, to issue plans for canalizing the Mersey and Irwell from Warrington, to which small vessels ascended on the tideway, to Manchester. His scheme was carried out and subsequently extended to compete with the Bridgewater Canal, which united Manchester with the Mersey at Runcorn. The canal then absorbed the Mersey and Irwell navigation in 1844, and the two became formidable rivals to the railways. And finally, in 1886, both were transferred to the Manchester Ship Canal Company for the sum of £1,712,000 sterling, a sufficient proof of their importance. The first scheme for constructing a ship canal was mooted in 1825, when a company was formed to unite Manchester with the Dee by a canal 51 miles long containing 14 locks. It came to nothing, however, sharing the fate of 2 later proposals, the second of which deserves short notice. In 1840, Mr. Henry Palmer drew up a plan for the Mersey and Irwell Navigation Company. For deepening the existing waterway sufficiently to pass vessels of 400 tons burthen into Manchester. By means of training walls built in the river above Runcorn, he thought the concentrated scour of the tides might be compelled to keep open a channel with a minimum depth of 10 feet. Locks and weirs would be established in the upper river, so that ships of the size mentioned could all reach Manchester except those with fixed masts, which would be compelled to discharge cargo at Barton, where the Bridgewater Aqueduct crossed the course. In 1882, the question was again taken up, this time with great energy. 70 leading Manchester merchants and manufacturers instituted surveys and reports on the feasibility of constructing a navigation to Manchester available for ocean-going vessels. Mr. H. Fulton and Sir E. Leader Williams undertook the surveys. The former was in favor of a tidal canal all the way to Manchester, where the rise of the country would necessitate a basin 90 feet below the level of the town. His colleague, however, spoke for a locked canal above Runcorn, on the grounds that the cost of excavation would be far less, and that the presence of locks would convert the river into a series of practically still-water pounds. The latter plan was accepted by the company, which in 1883 introduced a bill into Parliament for constructive powers, but the application was thrown out by the House of Lords after passing the committee of the House of Commons. When introduced again the following year, the lower house in turn rejected it, but on a third attempt in 1885 the company gained its ends after the costs of introduction and opposition had amounted to 250,000 sterling. The committees left their mark on the bill, however, for the Act demanded that for the training walls in the Mersey should be substituted a semi-tidal canal along the Cheshire side of the estuary, entering the Mersey at Eastham, 6 miles above Liverpool, whence a good low-water channel led to the deep waters. After some hesitation on the part of the Lancashire financiers, the necessary capital was subscribed, and the late Mr. T.A. Walker, of Severn Tunnel fame, obtained the contract for 5,750,000 sterling. On November 11, 1887, the first sod was cut at Eastham. On May 21, 1894, the late Queen Victoria formally declared the whole canal open to traffic. This titanic work necessitated the excavation of 54 million cubic yards, nearly a quarter of which was sandstone rock. At the busiest period, 17,000 men were engaged, aided by 80 steam navvies and dredgers, 316 steam engines and cranes, 173 locomotives, and 6,300 wagons and trucks running on 228 miles of temporary railway, the value of which plant approached £1,000,000 sterling. The cost of the canal, including construction of works, the purchase of lands, 1,289,000 sterling, purchase of canals, 1,786,773 sterling, parliamentary expenses, general expenses, surveying, etc., amounted on January 1, 1897, to the huge total of 155,168,795 sterling, 15 shillings 11 pence, a sum greatly in excess of what the promoters had originally contemplated. It must be mentioned, however, that as the work progressed, the scheme enlarged itself in the direction of greater dock and warehouse accommodation, etc. The untimely death of Mr. Walker in 1889, by throwing the contract onto the company, involved it in considerable loss. As often happens in great engineering feats, the unknown quantity of unforeseen natural obstacles, such as faults in the strata excavated, and heavy floods, pressed hard upon the contractors and promoters. In 1890 and 1891, winter floods worked great havoc with the cuttings. One cutting, in the Earlham division, was almost completed when the natural dam at the Manchester end, shutting it off from the river, suddenly gave way under the pressure of the spate, and in 10 minutes over 250 million gallons of water had rushed into the cavity, bearing with it more than 100,000 cubic yards of material. When the water had been pumped out, under cover of a new dam, trains of wagons were found tied up in knots, and heavy machinery scattered far and wide. During the 2 years mentioned, no less than 23 miles of cuttings were filled prematurely by water, which had, of course, to be pumped out before work could proceed. Retracing the course of the canal, we will remark upon its most noticeable engineering features. Throughout its length, excavation was needed, but in varying degrees. From Eastham to Runcorn, the level of the estuary at high tide being equal to, or greater than, that of the mean level of the canal, embankments were necessary for long stretches. Between Runcorn and Latchford, where tidal action ends, the canal leaves the river and enters higher ground, necessitating cuttings from 40 to 70 feet deep. From Latchford to the junction with the Mersey again, the cutting is continued, but from the latter point to the confluence with the Irwell, embankments once more are employed to keep in the water. The upper reaches of the Irwell required further cuttings 30 to 40 feet deep. The depth of the water is kept by the locks at 26 feet throughout, the gates at Eastham being closed as soon as the tide level of the estuary has fallen to that height above the bottom of the canal. During the flow of the spring tides, the opened gates permit a greater depth up to Latchford. A peculiar feature of the canal is the rapidity with which the tides work up to Latchford, where, at high spring tides, the level is raised to 9½ feet above normal about half an hour after high tide at Eastham, 21 miles farther down. Within 2½ hours of high water at Latchford, all this extra volume has again left the canal. The result is a strong current, which in turn entails the lining of the canal side with stone facings, which also have to withstand the scouring action of a ship's wash. The latter consideration has indeed made such protection necessary throughout the canal, except in a few places where natural rock is met with of sufficient height. In the Eastham division of the canal, 3 large embankments were made, known as the Pool Hall, Ellesmere Port, and Ince Bay embankments. The method generally employed was to tip 2 parallel mounds of rubble on the foreshore to act as toes, or supports, for the lower edges of the embankment slopes. and then pile between them mounds of stiff clay. At some points the engineers encountered great difficulties, owing to the pressure of a substratum of mud or sand through which the estuary water forced its way to the workings. In Ellesmere Bay, especially, for a distance of 1 1/5 miles, a particularly staunch protection was needed, for although at that time the deep channel of the Mersey lay on the north side of the river estuary, it had formerly passed close to the southern bank, and might return thither again. Accordingly, for 5,400 feet, 2 parallel rows of piles, 1 foot square and 35 feet long, were driven down contiguously into the sand so as to form 2 wooden walls 78 feet apart, the summits of which were at the bottom of the embankment. To make these subterranean walls the more secure, 2 additional rows of piles, shorter and 6 feet apart, were sunk to the same level at distances of 20 feet from the inner row and 25 feet from the outer row, and anchored to the sheet piling by stout cross timbers. The driving of these piles, which represent a total length of 100 miles of foot square balks, would have been practically impossible, not to say ruinously expensive, had force only been used. Recourse was therefore had to the erosive action of the water jet, a device that has proved of immense use in many undertakings. A jet of high-pressure water was pumped by steam engines through a pipe of 1½ inch bore and 40 feet long, which preceded the pile in its downward course, softening and loosening the sand to such a degree that the pile easily pierced the stratum. 21 pile drivers were kept at work, the best week's record being 554 piles sunk into place. As the rows lengthened, a trench 15 feet deep was excavated behind the piles for an average width of 12 feet, and immediately filled in with rubble and clay in equal amounts. This gave a firm and watertight foundation for the superimposed embankment. At intervals, cross dams were built from side to side of the canal, so that the failure of one part of the embankment should not flood the whole of the works. Just below Runcorn Lock, a concrete wall 4,300 feet long is substituted for earthwork. The wall is founded upon sandstone rock at its extremities, the central portion resting on gravel. It has a bottom breadth of 22 feet, tapering to 16 at the summit, which is about 40 feet above the foundation. The vertical side facing the canal is protected from damage by timber fenders. This wall is in itself a large and costly piece of construction. So well have the engineers done their work that after several years the walls remain staunch and sound in spite of severe storms. Some of the most difficult portions of the canal are included in the Irland Division, which extends from the 26th to the 30th milestone above Eastham. The cutting here is deep, and as the line of the canal crosses the beds of the Mersey and the Irwell many times, construction proceeded in short lengths across the bends, the river being allowed to pursue its natural course until each chord was completed. The dams at either end were then cut, and the arc of river turned into the artificial channel, the dried bed being filled in, the spoil of the excavations. The strata of blue clay, gravel, and alluvial deposit were of such a nature as to cause the sides of the cuttings to fall in, and sometimes entirely bury the steam navvies and other plant employed in excavation. At one place a slip was burnt and replaced in the hole made by its subsidence, but as a rule the slipped material was cleared away, and lumps of rock and quarry rubbish substituted. Most of the excavating was done by steam navvies of English, French, and German design. The English machine is stationed in the bottom of a cutting, and works a great ladle attached to the end of a beam, scraping up the side of the cutting until the ladle is filled with its load of 1 to 2 tons of material. The arm then swings round, deposits the spoil onto a truck. The foreign patterns resemble ordinary marine or river dredges, the earth, etc., being collected by an endless chain of small buckets, working round a boom which is gradually lowered into the hollow eaten out by the buckets. The French navvies proved particularly useful in light soil or soft clay. The English would make deal with all sorts of material, including blasted rock, which defied the other types. Apart from the dry excavating, these machines were serviceable, as the English navvy could easily be converted into a 10-ton crane by the removal of the ladle, while a slight alteration of the French excavator fitted it for work under water. Thanks to these powerful allies, the rate of excavation, attained 250,000 cubic yards a month in the Urim division alone. Even when rock was handled, the total for the same period reached 100,000 cubic yards. In several places, the excavated material was used to need deviations constructed to carry the railroads that crossed the canal at various points. The interruption to passenger traffic would have been so great had opening bridges been employed that the canal company adopted high-level viaducts, the underside of which was 75 feet above the level of the canal. In order to preserve a gradient not exceeding 1 in 135, embankments of great length were unavoidable, and their construction cost the company no less than 875,000 sterling. There are 4 railroad deviations, one at Warrington to carry the London and North Western and Grand Junction lines, another at Latchford for the Warrington and Stockport Railway, a third at Irvine, and a fourth at Cadishead, these last 2 for the Cheshire lines. The girders spanning the canal vary in length from 150 to 300 feet according to the angle of their crossing. 9 important highroads also had to be given a passage. At Warburton and Latchford, small additions of the 4th bridge afford a permanent means of communication at the same height as the railway viaducts. The remaining 7 are swing bridges, revolving on masonry pillars, with spans ranging from 75 to 140 feet. The Moor Lane Bridge may be taken as typical. It is 238 feet from end to end of the span, the longer arm 240, the shorter 98 in length. The main girders are 27 feet 8 inches deep at the center, diminishing to 6 feet and 8 feet 9.5 inches at the extremities of the arms. These girders rest on a square of cross girders attached to the upper roller path. A live ring carrying 64 conical rollers separates this from the lower roller path on the top of the masonry pier. The whole is swung round by hydraulic machinery. The most interesting feature of the canal is undoubtedly the Barton Swing Aqueduct, to which allusion has already been made. The Bridgewater Canal, built in the 18th century for the Duke of that name by the famous Brindley, connected the Worsley coalfields with Manchester and subsequently Manchester with Liverpool. The canal was, and is, considered a wonderful feat on account of the bold project, successfully carried out, of its engineer to keep it absolutely free of locks into Manchester, by raising embankments and viaducts, and cutting tunnels wherever the ground fell away or natural obstacles intervened. To cross the Irwell, he built a stone and brick aqueduct, which was the first of its kind, and one of the 7 wonders of its time. When the Irwell became in turn a canal, the question arose how one waterway should cut the other. The smaller must of course give way to the more important, but the construction of locks from the higher to the lower level would entail a waste of water which the Bridgewater supply could not make good. Sir E. Leader Williams met the difficulty by a conception as unique as that of Brindley. The canal should not have its level interfered with, but a section of it should be bodily moved out of the way of passing steamers. The masonry was pulled down and replaced by an iron trough resting at its center on a pier rising in mid-channel. The following is a description given by its designer. The pier is mainly built of concrete, with brickwork and granite in the part that takes the weight of the aqueduct, 1,400 tons, including the water which is always in the iron trough through which the barges pass. The sides of the trough are 1 foot above the water level. It is carried by side girders 234 feet long, 22 feet 3 inches apart from the centers of the girders, which are 33 feet deep, tapering off to 28 feet 9 inches at the ends, with a side towpath carried on a gallery 9 feet above water level. Watertight iron swing gates are provided at each fixed shore end, and also at each end of the trough. When all 4 gates are open, barges pass along the canal as usual. If a ship is to pass through the aqueduct, all the gates are closed, the shore gates keeping back the water in the canal, and the other gates confining the water in the trough when it is swung open for the passage of the ship. The gates are worked by hydraulic power, as is also the trough, which can be swung with barges in it, the gross weight to be moved remaining the same. At each end of the trough, a watertight joint is made by an iron wedge piece of the shape of the cross-section of the end of the trough, both ends and bottom being faced with India rubber. The fixed and movable ends of the aqueduct are slightly tapered and about 1 foot apart. This vacancy is filled by the wedge piece, which weighs about 12 tons, and is lifted by 4 hydraulic rams sufficiently to allow the trough to be moved. the water between the gates being passed off into the ship canal. The junctions just described are not at right angles to the trough, but are slightly diagonal, so as to allow sufficient clearance for moving the trough. After it has been again closed, the wedge piece is dropped onto its seating, being of the same taper as the ends of the trough and aqueduct. The arrangement of the annular girders, rollers, etc., are the same as those for the heaviest swing bridges already described, but half the weight of the movable portion of the aqueduct is taken by a central hydraulic press, 4 feet 9 1/2 inches in diameter and 2 feet 3 inches deep, which acts as a pivot and is free to turn. A hydraulic buffer and locking bolts are also provided. The power is obtained from the adjacent hydraulic station, which is also used for the road swing bridge. The aqueduct has never given any trouble, working quickly and with smoothness, a result for which much credit is due to constructors, Messrs. Handyside and Co. Not many miles from Barton may be seen another remarkable instance of barges moved in closed troughs with the same object of avoiding lock wastage. At Anderton, some little distance south of Runcorn, the Trent and Mersey Canal meets the Weaver navigation at a point where there is a difference of 50 feet in their levels. Barges up to 100 tons displacement are transported from the one to the other by means of a double hydraulic lift, working vertically. 2 troughs, each weighing with contents 240 tons, are supported on 2 cast iron rams placed under their centers, the cylinders of which are connected by piping. When both troughs are full, the pressure on the rams is equal and no movement takes place. But on 6 inches of water being transferred by siphons from the one trough to the other, the heavier forces up the ram of the lighter. Similar lifts have since been constructed at Fontenelles on the New Fosse Canal in France, at La Louvière on the Central Belgium Canal, and at Peterborough on the Canadian Trent Canal. This last has a rise of 65 feet. The second transports vessels of 400 tons burden. Among the other chief features of the ship canal, we must include the Weaver sluices, the locks, and the Manchester docks. The River Weaver entered the Mersey about 2 1/2 miles below Runcorn. When the embankment was built between the canal and the estuary, the natural passage of the river was cut off, and it became necessary to provide means for letting the waters of the Weaver into the estuary in the same period of each tide as they would have passed into the estuary if the ship canal had not been made. Great sluices were therefore erected on the embankment on a platform of masonry 470 feet long, 3 to 4 feet thick, protected on both faces by sheet piles and stones against the undermining action of the water passing over. Steel caissons, 36 feet long and 9 feet wide, were built into the platform to contain the lower part of the piers between the sluice gates, which are 10 in number, each 30 feet wide with a lift of 13 feet. A bridge passing over the tops of the piers carries the winding gear, by means of which 2 men can easily raise the ponderous gates. Since the Weaver is practically the only route by which Cheshire salt can reach Liverpool for export, any derangement of traffic over the navigation would have spelt heavy losses to the salt mines and the British salt trade. Under the Ship Canal Acts, the company had to permit Weaver salt barges a free use of the ship canal to Eastham, unless their tonnage exceeded that of those previously used. Chemical and other traffic had to pay the usual tolls to the company. If the owners preferred it, however, the barges could drop to the Mersey at Runcorn or Weston Mersey locks. The locks on the direct course of the canal at Latchford, Earlham, Barton, and Moat Wheel are duplicated. A 600 by 65 lock lying parallel to one 350 by 45 feet. By means of intermediate gates, these can be subdivided into smaller lengths of 150 and 450 feet, and 120 and 230 feet respectively, so as to pass craft of all sizes with the greatest possible economy of time. Large culverts running along the lock walls fill the 350-foot lock in 4 1/2 minutes, and the other in proportionate time. Between the smaller lock and the southern bank of the canal, which doubles its breadth at the locks, is a weir pierced by 30-foot sluices to pass all surplus water. In flood time these are especially useful. On such occasions, some of the spate is discharged through the embankments into the upper reaches of the Mersey estuary. At Eastham, a third lock, 150 feet long, is added to the 600 and 350-foot locks, having their width increased to 80 and 50 feet. The cement used in the construction of the locks was subjected to severe tests, a notice of which may be interesting to those readers who are unacquainted with the properties of this material. The cement was tested 14 days after delivery. Samples taken from every 30 tons were first passed through sieves of 2,000 meshes to the square inch, and all cement rejected which left a residue of more than 10% in the sieve. Briquettes having a sectional area of 2.5 square inches were then made and submerged in water for 8 days, at the end of which time their power to resist tensile stress was proved. The minimum permitted was a pull of 700 pounds. Some stood a stress of 3,000 pounds, or about 1 1/4 tons without breaking, but the average resistance was about 1,000 pounds. All cement used in the fourth bridge foundation had to undergo equally severe tests, for we read that the contractors required a briquette of 1 square inch section to resist a pull of 400 pounds at the end of 7 days. In fact, owing to the large amounts now used, cement for all important works is submitted to a rigorous system of testing and analysis before being accepted from the manufacturers. The Manchester and Salford docks, which commence at mowed wheel locks, have an area of 104 acres, 152 acres of quay space, and a frontage of 5 miles. These figures are, however, only temporary, since new docks are in course of construction. Dock number 9 will alone have a frontage of over a mile, and dock number 10 will be of almost equal dimensions. The quays carry sheds and warehouses rising to 7 stories, and over 30 miles of railway sidings. They are equipped with steam, hydraulic, and electric cranes, and other appliances for quick dispatch. There is also a grain elevator of 40,000 tons capacity. That, owing to the huge expenditure incurred by the company, the shareholders of ordinary stock do not find their investments profitable, will be evident enough on reference to the quotations of the money market. At the same time, it would be a great mistake to condemn this magnificent engineering achievement as a commercial white elephant. We must remember that the ship canal is in direct communication with the whole of the inland navigations of the country, that the area to and from which the canal traffic is carted contains 2.5 million people, and that in the districts nearer to the canal than to any other ocean steamship port is found 1/5 of the population of the British Isles. A city far inland has become a seaport, with facilities equal to any on the coast, and this in spite of great opposition from rival interests and almost insuperable physical obstacles. Why? Because Manchester is the center of one of England's greatest industries, which, owing to its natural position, was severely handicapped in competition with other progressive countries by the cost of transport to and from the ocean ports. If Manchester meant to hold her own, freights must be delivered at her very doors, unbroken, since breaking bulk often ate up the manufacturer's profits. The reduction in cost of transport and handling these 6 million tons of cotton imported annually into the Manchester district is amounted to 500,000 sterling, and the total benefit under this heading to the community may be reckoned at more than double that sum. A most eloquent testimony to the usefulness of the canal is the external change that has come over the face of Manchester. Previously to 1880, the city showed decided traces of incipient decay. Many large works were moving to Glasgow and other ports, where they could save the excessive costs of carriage. Empty warehouses boded the migration of trade. Since the opening of the canal, new industries have started at the terminus and along the banks. The deserted mills and warehouses again teem with life. Miles of new streets have been laid out, and renewed activity is seen on all sides. The traffic returns increase steadily from year to year. In 1896, the whole receipts of the Ship Canal Department were 182,000 sterling. In 1902, they had risen to 358,491 sterling, or nearly double. In 1896, the profits were 65 sterling. In 1902, 140,955 sterling. These figures show that though large accessions of traffic bring an increase in expenditure, that increase is not in proportion to the tonnage. The directors of the company do their utmost to encourage merchants to use their canal. Already suggestions have been made for deepening the canal a couple of feet to accommodate vessels of 11,000 tons capacity, double the size of the largest cargo steamer afloat when the act was obtained in 1885 for the construction of the canal. Established lines of steamers ply between Manchester, America, the Mediterranean, and other parts of the world. As recently as 1903, a regular fortnightly service was inaugurated with Boston, and the number of monthly sailings steadily augments. Whatever may be the future fortunes of the canal, nothing can detract from the public-spirited policy that brought it to completion, or from the skill and perseverance of its engineers. When Macaulay's New Zealander of the future has wearied of gazing upon the ruins of St. Paul's from the broken arches of the London Bridge, he might with profit turn his steps to the north. We feel confident that after a journey from end to end of the canal, even if its channel has silted in, and its locks and wharves have fallen into decay, his verdict will be, the people that did this work must have been a mighty race. End of chapter 13.